Okay, I think we should get going. Hopefully everybody can hear me. So we'll start with Everett Joseph. He's the NCAR director, so he'll have a few welcoming remarks. Everett, please go ahead.
Okay, thanks, Gokhan. Can you hear me okay and see me okay?
Yes, yep.
Okay, wonderful. Welcome everyone from whatever time zone that you are in, given the global audience that we have here today. It is a beautiful early morning here in Boulder, Colorado. I hope that you are safe and doing well. It's really my pleasure to welcome you to the 26th CESM Annual Workshop. I first want to thank Gokhan, Elizabeth, and the team of NCAR staff, NSF, and certainly the CESM Working Groups for all the hard work to organize this meeting. Just because it's virtual doesn't mean that it's easy. And so lots of technical issues, lots of coordination, and I really just want to thank them for their fantastic effort to organize this meeting. I would like to welcome everyone from across the US again and from the international community. Gokhan tells me that registration is on the order of 700, as it was for last year's virtual meeting. And that's truly amazing. We are absolutely thrilled with this level of interest and participation. This really demonstrates the strong community interest in CESM science. And this engagement follows from the world-class performance of the CESM simulations enabled by the community contributions to the system, and those contributions include from many of the attendees to this workshop. So we thank you for that. I would particularly like to welcome graduate students, postdocs, and early career scientists. I attended this meeting as a graduate student and as an assistant professor, and it was very beneficial to me. Access to these online meetings to early career scientists is really one of the upside, one of the positive outcomes of the virtual world that we operate in today. However, as we all know, the downside of virtual meetings is that there's limited ability to network. This has impacted us, but early career scientists the most. At NCAR, we have been very concerned about the overall impact of the pandemic on our early career colleagues, especially those with dependent care, for example. We are working really hard to develop a number of programs to mitigate the impact. Looking at the agenda, the CSM teams has built in lots of networking time into the agenda, and I really urge both early career scientists and more seasoned scientists who've been around to really take advantage of these sessions. They're no substitute for the networking that happens at regular in-person meeting. But it's the best that we can do at this time. Networking is such a critical part of how we do our science. So I urge you to participate in those opportunities. Speaking of access, broadening participation is a top priority at NCAR. As you know, it is a top priority for our new administration in the US and a top priority for NSF. At NCAR, we are specifically focused on diversifying the NCAR workforce and significantly increasing our engagement of minority serving institutions and non-traditional institutions in general. We have a history of being engaged with minority serving institutions to education and outreach programs, but we want to build on that and particularly scale up our engagement on scientific research. We think that there's a lot of room there to improve it in that sense. However, what we're doing is we're being very careful. We're really working on what we call best practices and guiding principles of how we build those partnerships, which we think is really critically important to their success and mutual benefit. We are promoting MSI partnerships that prioritize capacity building at the MSI that's sensitive to the workload of MSI scientists, especially at a number of the atmospheric sciences programs that we can think about that tend to be resource limited departments. And we're exploiting and we're promoting what we call non-exploitive and non-extractive engagements. For example, if you have an MSI partner on a proposal, not relegating them to the education and outreach activities of the proposal or just as a source of students for your program. At NSF, we want to center the partnership on science, on increasing the participation and leadership of MSI scientists on proposals, in peer review publication, and in leading experiments. And I really want to commend the CESM leadership, GOCON in particular, for their efforts on reaching out to non-traditional and minority serving institutions and other underrepresented groups in Earth system modeling to entrain these groups into our workshops and tutorials. The CESM leadership has also made significant effort in diversifying CESM leadership, the CAB, the SSC membership, and also working group chair. So thank you very much. The workshop agenda is impressive for this meeting. In addition to historically important report outs from working groups, the agenda includes several new cross-disciplinary topics, such as how to properly represent fires in climate simulations, application opportunities for machine learning, and other planetary scenarios, which should be very, very exciting topics. Further, you will hear plenary talks from invited speakers, including Dr. Valerie Manson-Damont, Dr. Francisco Doblas Reyes, and Dr. Gregory Jenkins, who will provide insight on climate change state of the knowledge, model development for the Destination Earth program, and climate justice challenges and opportunities, respectively. NCAR is proud to help foster the development of the CESM system. Unified modeling is a critical component of our latest strategic plan, and we are implementing strategies to bolster our capabilities to address societally relevant, actionable science. Our focus on actionable science is not at the expense of the fundamental research that we do. We hear concerns about that all the time, and we want to be very clear. It's not at the expense of the fundamental research that we do, but it's conducting our research from that research from a more use-inspired perspective, driven by complex problems, and conducting that research through deep engagement across our own disciplines and across other disciplines such as computational sciences, mathematics, and beyond to disciplines such as engineering and human dimension research. We are also actively developing our capabilities by bridging our modeling systems, enabling large eddy through climate simulations with a unified modeling framework built by NCAR and for the broader user community. NSF has been critical in supplementing our modeling system development, and we really want to be thankful to NSF for their efforts. We're also really ultimately indebted to you, our community, and we really look forward to working with you in the co-design and co-development of CESM version 3. I would be remiss from my position if I did not acknowledge the news coming out of Washington, D.C. about climate. There are two activities that we are here at NCAR and NCAR leadership we're keeping our eyes on. The first is a National Academy of Science, Engineering, and Medicine study sponsored by the NSF GEO on how the NSF, the National Science Foundation, can take a system approach to studying the Earth. The Academy Committee conducting this study has held a number of discussions and workshops on education, on workforce, computing, and the integration with social science. A couple of weeks ago, we had the opportunity to participate in a roundtable session with other geoscience facility leaders on the role of facilities in Earth system science. We will continue to follow the committee and the work of the committee and ensure that we remain engaged to the extent possible. The other issue we're keeping our eyes on is the federal budget and the opportunities for NSF and for climate research and for our community. These are truly potentially transformational opportunities for our community to advance work on climate in both fundamental and use-inspired research. We are working, at NCAR, we're working very closely with UCAR to monitor the progress of the budget and to understand how NSF plans to implement any new investments in the community. And we're positioning ourselves to assist NSF in that endeavor. Finally, I hope you have an exciting and highly productive workshop, and look forward to hearing more on how we can work together to understand climate change and the vulnerabilities to meet the needs of the global society. And with that, I'll just again, thank you very much and turn it back over to Gokhan.
Thank you very much, Everett. That was very nice. Thank you. So I'll share my screen. I just wanted to also, before I start my presentation, I would like to remind everybody our code of conduct at NCAR. Please obey it, and you already acknowledged it when you registered. Thank you. So I'm Gökhan Danabashoğlu. I'm the CESM Chief Scientist, and I too would like to welcome you to this 26th Annual CESM Workshop. What I'll try to do in this presentation is to provide some updates on several large community projects and simulations, as well as on a few new and ongoing science and development efforts. And I would like to note that many of the topics that I'm going to touch upon this morning will be covered in much more greater detail during either working group or cross-working group sessions. So I'll start with the AGU CESM2 virtual special issue. The collection of manuscripts included in this issue contains details of our CESM2 CMIP6 simulations, as well as their detailed analysis. These are truly community efforts. They involve a lot of co-authors from the university community, and many of the manuscripts are led by the community. As of now, we have 43 published manuscripts, and several of the manuscripts are still in review. These articles are available at both the AGU site. They are only including, of course, the published manuscripts, and they're all open access. And you can also visit our CESM publications website, which includes the manuscripts also in review. And I just wanted to remind people that the overview manuscript for CESM2 was published earlier last year, and it's I just included its title and reference to it here. More recently, Jean-Francois and I led or wrote an opinion piece in EOS advertising this particular special issue. We included some highlights as well as a summary of our sort of challenges that we encountered during the CESM2 development phase. Regarding CESM2 releases, since December 2018, we had three what we call incremental releases of CESM. These were non-answer changing releases. They simply further expand the available set of out-of-the-box configurations for readily performing the CMIP deck, historical, and any MIP Tier 1 simulations for CMIP6 purposes. In late September 2020, we had another CESM release, CESM 2.2. This was an answer-changing release. It contains many new developments since 2018, including a functional release of our new ocean component. That's the modular ocean model version 6, MOM6, to be used in CESM 3. One of the major efforts over the last year has been the creation of CESM, a new CESM2 large ensemble. This is a major partnership collaboration with the Institute for Basic Science, Center for Climate Physics, ICCP, in Busan, South Korea. This new ensemble contains 100 ensemble members, and it's for the entire 250-year period from 1850 all the way to 2100. And we used SSP 3.70 scenario for the future extension part. I'm quite delighted to let you know that the data sets from these CESM2 large ensemble simulations are being just released today. And Keith Rogers from ICCP will be presenting additional details this afternoon at 4:20. He'll provide also the information related to how to access the data sets. And we'll be sending also a separate email to the CESM community with additional details. I just wanted to include sort of a teaser plot from Keith's presentation here. The plot here shows the expansion of the growing season length, considering net ecosystem production. This can be also looked at as carbon uptake within the system. And it is showing the ensemble mean seasonal cycle of the net ecosystem production. The bluer colors are showing 1850-ish or early in the integration. And as we go to warmer colors, they show what's happening in the future, the last one being the 5-year average near 2100. And you can, perhaps not surprisingly, you can see the increase of the growing season. It starts 2 weeks earlier, and it ends roughly 1 week later with respect to the 1850. Another interesting feature is that the amplitude or the peak of the net ecosystem production increases more than doubles actually by the time we reach 2100. Again, Keith Rogers will be talking about these simulations in more detail. Another set of simulations that we actually performed were with CESM high resolution version. These use an older version of CESM 1.3, and these were conducted or performed by the International Laboratory for High Resolution Earth System Prediction, or IHASP. They use nominal 1/10 of a degree ocean and sea ice resolution and 1/4 of a degree atmosphere and land resolution. To date, we have completed a 650-year pre-industrial control, an 80-year 1% CO2 simulation, 3 members of the 1850-2100 transient simulation, all of the high-res MIP coupled and AMIP simulations, and finally, 5 cycles of the OMIP, that's ocean sea ice coupled simulations for the 1958-2018 period. Our ongoing simulations include decadal prediction cases, 4 times CO2 quadrupling experiment, and additional members for the transient simulations. And I would like to note that by the completion of this, when we complete this 4 times CO2 case, we will be completing full deck simulations. So I think that's an important milestone. And regarding data releases, again, I'm delighted to tell you that on Saturday, we actually released additional data sets. And you can check the IHASP website at Texas A&M University. Now the PI control is extended all the way to 500 in terms of its released data sets. We included in the release one member of the transient simulations. And I note that also all high-res MIP simulations were already released to the community as part of our high-res MIP contribution. All of the corresponding low-resolution simulations are also available for the community. Earth System Prediction Working Group have been performing a few new sets of prediction simulations, and one of them is the SMILE project. It stands for Seasonal to Multi-Year Large Ensemble. This is a new initiative. It's a new set of initialized hindcast simulations using CESM2. These are only 2-year simulations. They have 20 members each. They have 4 start years per year, and the 1970 to 2018 period has been completed. The plots here show the La Nina prediction skill from the new simulations. Those are the SMILE ones shown on the left side, in comparison to what we got before with our decadal prediction large ensemble. These are November start dates, and 3 La Nina cases are considered: 1973, 1983, and 1998. The black lines are from the observations, and the solid or thick solid red line is representing the ensemble mean in each case, and the ensemble members are shown by thinner red lines. So you can see that there is actually some improvement in the La Nina prediction over a 2-year period in the new simulations. Another effort by the Earth System Prediction Working Group concerns the subseasonal to seasonal hindcasts and real-time forecasts. In one set, they are using the low-top version or the CAM6 version of the coupled system CESM2 with 11 ensemble members. They have done it for the 1999 to 2000 period. They start weekly, and these are really short, 45-day long simulations. They have also repeated the same simulations using the high-top version of the model, that's CESM2 Vacuum 6, but because it's expensive, they are running it only for the winter season, and only 5 ensemble members are used for each start date. These simulations are being contributed, or the output from these simulations are being contributed to the operational NOAA week 3 to 4 outlook. And the bottom panels here show the 2-meter air temperature skill in terms of anomaly correlation coefficient. The reddish colors are from CESM2 CAM6. The blue color is from CESM2 Vacuum 6 version, and they are being compared to our CESM1 older model version with CAM5. And they are using different ensemble members from 5 to 10. The left panel is for the winter or DJF global land, and the right one is for the North America land only. And you can see that our new set of simulations are producing anomaly correlation coefficient or skill comparable to what we get in CESM1. And I'm told that these skills are actually better than those of some operational centers. I would like to next highlight some of our simulations related to or looking into climate responses to COVID-19. And because of this pandemic, we are in this virtual situation. But we have actually performed this study in comparison to the 2019-2020 Australian bushfires. This effort is led by John Fasulo, and again, you'll hear his presentation and poster in some of the sessions in this workshop. The background image is here showing the Australian bushfire emissions. This is for January 6, 2020. So what we have done is essentially we have run, we have the usual 10-member ensemble SSP245 case, but in this case, we used a new 50-member ensemble using actual GFET fire emissions extended with SSP245 scenario. Then we ran 50 members of COVID emission scenario simulation. And then we supplemented that with addition of the Australian fires with another 50 members. So these are relatively order 5-year simulations. The top panel here shows the aerosol optical depth, and the bottom panel on the right shows the top of the atmosphere net shortwave radiation time series. The red line is our control. It's the ensemble mean of the 50 members, and its shading is shown by the light gray line here. The COVID case is shown by the blue line. It's just showing the ensemble mean for clarity purposes. And you can see that the Australian fire case with COVID is the green line here, where the spread is shown by the darker gray. And you can clearly see that both in aerosol optical depth and also TOA net shortwave radiation, we are seeing significant impacts of the Australian fires. And their impacts are much larger than what we see with the COVID emissions changes that arise from COVID. And you can probably see that these responses in aerosol optical depth and TOA net shortwave radiation to Australian fires are similar to major volcanic eruptions. Another experiments that I wanted to highlight is related to coupled land ice simulations. In a study, this manuscript, the collaborators actually looked at the change in surface mass balance in response to increased CO2 concentration. So they performed a 350-year simulation starting at pre-industrial control conditions. They increased the CO2 concentration by 1% per year up to quadrupling time of CO2. And then they kept the CO2 levels at that high level for another roughly 200 years, all the way to 350 years. So the plots on the right side show the surface mass balance distributions. The left panel is for the pre-industrial control. The middle panel shows what's happening at the quadrupling time. So it's the surface mass balance at quadrupling, around quadrupling, and its difference from the PI control. And then the last panel, or the rightmost panel, is the last 20-year mean minus the PI control surface mass balance. Red colors show net accumulation, and the blue colors show net ablation. So you can clearly see that with increased CO2, we are seeing increased areas of ablation. And the model simulations indicate that the sea level rise will, or sea level will increase by about 1 meter by year 350 in this quadrupling CO2 experiment. I would like to also advertise that we now have the capability in CESM2 and CESM to run multiple ice sheets at the same time. So that means we can now run Greenland and Antarctic ice sheets together, although I should mention that this is still in the testing mode. As Everett mentioned, NCAR's strategic plan is calling for actionable science. So we have quite a few members of the CESM community looking at actionable science. And in this slide, I'm showing examples for polar climate. On the left side, a collaboration is summarized. This is between scientists, indigenous people, and decision-making experts to produce and share actionable knowledge to inform decisions about the socio-ecological systems in the Arctic and beyond. There are also studies concerning Arctic shipping. They are looking at likelihood of potential ship paths and assessment of maritime risk. And on the lower right, it's a new project. It's Antarctic Marine Protected, concerning Antarctic Marine Protected Areas. This work is in collaboration with the Scientific Committee on Antarctic Research, the Southern Ocean Coalition, the Pew Charitable Trusts, and Sea Legacy, and they are focusing on identification of biological hotspots and forecasting locations of highest ecological value for protection. Another study that is relevant, or that's relevant for societal applications, focuses on improving simulation of surface ozone. And this study is conducted by Musica. Musica is a framework that is unifying the chemistry modeling within NCAR. And I should note that Musica has been released in the latest version of CESM 2.2 as well. In these simulations, the spectral element dynamical core for the atmospheric model is used with regional refinement. It is using 14-kilometer resolution over the continental United States, with the resolution gradually increasing to or getting closer to nominal 1 degree resolution as we go away from the continental US. They are looking at essentially impacts of both model resolution and increased chemical complexity. On the lower left panel, it is showing the impacts of increased resolution on ozone concentration. It is high res minus low res, and you can see the increase in ozone concentration, and particularly they are concentrated on urban areas. On the lower right side, we are seeing the increased role of increased chemical complexity. So this comparison is using the highest resolution in both simulations, 14 kilometers in both. One has higher level of increased chemical complexity. The other one has a simpler version of the chemistry. And you can see that with increased chemistry complexity, there is actually a reduction of ozone concentration. And this is actually a good thing because the simpler chemistry was producing actually a positive bias in ozone concentration. So this is actually representing an improvement. The bottom line is that both increased resolution and increased chemical complexity actually is improving simulation of surface ozone, and that's societally important. Changing gears, so more on the development side, as CESM, we are fully aware of our storage footprint, and there are challenges, of course, with the storage limitations. So in collaboration with CISL and also our colleagues at Colorado School of Mines, we are pursuing lossy compression of CESM data. Application of lossy compression applied to climate data sets can result in large amount of data reduction with minimal drawbacks if, that's the big if, it can be applied carefully. Our collaborators determined optimal compression settings for several test data sets using a metric called the Data Structural Similarity Index measure. And they have some tests available for users. And if you are interested in participating in this effort and helping us out, please contact our collaborators, Dorit, Allison, and Alex. They have developed a new Python package. It can assist users, this package can assist users in analyzing potential compression effects visually and through budgets and additional diagnostics. I wanted to also highlight streamlining coupled simplified modeling efforts with CESM. This is an NSF-funded proposal effort, and I wanted to show here a prototype CESM configuration query tool. It's a graphical user interface. It's intended to help users create new cases easier. So if one, for example, chooses to perform a control simulation for year 2000 conditions, let's say, this GUI interface will automatically give you available options for each component, including their physics and many other sort of underlying possible forcing scenarios that can be used. For example, it can be used to, for example, with year 2000 conditions to increase CO2 levels or keep them constant, that sort of thing. CESM, in collaboration with, again, university community, has been developing a library of variable resolution grids for various scientific applications. And these are all performed or done using the spectral element dynamical core. And as far as I know, we have now 7 applications, and they are listed here. So just to detail a few of them, Arctic Grid is using regional refinement over the Arctic region, and the resolution is 1/4 degree, and then gradually goes to 1 degree resolution as we get out. Its sibling Arctic Greenland Grid uses still 1/4 degree resolution within the Arctic domain, but its resolution is increased to 1/8 of a degree over Greenland. We have the Antarctica, North Atlantic, continental US, that's the one that was used with Musica. And then we have Himalayan Grid, and then the newest edition is the South America version. And I note that both the Himalaya and South American versions actually use 6-kilometer resolution as their finest grid. The upper right panel shows a simulation, a snapshot from a simulation using the Arctic Grid from here. The colors show the precipitation rate. And then hopefully you can see there are some streamlines here in white colors. They show the wind speed. Finally, I would like to touch on 2 sort of efforts towards our next workhorse version of CESM. The first one concerns where we are with respect to our vertical resolution evaluation efforts. This is led by Isla Simpson. And again, there will be more discussions about this during the Atmospheric Model Working Group meeting. The motivation here is to improve the representation of stratosphere and boundary layer in our standard model for climate applications, and expected improvements we are expecting improvements in the representations of QBO, stratospheric polar vortex, and boundary layer clouds, for just to list a few. I think we're pretty much settled on using 80-kilometer top with 91 vertical levels. 10 of these levels will be within the boundary layer. And then we are also creating half the height version of the model at 40-kilometer model top with 58 vertical levels. I should mention that all of these need to be still discussed in detail at the CESM SSC, so that hasn't been done yet with respect to the final decisions here. This new grid will have about 500-meter grid spacing in the free troposphere and lower stratosphere. And as I said, 10 levels within the boundary layer. And then currently it is being evaluated. The addition of 10 layers within the planetary boundary layer is being evaluated. Final topic that I wanted to touch on concerns the atmospheric dynamical core evaluation. Again, this is for the next version of the workhorse version of CESM. This effort is led by Peter Lauritsen and again, Isla Simpson. We are considering 3 dynamical cores. That's the FB3, MPAS, and SE dynamical cores. And the focus here is for nominal 1-degree CESM that will be used for mostly climate applications. Although we'll end up choosing 1 dynamical core for this particular application, all dynamical cores will remain within CESM and will be available for use for any other application. So no dynamical core is being eliminated. And it is a lengthy process, and it's, I think, an important process. That's why I'm fine with, I think we should take our time. It involves multiple phases. In phase 1, we've looked at inherent properties of the dynamical cores. This includes computational performance, tracer transport characteristics, energy and momentum conservation. This is nearly completed. The second phase, which is about to start, will be considering general performance under comprehensive AMIP simulations. And the remaining other phases, which is to be defined in detail, will include performance in coupled simulations, including studies with chemistry and climate, paleoclimate applications, and perhaps additional ones. For this purpose, we have a set of stakeholders. We have already a dynamical core task team. They are performing the simulations and analysis. We are about to form a dynamical core assessment panel. These teams will be interacting with each other, and eventually the dynamical core assessment team will provide a recommendation to the CESM SSC, which has the ultimate decision-making power. So with that, I will conclude. If you have any questions, you can put them in the Q&A box, and I'll try to, we have only 1 minute left. Or you can save your questions, as I indicated before. Many of the topics that I touched upon here will be discussed in more details tomorrow, starting tomorrow, even this afternoon, in the working group sessions and cross-working group sessions. Actually, they'll start tomorrow and tomorrow morning. Thank you. So I'll stop sharing and see whether. Okay, I don't see any questions. Okay, so I think we are right on time. So I would like to now continue sharing my screen. Okay. Next up is the CESM Distinguished Achievement Award. So I am quite happy to announce that this year's recipient is Jerry Meal. He is from NCAR, and I'll virtually give him the plaque that we already prepared for him. So I just wanted to quickly mention that he is, from his nomination material, he is one of the leading experts on climate variability and change. He has significantly advanced and promoted CESM's wide application to societally relevant climate and climate change science problems. He has focused his CESM-related work on understanding the coupled climate system and how changes in each component of the Earth system can interact and lead to rapid and unexpected impacts. He has led seminal papers on monsoons, decadal variability and extremes, as well as the impact of solar variability, volcanoes, and anthropogenic forcing on the coupled climate system using both the low and high top versions of the CESM. He just recently, I think last year, stepped down as the co-chair of the Climate Variability and Change Working Group. He was one of the longest serving co-chairs. Before this working group, he was the chair of the co-chair of the Climate Variability Working Group. And he has shown extraordinary service both nationally and internationally in driving coordination and innovation in coupled model experimentation. His nomination material is like 2-3 pages, so I don't want to read the whole thing. And in the interest of time, I will pass the presentation to Jerry. And congratulations, Jerry.
All right. Share the screen here. All right, thank you very much, GoCan. This is really a tremendous honor, and of course, I really appreciate it. But I do have to acknowledge a number of other people who make this kind of award possible, because my work involves analysis of model simulations and observational data sets. I want to acknowledge the CSM model developers, not only at NCAR, but at the universities and across the CSM working groups and the software engineers who combine with the model developers to provide really credible and fantastic modeling tools to allow some really interesting research to occur. The people who develop observational data sets are really important as well, because you want to analyze observations to try to figure out what's going on in the real system and use the modeling tools to give you insights into what the observations may or may not be telling you. This goes on in places like climate analysis section at NCAR and a number of universities and government labs. So that's really an important part of this. Collaborators are really important. So I've really been lucky to have strong collaborators over the years. This is important because not only it makes the science a lot more fun, but it also really contributes to much stronger research efforts. And finally, of course, funding support. Couldn't do this without funding support from NSF NCAR and the RGMA group, RGMA program at the Department of Energy. So after having said that, want to give this talk, move this out of the way here. And over the years, I've had graduate students ask me a number of times, how do you decide what to do next? You're doing some research, you get to the end of a paper or research project, and how do you decide what you do next? And I always tell them that it's really a research path, and that one thing leads to another inevitably. And so when you're looking at one part of a problem, and even if you get to the end of it, you feel like you never really get to the end of it, because other things come up. There's questions that are raised as part of the research. You may realize that you've missed something. There's gaps that you've missed on your research path. And so, I just say, well, one thing leads to another. And so I wanted to give an example of one of those research paths with a research path that I've been on for a while, involving decadal variability, predictability, and predictions. So in terms of initialized prediction, and this is kind of the motivation to look at decadal climate variability, you want to try to look at this interesting space here, the seasonal to decadal timescales here. So this is in this kind of spectrum of timescales, going from subseasonal to seasonal, seasonal to interannual, and then the kind of projections that go on into the century timescales. But earlier, kind of in the shorter time scales, you get some skill from the initial state. And that's where you try to initialize these processes and mechanisms from the initial state to give you some skill. And then as you get further along, after a decade or so, then you get skill from the external forcing, in particular the increasing greenhouse gases. But there's this kind of twilight zone in the middle here, the seasonal to decadal time scale, where you can get some skill from the initial state, hopefully. And then you start to get some skill from the external forcing, particularly from the increasing greenhouse gases. So what you want to do is try to maximize the amount of information you can get out of the initial state and these processes and mechanisms that can give you some skill on into these timescales that'll carry you through then until the external forcing kind of takes over. So To illustrate where the skill comes from, this is a really nice figure that Grant Brandstetter and Haiyan Tang put together a few years ago. And this is using a skill measure called relative entropy, but you just have to know that the higher you are here on the y-axis, the greater the skill. And this is looking for one particular area in the North Atlantic, upper 300-meter ocean heat content, but you can produce these kinds of plots for a lot of different quantities in a lot of different areas of the globe. And you get kind of the same kind of results. They use 12 CMIP5 models, but if you just focus on the dark blue line and the dark red line, which is the ensemble, multi-model ensemble average, the skill related to the initial state starts out really high and then of course drops off. So by the time you get out to maybe 5 or 6 or 7 years, you're getting a relatively lower skill, but then the skill from the external forcing kicks in. And after about 8 or 9 years, then that's where you get most of the skill on this seasonal to decadal time scale. So what you want to do is try to get as much skill as you can out of this initial state to carry you as far as you can until you actually intersect with the skill that is coming from the external forcing. So the whole kind of premise of decadal climate variability and related to initialized predictions is you hope that there are some relevant decadal timescale processes and mechanisms that come from coupled processes, probably involving the oceans, because these are slowly evolving kinds of things. And the two typical things that you look at are Atlantic multidecadal variability, the AMV, sometimes referred to the Atlantic multidecadal oscillation, or AMO, and Pacific decadal variability, PDV, and a lot of times, at least people like me call it the IPO, interdecadal Pacific oscillation. These are all kind of terms that are used interchangeably, but basically you're looking at the two big ocean basins, the Atlantic and the Pacific. You're trying to look at a couple of processes that have slowly evolved that can give you some skill that if you initialize them properly and get them kind of going in the right direction, that can give you some skill beyond maybe the first year or two, maybe on out to 3 to 5 or even 6 or 7 years. But the big issue for studying and understanding and predicting this decadal climate variability is the observational record is short. If you're looking at AMV fluctuations, you may have just a couple of fluctuations over the time period of the instrumental record. Same thing for Pacific decadal variability. And you have external forcing in the observations that can act on decadal timescales to complicate the whole picture. So what you do is you have to use a hierarchy of climate models. And some of the ones that we've been using are, of course, fully coupled unforced long control runs, where the model itself is generating its own internal variability without any external forcing interfering. Historical simulations, where you have time evolving external forcing that comes in that's superimposed on the internal variability of the model. And you can use those two in concert to try to figure out how the models are depicting this kind of low frequency variability. More recently, we've been using these pacemaker model configurations. The pacemaker kind of methodology means you specify observed sea surface temperatures in one region while the rest of the model is fully coupled. So you get kind of a forcing response where the model responds to the forcing from observed SSTs in one region. And then finally, using the atmospheric model alone with climatological SSTs, where you specify convective heating anomalies to test teleconnections from the tropics through anomalous Rossby wave responses from the tropics to the mid-latitudes. So those are some of the versions of climate models we've been using. And of course, the first question is, because we're looking at these two candidate basins, the Atlantic and the Pacific, you want to know how the AMV and PDV are related. And maybe if one basin was driving the other, then if you could just predict things that were going on in that basin on decadal timescales, and that would drive the other basin. And because you'd have SSTs pretty well predicted in both basins through teleconnections, you could get a lot of skill in the global initialized prediction problem on the S2D timescales. So let's see if they are related or how they're related. So we use these idealized pacemaker simulations where we specified the observed pattern of internally generated, or what we think is internally generated variability for first the Pacific, and this of course is kind of depicts the positive phase of the IPO, where you get these above normal sea surface temperatures in the tropical Pacific, and you specify these sea surface temperatures, this pattern between these two green lines here in the Pacific, and then you run the model to see how the rest of it responds. And you look over here in the Atlantic, and you see in the tropical Atlantic, both north and south of the equator, you're getting a same sign SST response between the Pacific and the tropical Atlantic. And this is coming about through a number of different processes. But then when you look at When the Atlantic, you have this Atlantic multi-decadal variability pattern here between the green lines. If you specify that pattern, then you see that the Pacific has the opposite sign in the tropical Pacific. So you get this opposite sign response if the Atlantic's forcing the Pacific, and you get the same sign response if the Pacific is forcing the Atlantic. So that means they're not both working in the same way as they're interacting, which is kind of interesting. So, okay, so now that result comes from this kind of strange configuration, these pacemaker configurations. Now let's look at another kind of level of model simulations, the 1800-year CSM pre-industrial control run. And let's do some lagged regressions. And if you look at the lagged regressions where the PDV is leading by 3 years, you see that when the PDV or the IPO is in its positive phase, you get the same sign SST response in the tropical Atlantic, both north and south of the equator. If the AMV is leading by 3 years, you get this kind of opposite sign response between the Atlantic and the Pacific. So this is kind of reassuring because the fully coupled model, when it's running freely and internally generating its own decadal timescale variability, you're getting something that looked like what we were getting in the pacemaker simulations. So now we can go to the observations, now that we have some clues as to what to look for from these different, the model hierarchy, these two different types of model simulations. We can actually try to analyze the observations with all its problems and its short record and everything else. But if you do this lagged regressions for when the PDV is leading by 3 years, you do see that there is a hint of the tropical Atlantic having a same sign response to the tropical Pacific. And if the AMV is leading by 3 years, you see this opposite sign response between the tropical Atlantic and tropical Pacific. So it looks like there are at least traces of this kind of these connections between the two big ocean basins on decadal timescales that we saw in these different types of model simulations. And then that leads us to formulate a new paradigm for understanding decadal timescale variability, and that the Atlantic and Pacific are mutually and sequentially interactive, such that when the Atlantic is driving the Pacific, you get this strong Walker circulation, strong trade winds, you get heat divergence out of the surface layer in the Pacific, you get cooler than average sea surface temperatures and decadal timescales in the tropical Pacific, and you get this opposite sign response between the tropical Atlantic and tropical Pacific. But if the Pacific is leading the Atlantic, you also get this anomalous Walker circulation where you get this strong descent. But you also get these teleconnections coming out of these big convective heating anomalies associated with these warmer than or above average Pacific sea surface temperatures for this depiction of the positive phase of the IPO. You get this PNA pattern in the North Pacific, PSA pattern in the South Pacific, anomalous lows in the North and South Atlantic that weakens the trades, that weakens latent heat flux, and that contributes to, along with some ocean heat convergence properties, to warmer than normal SSTs. That's the same sign response to the tropical Pacific. So this indicates that we have to actually be able to simulate processes and mechanisms in both the Atlantic and the Pacific, such that they're mutually interactive, and one isn't driving the other all the time. They're kind of sequentially driving each other. And that gives you some insight into what the challenge is for initialized S2D predictions. But first of all, okay, let's now just focus on the IPO in the Pacific. So we know that the Atlantic and Pacific are important, they're mutually interactive, but let's focus on the IPO in the Pacific. And the question is, if we can actually predict the IPO, then what additional effects could we get, not only on its interactions with the Atlantic, these kind of mutual interactions, but what effects could be predicted elsewhere? And global average temperatures is one that's kind of fairly well known. And this is documented here, where we see that looking at different observational data sets in the CMIT-5 multi-model ensemble, when the IPO is in its negative phase from the 50s to the 70s, the warming trends, global warming trends were pretty flat. When the IPO is positive from the 70s to the late 90s, you see a much more rapid warming of the global temperatures. And when the IPO went back into its negative phase in the early 2000s, you see that the trend, the global warming trend, reduced again. This has been generically referred to as the hiatus, probably more accurately referred to as the early 2000s slowdown. And you can see the CMIT-5 models just kind of continue warming. They don't seem to capture this slowdown, even though the spread, this kind of gray shading is the spread of the model simulations, indicate that maybe some of the model simulations may capture this, this slowdown. So the question then is, do any of the CMIT-5 model simulations capture this early 2000s slowdown? So we looked at the CMIT-5 multi-model data set, 262 realizations of 20th and early 21st century climate. And it turned out 10 members had a reduced trend of global warming over this time period from 2000 to 2013 that resembled the actual observed trend in the observations. And here are these 10 members. You can see these red lines are all relatively flat compared to this kind of cloud of the other the 262 realizations. And the question is, well, what was going on in these 10 members that was contributing to this slowdown? And if you look at the composite across these 10 ensemble members, they're all showing this negative phase of the IPO. So that seems to suggest a couple of things. One is that that these 10 members just happened to sync up with the internally generated variability that was going on in the observed system. And that's a fairly rare event to actually get an exact match of something that's randomly occurring in the observations and randomly occurring in the model simulations. But it also indicates that this negative phase of the IPO is probably an important part of this kind of response. So the question is, what's then producing that? And so now we can look at, in this study, we looked at an older model, the CCSM4. We were looking at 21st century simulations. We were looking at decades that had an almost flat warming trend and decades that had a really a more rapid warming trend. And the decades with near zero global warming trend, these hiatus or slowdown decades, show this negative phase of the IPO. And decades with rapid warming trend showed a positive phase of the IPO. So then you ask the question, well, why is that happening? And we can analyze these model simulations, which is a much easier task because you have more complete ocean data in these model simulations than you have in the observations. And it turns out that during the negative phase of the IPO, and when you have this slowdown in temperature trend, that's because globally averaged over the ocean surface, the surface layer is cooler than normal. And that's because more heat is being put into the deeper ocean. And there are three processes that do this, and they can act either singly or in combination in these model simulations. Stronger subtropical cells in the Pacific that sink more heat down into the subtropics. Stronger Atlantic meridional returning circulation, or AMOC, that sinks more heat down into the North Atlantic. Or a weaker Atlantic bottom water formation, which means you have less cold water going really deep, which is a net heat gain for the subsurface ocean. So that was an interesting kind of chain of research that led to understanding that kind of internal variability and in relation to external forcing. But there was also some interesting connections that kind of came up with the IPO connected to Antarctic sea ice. And this kind of started out by looking at the fact that the CMIP5 multi-model ensemble average, which is this dashed line, showed decreasing Antarctic sea ice extent from the late 70s up to, say, around 2014. While the observations were showing somewhat of an increase of Antarctic sea ice extent up to 2000. And then that upward trend increased by almost a factor of 5. And you got this more rapid increase of Antarctic sea ice after around 2000. And that was kind of suspicious because that was right around when the IPO transitioned from positive to negative. So in other words, it was in its positive phase in this kind of depiction here, where you have above normal SSTs in the tropical Pacific, and then transition to negative, where most of the SSTs in the tropical Pacific on decadal timescales were a bit below normal. So how could that be happening? Well, we can now use another tool in the modeling hierarchy. We can use the CAM, which is run with climatological SSTs, and you force the CAM with convective heating anomalies. In this case, negative convective heating anomalies from this negative phase of the IPO when you have below normal precipitation in the tropical Pacific, negative convective heating anomalies. And you can actually see that if you look at this, in this case, this is the June, July, August observational pattern looking down in Antarctica here. This is a polar projection. So it's Antarctica here in the center. South America is over here on the left. Australia would be over here on the right. And you see this pattern of anomalous lows and highs going around Antarctica. And you can see that there's a direct connection between these blue shaded areas, which are areas where the Antarctic sea ice is increasing, and southerly winds. Other winds, anomalous winds blowing from the south to the north, pushing the ice out, expanding it out, and contributing to this expansion of the Antarctic sea ice. And we can connect this to the IPO-related convective heating anomalies, using this, the CAM, the specified convective heat anomalies, to show you get a very similar teleconnection pattern around Antarctica. Get this big strengthened Amundsen Sea low over here, high south of Australia and high in the South Atlantic. And again, you get a preponderance of southerly winds that would act to blow the sea ice out and expand it out, which is what you saw in the observations. That gives you some insight into what could be happening and how the IPO could be connected to this Antarctic sea ice. So, okay, we published this paper in 2016, right? So sure enough, right in 2016, suddenly the Antarctic sea ice extent plummeted. So you're going along here, this was this kind of slow increase here from the late 70s to 2000. Now you get this more rapid warming expansion trend here in the 2000s. And all of a sudden you hit 2016, it just dropped off the table. And it's kind of stayed there ever since, more or less. It's been more or less below these levels in the 2000s. And this is right when the IPO transitioned to positive. So if you look at the negative IPO SST anomaly pattern from 2013, you see this, of course, below normal SSTs in the tropical Pacific in the observations. Positive IPO from 2015 to 2019, you see in the observations is kind of positive or above normal SSTs in the tropical Pacific. So maybe there was something in this transition from negative to positive IPO that contributed to this decrease in Antarctic sea ice. Excuse me. So we go back to the CAM convective heating anomaly experiments. Now we put a positive convective heating anomaly in the area of the Western tropical Pacific that had warmed up with the positive phase of the IPO. We look and compare to see what was going on in the teleconnection pattern in the observations. And now you see that this pattern of anomalous highs and lows are producing a preponderance of anomalous winds that are blowing from the north to the south. And when you see these winds blowing from the north to the south, that's where you see these orange and red areas, which are the areas where the sea ice is shrinking or retreating. So you're not only getting the winds pushing the ice back towards Antarctica, but you're getting warmer air advecting across the ice to help melt it at the ice edge. And you can see a very similar pattern in this convective heat anomaly experiment. This anomalous low over here, anomalous high in the South Pacific, low south of Australia, which suggests that there was a connection from the IPO convective heat anomalies to this decrease now in Antarctic sea ice. But there was something else going on that was pretty interesting. That was having to do with the ocean temperature structure. So now we're looking at observations from Argo floats. Zonal mean ocean temperatures average from 50 to 65 south over the upper 600 meters of the ocean. And you can see coming along here from 2004, it's kind of below normal, but all of a sudden you start seeing these kind of episodic pulses of warmer water kind of moving up higher in the column. And of course, the temperature structure in the Southern Ocean means that the warmer water is actually in the subsurface. The cooler water is above it in the surface layers. So something was pulling this warmer water up. And what was happening was that the negative phase of the IPO on average was producing stronger westerlies over the Southern Ocean. This was actually producing Ekman suction, which is pulling up this warmer water. And when you finally then got the transition to the positive IPO, you suddenly had anomalous kind of easterly anomalies. You were getting Ekman pumping now coming and bringing warmer water in from the north. And suddenly the whole column now, which had kind of been set up to have this transition, the whole column is now warm and it's kind of remained warm. And that's also contributing to the retreat of the sea ice. So anyway, that was another way that we connected the IPO to something else that we're interested in, like Antarctic sea ice. But the question is, okay, can we predict any of these things? Actually, this was, excuse me, I gave a talk at Lamont in the kind of around the 2014 timeframe and showed these results. And I was looking at the model is initialized. This is CCSM4 initialized in 2013. And it looked like the model was showing a transition to a positive phase of the IPO. This is now the prediction for the model initialized in 2013 for the 2015 to 2019 5-year average. It's quite different than persistence, which was persisting the negative phase of the IPO, and different from the kind of warming that was going on everywhere else. There was also a more rapid, 3 times as strong a warming trend with the predicted positive IPO than the kind of initial state or the previous state. And Mark Kane said we should publish that if you have an idea of what physically could be producing it. And I said, well, we think that we can see that seems to be this buildup of off-equatorial Western ocean heat content that seems to be triggered by an El Nino event, kind of like a westerly wind burst event with a MJO event can trigger an interannual transition of El Nino. And he goes, we better publish it. So we published this, and this came out. This work was done in 2014 and into 2015. So it actually appeared in 2016, but the prediction was for a time period verifying in the future from 2015 to 2019. And so we had to wait around for a few years to see how this verified. And as it turned out, here's the verification data from observations. And this is now with another model. This is with CSM1 from the DPLE. These are the predictions from the DPLE and computing anomalies in several different ways. But basically, you can see this positive phase of the IPO predicted similar to the observations and quite different from persistence. Excuse me. So This seemed to indicate that maybe there was something to this, and maybe this mechanism could actually be something we could predict. But how does it work? So let's go back and now look at the 1800-year pre-industrial control run from CESM1. And now we can composite these IPO transitions and get a lot more samples, right? So we get 1800 years, we got roughly 50 cases of a negative to positive IPO transition, about 50 positive to negative. And if you look at the composites, and this is the IPO index, the blue line is the IPO index, and of course it's transitioning from, in this case, negative to positive. These are the off-equatorial ocean heat content values for the off-equatorial Western Pacific in the model, showing that you get above normal off-equatorial heat content that seems to get to some kind of threshold. And then something happens here and it transitions and it starts to drop off or starts to discharge when the IPO goes into positive phase. Opposite thing happens when it goes from positive to negative. And what's happening is around this time of transition, you have a much greater chance of an El Nino event happening compared to an La Nina event. So this suggests that for a lot of these transitions, you're getting more El Nino events than La Nina events, and that the El Nino events are actually contributing to this transition. And vice versa, you get a better chance of La Nina events for the positive to negative transition compared to the number of El Nino events. Well, how can this be working? Well, we then can analyze the model to actually figure out what the mechanism is. And this is fairly complicated. I can't spend a lot of time on it. But basically, if you're just looking at 3 years before transition, you see the negative phase of the IPO. 3 years after the transition, you get this positive phase. And what's happening is that you get convective heating anomalies associated with the negative SSTs that are producing an anomalous gill response that's producing wind anomalies that are forcing, in this case, we're looking at wind stress curl. You're seeing ocean heat converging into the off-equatorial Western Pacific that persists and that builds up over time. And then you get an El Nino event that comes along, you get westerly wind anomalies along the equatorial Pacific, and you get opposite sign gill response from the positive convective heating anomalies here. And now you get a divergence of heat out of the off-equatorial region and a convergence of heat into the equatorial region that deepens the thermocline. You get Kelvin waves coming across that deepen the thermocline, and you get that transition. You also get some interesting kind of contributions from trade winds, anomalous trade winds further to the east that looks like meridional modes that can contribute to this. So that was another way to use the model to try to figure out a mechanism for something that we think is important for initialized predictions.
Jerry, you have a few minutes left.
Okay, this is the last slide here. So the remaining challenges. So model error is a huge challenge for initialized prediction. And this is illustrated here in this picture from the CESM1 decadal prediction large ensemble. You can see the observations for global average temperature, the black line here, and the model drift are these successive dots going from blue to red. You can see the drifts are very rapid and fairly large, and the model tends to drift to its preferred systematic error state represented by the uninitialized or free running version of the model from the CESM1 large ensemble. And okay, so you get these big drifts, but the trends in the initial states and the drifts are not the same. So you can see the initial state trend is this kind of a slope, the drifted state trend has this kind of a slope. They're different. So if you're trying to bias adjust, you're going to have some problems because the drifts aren't going to be the same magnitude, and there's some other problems. So I say that's one of the big challenges that remains to initialize prediction for seasonal to decadal timescales is model errors that produce bias and drift. So this research path, just to review kind of how this research path seemed to work, and if you were following along and watching the years of the publications, you could tell that this was not necessarily a linear process because you publish something and then you realize you missed out something, you need to fill in something, so it's not a linear process, but the path kind of starts out with this short observational record. So you need to use a hierarchy of model simulations, but what is it we're trying to understand? The observations show that the decadal variability seems to rise in the Pacific and the Atlantic, the PDV and the AMV, but how do they work and how are they connected? We use pacemaker simulations to propose this new paradigm that they seem to be mutually interactive. Both are important. But okay, let's start by focusing on the PDV represented by the IPO. The IPO seems to affect global surface temperature trends and Antarctic sea ice. How does that work? We use the CCSM4 model simulations to show that this negative IPO and the slowdown in global temperature trends are internally generated and produce a cooler ocean surface layer, and more heat then is put into the deeper ocean through these stronger subtropical cells, stronger AMOC and weaker Antarctic bottom water formation. So we know what the processes are that are producing these speed ups and slowdowns and the negative and positive phases of the IPO. But then that seems to affect other things like the Antarctic. So how does that work? We used CAM specified heat anomaly experiments to show how these teleconnections that are driven from the IPO-related tropical SST anomalies can produce anomalous surface winds around Antarctica that are either predominantly southerly, which gives in the negative IPO, is pushing the sea ice out or expanding the Arctic sea ice, or northerly, winds coming from the north, flowing to the south, that's associated with positive IPO, that shrinks, contributes to shrinking the Arctic sea ice. But okay, we still want to be able to try to predict this, right? Because it seems to be fairly important to try to predict these kinds of things. So we used initialized hindcasts. And the first studies were done with CCSM4 and then the CESM1 decadal prediction large ensemble. We have some evidence that maybe some skill in predicting some of these transitions. And most recently, we were showing this negative to positive IPO transition that occurred around 2015, 2016. There is evidence that we could predict that, but how does this work? How do you get skill from this kind of prediction? So we go back to the PI control run with CSM1, and we also use these specified convective heat anomaly experiments with CAM. We show that this buildup of off-equatorial Western Pacific Ocean heat content during negative IPO can be triggered by ENSO activity to transition to a positive IPO. But we still have some issues, right? There's a lot of issues, actually. One of the big ones is model error that really affects how you interpret and formulate these initialized predictions. And I think that's probably one of the big challenges we have remaining in this research path. So thank you very much.
Thank you very much, Jerry, and congratulations again.
Thank you.
Any questions for Jerry? You can type it in Q&A. We have a few minutes. In the meantime, Jerry, I was going to ask what your thoughts are with respect to the role of increased model resolution. Do you think what are your thoughts, I guess? Will it improve the prediction skill or will it degrade it?
Well, there's evidence that increased resolution reduces model error, and that's the big obstacle we've got, right? We want to reduce model error any way we can. So if increased resolution, and there's a lot of evidence that increased resolution does reduce model error, so that's going in the right direction. But of course, then the counter to that is then you have to spend a lot more computer time running initialized hindcasts with the higher resolution. But I think that's one of the things that is going to be important for increasing decadal prediction skill, but also improve parameterizations and hopefully understanding more of these processes that we can maybe try to capture them better in these in the initialized hindcasts.
Okay, thank you. You may be familiar with this. Alan Robach is talking Mike Mans, and I responded, but Alan says, but Mike Mann says the AMO does not exist and is rather forced by volcanism. Also, can the model predict ENSO?
Yeah, well, I mentioned at the very beginning that when you're looking at the observational record, it's not only short for decadal timescale processes, but you got this complications of the external forcing. And I think there is evidence that some of the variability that is occurring on decadal timescales, particularly in the Atlantic, could be forced not only from volcanic eruptions, but also from anthropogenic aerosols that are time evolving and evolve differently in different regions. And so I think that's one of the big challenges, is trying to figure out how much of this decadal variability is internally generated and how much of it is externally forced. There is evidence that a lot of it is internally generated because we can look at these long unforced model control runs where there is no change in external forcing, and you see the model itself is internally generating patterns of variability and timescales of variability on decadal timescales that resemble what is happening in the very short observational record. So I think it's all going on, and that's what makes it very complicated when you're trying to interpret the observations, is you have both of those things going on. In terms of ENSO prediction, I think there is some evidence that we do on the seasonal to interannual timescale, we do have evidence that we can skillfully predict at least some parts of ENSO. The question is if you can get beyond maybe a year or two. It looks like maybe there is at least some skill in maybe getting some aspects of ENSO variability beyond a year or two, and that could actually be associated with the base state provided by this kind of slow background changes in decadal variability. So I think all these things make this problem really interesting scientifically, and it's pretty exciting to work on because there's really a lot more to learn, and it's still a fairly new field. The first paper published on initialized decadal predictions was just published in 2007. So this is still a fairly new field, and that's what makes it great, because we're still trying to figure out what's going on.
Okay, so I think in the interest of time, we should move on. But Jerry, there are two additional questions. One with from Peter Jant, and the other one is Sanjay Kumar. You can just respond them.
Okay, thanks a lot, Gökhan, and thanks again for the award.
You.
Really
Could you stop sharing your screen, please?
Yes.
Excellent. So now moving on to, you can see my screen hopefully. So now moving on to a graduate student award. And I am extremely pleased to announce the winner of the CSM Graduate Student Award. It is Patricia Dorepentini. Hopefully I'm pronouncing the last name correct. I practiced a little bit. And she's from University of Colorado, Boulder. And she's just graduating or just graduated. So Patricia has made important contributions to the CESM project through her discoveries relevant to discontinuities in the prescribed historical biomass burning emissions and their impact on Arctic climate. And this work grew out of her analysis of the standard CSM2 simulations, in which she found oddities in sea ice in the latter part of the historical period. She also led one of the CSM2 special issue papers in which she analyzed and compared the performance of the Arctic sea ice in two versions of the CESM. I'm assuming that she'll be talking about one of these topics. So again, congratulations, Patricia. It's the floor is yours. The virtual floor is yours. I'll stop sharing. Please go ahead. You are muted. Okay.
Okay. Thank you, Gökhan. I'll share my screen now. Okay, hopefully this is working. I'm just going to change to a laser pointer. Great. Yeah, so thanks a lot, Gökhan. I feel very honored and grateful to have been chosen for this award. I would like to thank the committee and as well as those who nominated me and acknowledge the other graduate students that have been nominated for the amazing work that they do. So my name is Patricia Dorepentini, and as Gökhan mentioned, I'm a PhD student at the University of Colorado Boulder, and I will be starting as an ASP postdoc in CGD this fall. And in this presentation, I will be talking about the impact of CMIP6 biomass burning emissions on Arctic sea ice loss. This work has been done in collaboration with several people from the University of Colorado Boulder, NCAR, and NSIDC, as listed here, and is currently under review at Nature Climate Change. Okay, so I want to start this presentation by showing you the time series of observed Arctic sea ice area at the sea ice minimum in September from 1979 to 2020 from NSIDC, with the blue line showing the linear trend over the whole observational record. In addition, I've also added the trend from 1996 to 2007 in pink and from 2007 to 2020 in cyan. And you can see that over the period shown by the pink line, the trend in sea ice decline was larger than the overall trend. And then since 2007, the trend has been smaller than the overall trend, indicative of a reduced rate of observed Arctic sea ice decline in recent years. And so this acceleration in the rate of Arctic sea ice decline at the beginning of the 21st century and the recent reduction that followed have already been reported in the scientific literature. And these papers have shown that internal variability can explain these periods of high and low trends in Arctic sea ice decline. For example, through interdecadal variability of Arctic atmospheric circulation related to teleconnections from the tropical Pacific. Interestingly, when analyzing the latest version of the CSM model, the CSM2 that was submitted to the CMIP6 archive, we found a similar acceleration in the sea ice loss, followed by a recovery, as is shown in this figure that shows the time series of September Arctic sea ice area anomaly. Note that this feature of the sea ice evolution in the CSM2 is present in all months of the year, although it is most pronounced at the sea ice minimum in September, which is what we're showing here. By comparison, the CSM1 large ensemble, the previous version of the CSM, which is forced with CMIP5 forcing, shows increasingly larger negative sea ice area anomalies with time until the Arctic reaches ice-free conditions, consistent with what we would expect. Another way to look at this is to plot the 20-year linear trend in September sea ice area, shown in the figure on the right here, with the end year of the 20-year period indicated on the x-axis. And so in this figure, you can clearly see that the negative trend in sea ice area in the CSM2 increases rapidly starting in the mid-1990s and reaches a maximum value around end year 2010, after which the trend decreases and reaches 0 or even slightly positive values for a few years before it starts increasing again. In contrast, the CSM1 large ensemble shows the trend is slowly increasing with time until about end year 2030, and then it starts to decrease as the Arctic transitions to a seasonal ice cover. We found that one important difference between CMIP5 and CMIP6 that explains this odd behavior in the CSM2 has to do with biomass burning emissions, which we'll abbreviate to BB emissions in the text. So biomass burning emissions are emissions of gases and particulate from the burning of live or dead vegetation, including human-initiated burning and natural lightning-induced burning. And estimates of biomass burning emissions that are used as prescribed forcing in climate models come from a variety of sources. However, starting in 1997, these estimates are based on the Global Fire Emissions Database, or GFED, which combines newly available satellite information on fire activity and vegetation productivity to provide a more realistic picture of biomass burning emissions. In CMIP6, the biomass burning emissions were updated to include internal variability instead of using decadal means, which is what was done in CMIP5. And as can be seen in this time series of black carbon emissions over the Northern Hemisphere mid-latitude on the left and globally on the right, this results in an unrealistic increase in the internal variability of biomass burning emissions over the GFED period, which is indicated by the two vertical lines on this plot, compared to pre and post GFED years. So to investigate the impact of this increased internal variability in biomass burning emissions over the GFED period, we conducted sensitivity experiments, which we'll refer to as CSM2BB, in which we averaged the biomass burning emissions over the GFED period from 40 to 70 north and used a fixed annual cycle to remove the internal variability while conserving the total integrated amount of biomass burning emissions. So this is represented by the green line here on the left, with the emissions pre and post GFED being the same as in CMIP6. We do this only over 40 to 70 north to really isolate the impact of Northern Hemisphere mid-latitude wildfires on Arctic sea ice. And as a result, our sensitivity experiment has prescribed biomass burning emissions that are more similar to CMIP5 over the GFED period. And in the figure on the right, you can see that the global emissions are almost unchanged in the CSM2BB, as Northern Hemisphere mid-latitude emissions make up only about 14% of the global biomass burning emissions. So moving on to the results, this figure shows the evolution of the Arctic temperature anomaly. We found that by removing the variability in biomass burning emissions over the GFED period, the large Arctic warming that was simulated by the CSM2 here shown in black is much reduced in the CSM2BB shown in the green line and falls more in line with the CMIP5 forced CSM1 large ensemble, which is shown in orange. Spatially, you can see how the warming in the Arctic, represented here by the trend in the surface air temperature over the GFED period, is reduced in the CSM2BB on the right compared to the CSM2, especially over the central and western part of the Arctic. And as a result of this reduced Arctic warming, the sea ice decline is also less pronounced in the CSM2BB compared to the CSM2, again falling more in line with the CMIP5 forced CSM1 large ensemble. And spatially, this can be seen by less negative trends in September sea ice concentration, again, mainly over the central and western part of the Arctic Ocean. So in another paper that was led by John Fasulo, we showed that the processes that lead to this Arctic temperature and sea ice response are related to changes in the clouds. And so by taking the difference between our sensitivity experiment and the regular CSM2 runs, we show that the CSM2BB simulates larger amount of vertically integrated cloud droplet number, especially over land, over Siberia and North America, where the wildfires are occurring. These clouds then block more of the incoming solar radiation, such that the net surface shortwave flux is reduced, which explains why we see a cooling at the surface in the CSM2BB compared to the CSM2. We also find indications of a similar sea ice response to increase interannual variability in biomass burning emissions in other CMIP6 models. And so similar to the CSM2, which is shown at the bottom here, the CMIP6 models that are highlighted in purple show a rapid increase in their negative sea ice area trend over the gray shaded region, which represents about the first third of the GFED period, followed by a decreasing trend for a few years. However, there are several other CMIP6 models that do not show much of a response, as shown by the models colored in teal, which indicates that there's a large contribution from model uncertainty on the response to the specific forcing across CMIP6. But one improvement in CMIP6 compared to previous CMIP version that was reported by the CISMIP community last year was an increase in the CI sensitivity to cumulative CO2 emissions and global warming, shown on the left and on the right here. So CI sensitivity is the ratio of the change in sea ice area over the change in CO2 emissions or global warming. So it basically represents the sea ice response to a change in CO2 emission or temperature. And as you can see in these two figures, the CMIP6 models, which are shown in green by the green lines, have higher sea ice sensitivity, meaning more negative in this case, compared to CMIP5 in orange and CMIP3 in blue, such that the multi-model ensemble mean, which is shown by the X here, is larger in CMIP6 compared to the previous CMIP version, and is also closer to the observed sensitivity, which is shown by the black dashed line. The CSM model also shows this increase in CI sensitivity from the CMIP5 version, here in orange, to the CMIP6 version, shown in black, which is consistent with what was shown for CMIP6 models as a whole. However, we find that the CI sensitivity of the CSM2BB, our sensitivity experiment, falls about halfway between the CI sensitivity of the CSM1 large ensemble and the CSM2, which suggests that about half of the increase in CI sensitivity from CMIP5 to CMIP6 can be explained solely by the increased interannual variability in biomass burning emissions, at least in the CSM model, but potentially also in other CMIP6 models. So finally, I want to come back to the observation and ask what our results mean for understanding the evolution of the observed Arctic sea ice loss. So as I mentioned at the beginning of this talk, the steepening of the trend of observed Arctic sea ice decline since the mid-1990s and the smaller trend since 2007 qualitatively match the behavior that is simulated by the CSM2, as can be seen in this figure that shows the 20-year linear trend in September sea ice area with the observations shown in red. In fact, the end year of the maximum negative trend in the observations is only shifted by a few years compared to the ensemble mean of the CSM2. So this good qualitative match with the observations raises the question as to whether the same forcing has affected the observed Arctic sea ice loss since the late 1990s. In the CSM2BB in green, the acceleration of the rate of Arctic sea ice loss during the GFED period is reduced compared to the CSM2, as I've shown before, but also compared to the observations, which suggests that there might be a forced contribution from the biomass burning emissions to the observed early 21st century acceleration of the Arctic sea ice loss. However, the recent reduction of the rate of Arctic sea ice loss is also present in our CSM2 BB experiment, and its magnitude is comparable to the observation, although it is a lot less than in the CSM2, which suggests that there must be other forcings that lead to this sea ice recovery, at least in addition to the to the biomass burning forcing. So just to summarize, I've shown that the CSM2, as well as other CMIP6 models, simulate an acceleration in sea ice decline that coincides with the start of the GFED period, followed by a recovery until the start of the 2020s. We conducted a sensitivity experiment in which we removed the internal variability in biomass burning emissions over the GFED period, and those sensitivity runs show reduced Arctic warming and sea ice decline compared to the CSM2 when the biomass burning variability is removed. We've also shown that half of the increase in sea ice sensitivity from CMIP5 to CMIP6 in the CSM can be attributed to the increased variability in biomass burning emissions over the GFED period. And finally, there is indication of a biomass burning force signal in the observed early 21st century accelerated rate of Arctic sea ice loss, but the biomass burning variability cannot explain the recent reduction in the rate of sea ice decline. So I've left my contact information at the bottom here, and I think with that, I will stop, and I'm happy to take any questions. Thank you.
Thank you very much, Patricia, for that nice talk. And again, congratulations.
Thank you.
And any questions for Patricia? I had a quick question. How many ensemble members did you end up running with the biomass burning emissions, the modified ones?
Yeah, so in this talk, I've shown 10 ensemble members. There were actually 20 that were run, but the additional 10 were done as perturbations starting in 1990. And because we know that sea ice has memory on, for a few years, depending on through sea ice volume, we decided not to include those additional 10 members to, avoid some type of correlation just due to the initial conditions. So yeah, we've used 10, but there are 20. And for things, if you're looking more at atmospheric fields, then using the 20 members would be possible. Yeah.
Okay, and here's some congratulations on the chat side, so you can see them separately, I guess.
Great.
Sanjeev also says congratulations. So any questions for Patricia? Any other questions? Okay, up there just came. Have you thought about, this is from Rebecca Buchholz. Have you thought about, she says, thanks again, great work. Have you thought about how the IAV pre-GFED might be impacting trends?
Yeah, that's a good question. From 40 to 70 north, that internal variability is actually quite small. But that's interesting. Maybe like using a flat, fixed annual cycle for the whole period could answer that question. We haven't really thought about that. We were focusing on that large increase from pre-GFED to GFED. But I suspect that might not be large, given that the internal variability, especially from 40 to 70 north, was pretty small. Globally, pre-GFED, it is obviously a little bit larger. Yeah.
Okay, and unfortunately, I lost my Q&A box. Do you see any other questions, Patricia, there?
I don't see any other questions, and I have the Q&A box here.
Okay, somehow it disappeared from my screen. Anyway, okay. Actually, we are quite on time, 10:04 local time. Again, thank you very much, Jerry and Patricia. Well-deserved awards. Thank you again. So we'll take a 20-minute break, and we'll be back at 10:25. I don't think that we will not stop the Zoom webinar, so you can stay on. And we'll have 3 very nice plenary talks scheduled for the next session. Thank you, and see you in about 20 minutes. I just wanted to quickly check, is Valerie there? We see Paco and Greg, but we can't see Valerie. And Greg just disappeared. Oh, Valerie's just connecting. Okay,
Hello.
Great, Valerie. So we were just worried about you. Great. We'll be starting in about 6 minutes. If you want to check out your slides, that's fine.
Okay, let me do that. Oh, I can't because someone else is sharing the slides.
Yeah, I think Ryan just stopped it.
And in principle, this should work. Can you confirm that you can see my slides?
Yes, we can. Thank you.
Perfect.
Great. Thank you. So we'll be back in about 5 minutes. Thank you.
Thank you.
People are starting to come back, so we'll just wait. We're at 217 right now.
And without any jet lag, which I really appreciate.
It's a bit late in the day for you, though, right?
Yeah, but it's even better like that.
Yeah. Good. Okay, well, we'll go ahead and get started. Welcome back, everybody. And we have 3 plenary talks lined up for this morning. And our first speaker is Valerie Masson-Delmont. She's a senior scientist at IPSL. Her research interests include past climate variability, understanding mechanisms of climate change, both from paleoclimate records as well as from model simulations. She's currently serving as the co-chair of the IPCC Working Group 1, and today she'll be talking about some perspectives from IPCC Working Group 1 ARC 6 report. Floor is yours, Valerie. Thank you for joining us.
Thank you very much for your invitation, and just confirm that my slides project correctly and that you can hear me. Perfect.
Yes.
We are fully in the final run towards the approval of the Working Group 1 report, and I cannot share the key findings with you at this stage. But what I would like to reflect on is the process to prepare this report, a couple of innovative aspects related to the design of the structure and key concepts that are used in the report. As you know, the IPCC has the mandate to prepare assessment reports related to the state of knowledge, and reports are getting thicker and thicker. And at the same time, there are higher and higher expectations for a clear communication of key findings in a way that is accessible to decision makers and to the general public as well. And this is a high-level challenge that we are all facing. I would just like to remind to everyone the mandate of the IPCC. Some of you have a long experience with the Intergovernmental Panel on Climate Change, and it's nice to virtually meet again a number of colleagues and friends. But I would like here to speak to the early career scientists and to provide a bit of an overview. So the IPCC has the mandate to assess the scientific, technical, and socioeconomic information relevant to understanding the scientific basis of risk of human-induced climate change, potential impacts, and options for action regarding adaptation and mitigation. Regarding climate science, this means understanding how the climate system operates, how it reacts, what is human-induced climate change now, and physically possible futures. We are organized in 3 working groups and a task force on national greenhouse gas inventories. And a novel aspect for the 6th assessment cycle in which we are now is an unprecedented coordination and integration across the working groups and this task force as well. The reports are designed to be policy relevant, so we do not prepare encyclopedias of climate science or climate change science. We focus on key findings that are policy relevant, and we need to be neutral, so never policy prescriptive. This means that when assessing response options, we look at the co-benefits and trade-offs, the potential effects and the limits, the costs, etc. So this is a key dimension of the way the assessment is prepared. And the context at the start of the AR6 has been specific. In 2015, there has been the design of the Paris Agreement. There was also in the United Nations framework agreement on sustainable development goals. There was also a UN focus on risk with the Sendai framework to reduce the disaster risks. And this has also set the scene for a stronger emphasis on climate change, climate action, and the multiple dimensions of sustainability. The reports are prepared in a way that is as comprehensive, objective, open, and transparent as possible. we are facing the challenge that the core basis underpinning a scientific assessment is the production of timely new research. But you can see that with just the keyword climate change on Web of Science, we are reaching a stage where more than 40,000 publications appear in scientific journals every year. It is, of course, a growing challenge to be able to assess this mass of publications. At the same time, more than ever, there is a need for a collective effort to investigate what is robust, confirmed, strengthened, what is emergent, potentially important, but which needs to be confirmed. Why are there scientific controversies when different bits of knowledge are inconsistent, when there are limits to the observational data sets, to the skills of the models, to what they include in terms of processes, etc. And another part of the assessment is related to the identification of knowledge gaps. For the AR6 reports, there have been different approaches to that. Sometimes a specific section at the end of chapters, sometimes a design of the assessment of knowledge gaps in the core part of each chapter, grounded in sometimes as well in the key findings of the reports. And this process plays a key role in the maturation of knowledge. So the IPCC reports both stimulate timely publications and collective efforts. One of them is, of course, the intense work targeting CEMIP6 projections, for instance, and the collective assessment helps the maturation of knowledge as well. So for each report, the decision to prepare a report is in the hands of the panel, where there is a representative of each member state, each government. When there is the decision made to prepare a specific report, we start by a brainstorming with about 100 scientists over 1 week to define the scoping of the report. There are two main pillars. On one side, the policy relevance, and on the other side, a significant amount of new knowledge that has not been previously assessed, if possible. This leads to a design of a report structure with chapter titles and indicative bullet points for each chapter. And based on that approved outline, there's a call for authors. And authors can be nominated by observing organizations like research projects. They can be nominated by governments, and they can also be nominated by bureau members like me. The IPCC operates with a small secretariat in the WMO headquarters in Geneva, with for the bureau 34 scientists who are elected for one assessment cycle. And most of the work is actually done by all the authors who apply and volunteer to do this service to the broad state of knowledge. The selection pressure is high. Only 1 out of 6 to 1 out of 10 applicants has been selected for this cycle. That's really important, that there is a huge motivation from scientists all over the world to contribute to the IPCC process. And then the authors write a first order draft. It goes under review by the scientific community. They revise their chapters, and the distillation process starts with executive summaries for each chapter, a draft technical summary, a draft summary for policymakers, and this goes with a cutoff date for publications being assessed for transparency and traceability. It goes under review by experts and experts nominated by governments. The chapters are consolidated, and this goes together with also a cutoff date for the publications that are associated with the review process. Then there's a next step where we are currently for the Working Group 1 reports, the government review of the summary for policymakers. The authors revise that summary for policymaker, and then it's approved line by line, word by word, in a plenary session. This process is, I would say, the last step of a co-design where we listen to the needs indicated by governments, they contribute to the process, nominations, and review, and they endorse the summary and make sure that it's clearly expressed, balanced, and reflects the scientific content of the detailed underlying report. You can also see that as a super quality control process in a way. It also helps to separate the scientific report, which is endorsed by governments, from negotiations on political aspects. So in my view, it's a core part that helps separate the body of scientific evidence and the state of knowledge on one side from the international climate negotiations on the other side, for instance. We are facing a communication challenge because at the same time we are expected to express our key findings in plain language in an accessible way, but we are also supposed to be extremely rigorous, provide traceability of key findings to the lines of evidence from the assessed publications. And we use a calibrated confidence language, the same as at the time of AR5, to report the confidence associated with each key finding. And sometimes we use a likelihood scale for information that is quantitative. This is a barrier for the way our key findings can be understood by a number of end users, practitioners that are not familiar with sometimes the scientific language. We've also introduced for this cycle the term deep uncertainty related to processes that are poorly understood and when there's no possibility to discriminate between, for instance, different approaches to understand a specific process. So this is an additional aspect compared to the usual calibrated confidence language. At the start of this cycle, we've worked hard with specialists of communication. We've included their insights. We've provided their insights to help author teams build on their knowledge on communication. And it includes work on the visual style guide for the figures. It includes a handbook for effective communication and public engagement on climate change, and case studies from special report IPCC authors showing their experience and insights on how to engage with different audiences. And for the main Working Group 1 report, we've used this approach of media training about communication, to develop in parallel to the detailed assessment the key findings from the report that the authors wish to communicate at the highest level. And this has been used to frame, for instance, the summary for policymakers that is currently under review. So we are in a cycle where the pressure to release special reports has been higher than ever. In 2015, we had received 31 invitations for themes of special reports. We've clustered some of them, and as you know, we've released 3 special reports. They have been co-supervised by 2 working groups for the ocean and cryosphere, and 3 working groups for the 1.5 report and the land report. In the 7th assessment cycle, after 2023, it has already been decided that there will be a special report on cities and climate change. And this has been announced early on so that there is the possibility now and in the coming years to provide and to produce, to publish relevant scientific information, including from the academic sector, but also from practitioners using climate information to take action at city levels around the world. I'm going to focus in the rest of the presentation on the Working Group 1 report, but building on some aspects that have been implemented in the first 3 special reports. If you look at the 1.5 report, it has been prepared by around 90 authors from 40 different countries, and they have assessed about 6,000 publications, almost at the time when these publications were prepared. That has been particularly challenging. And from a Working Group 1 perspective, I want to flag that the approval process for our related material has been rather smooth. The most difficult aspects for the approval of the Working Group 1 of the 1.5 report were related to the Paris Agreement, to the nationally determined contributions, that imply a trajectory of emissions in the coming years, which is inconsistent with the trajectories leading to limiting global warming well below 2 degrees or at 1.5 degrees. So the tension on the approval of the report was fed by unresolved issues in the UNFCCC process itself. I want to flag for that report unprecedented integration within each chapter across disciplines and working groups. It also reflects changes practices in the scientific communities worldwide. The approach to link emissions, levels of global warming as a key integration dimension, and regional consequences. And it's one of the first times where we used information from global climate models, for instance, and information from regional modeling efforts in the same place to provide a comprehensive picture of what are the implications of each additional fraction of global warming. We also developed some communication tools building on one box from one chapter, Storylines of Warmer Worlds. This report was also an opportunity across the working groups 1 and 3 for a clearer formalization of remaining carbon budgets. It was also an opportunity to frame the multiple dimensions of feasibility, with working group 1 focusing on the geophysical feasibility of some aspects, while experts from other disciplines and working groups are addressing all the other dimensions. And I want to bring to your attention this publication in Environmental Science and Policy that is stressing the complexities of the interplay between science and policy, given the invitation from UNFCCC to prepare this report. And the analysis from these observers that it may herald ways related to the evolution of how the IPCC operates, for instance, related to the global stocktake in the future. Regarding the special report on the ocean and cryosphere, it's a report that focused on geographies, high mountains, polar regions, the ocean, coastal areas, and on some of aspects related to extreme events and abrupt change as well. The focus, in my view, on that report is on the fact that human-induced climate change is affecting slow varying components of the climate system, with a dimension of commitments that has been clearly emphasized and on which we will build for the Working Group 1 report. It's a bit frustrating now to focus only on the physical science basis, while we had worked on such a socio-ecosystem approach in the SROC report. And as you can see, this has also led to more intense coordination across working groups than in the past, so that what we provide now in the AR6 Working Group 1 report can also be integrated for the coming Working Group 2 report. We flag in that report deep uncertainty associated, for instance, with the Antarctic ice sheet response and implications for sea level rise, and for eventualities that are associated with a low probability of occurrence, but potentially high impacts or risks. We have used the framework of storylines, and this is also used in the Working Group 1 AR6 report. I also like to flag that it's one of the first reports within the realm of IPCC that places a high emphasis on aspects related to education and climate literacy. This is a report from observers about the approval process, stressing that the process with the government delegates ensured that the report was more readable, accurate, and relevant, and that it is a process of translation for which few of us have been trained, explaining technical details in a language that can be understood by policymakers while being true to the underlying science. And if I move to the land report, that land report has been a combo of multiple initial invitations, and it has been designed to address multiple challenges at the same time: adaptation, mitigation, aspects related to biodiversity, water, pressure on land at the same time. And this has been highly appreciated. The Working Group 1 contribution is a bit less visible and less integrated, and there's a focused chapter on land climate aspects, also stressing what we know, but the limits to our tools and to our understanding of the land carbon sinks evolution in a changing climate. Governments really support the fact that we don't approach challenges in silos. So it was highly valued that this report is the first one to encompass the three main international conventions on climate, biodiversity, and desertification, and that it took a systemic approach to the food system compared to the sectorial approach that is often used for other aspects. And the approval process was, again, remarkably constructive. And this is also a spirit we have seen in recent IPCC plenary sessions, which have moved online and are going to continue online for the next weeks at least. So if I go back to the design of the Working Group 1 report, the intent was to build on the three special reports to address the vision for the AR6 of feeding into the work of the Climate Convention and the post-2015 agenda, including Sustainable Development Goals. It was quite prominent from the beginning that we need to have a stronger emphasis than in the past on regional aspects. On the Working Group 1 side, we worked really hard to identify scientific developments, what to expect now, but a few years ago, and to be able to capture these scientific advances in the design of the Working Group 1 report. And this includes cross-cutting aspects with the other working groups, including, of course, regional aspects, and we've had more coordination than ever on that, but also on aspects related to scenarios, emission pathways, and corresponding global warming levels. And the work that has been done on emulators is an unprecedented handshake across working groups 1 and 2, for instance. I also took note of the report from observers related to the approval of the AR5 report. At the time of the AR5 report, which had more or less the same design as the AR4, it was stressed that it didn't have the same punch, that several aspects stood out due to stronger evidence, increased certainty. The attention of the media was quite focused on the so-called hiatus, the slowdown of global warming at that time. And the emphasis was put on the links between cumulative emissions and temperature. When scoping the Working Group 1 report, the wish was really to have a novel design of the structure, to reflect science advances and progress in understanding, to place a strong emphasis on the global and the regional scales, and to develop an approach which would not have a chapter on atmospheric observations, a chapter on model evaluation, and a chapter on other aspects, but to facilitate the integration of multiple lines of evidence. And this is also related to the confidence in understanding and the confidence of the fit for purpose associated with projections. We also wanted to build on the special reports, not duplicate them, but update their key findings and enhance the handshakes with the other working groups. And this has resulted in a new outline where we have a set of chapters on large-scale climate change, the current changing state of the climate system in a long-term perspective, including insights from Paleoclimate research, human influence on the climate system against natural drivers and variability, and future global climate on the near term and on the long term. The second set is dedicated to process understanding and the global cycles of carbon, energy, and water. At the same time, we have also decided to put a specific emphasis on short-lived climate forces, which are relevant for climate and for air quality. And we have a chapter that reflects the SROC report on ocean cryosphere and sea level change again. There was a strong push from governments to provide an update on these issues, including on the very long term. And finally, regarding regional climate information, it's a huge pillar of the Working Group 1 report on methods, on progress related to changing climate and extreme events, including attribution at the scale of individual events, and a strong emphasis on climate information for risk assessment, where you can directly see the handshake with Working Group 2. The Atlas of Regional Climate Change has been expanded following a dedicated workshop to include an interactive atlas, which will be a novel aspect of making Working Group 1 data and assessment more accessible in a more interactive way compared to the printed atlas that was previously available. I would like to flag that the selection of authors was a very delicate aspect for the AR6. We received almost 1,000 nominations, and we selected about 232 authors. At that time, there has been some renewal since the beginning. I want to flag that the representation of female scientists has increased, and we paid a specific attention to avoid glass ceiling effects at the various roles that are available. And the climate science community is changing, it is expanding. There are more and more scientists from a diversity of countries around the world, and this is also reflected in the largest fraction of scientists from economies in transitions and developing countries that contribute to the AR6 assessment. Even when you have the best minds around the world and you put them together, you face challenges that are related to different cultures, different ways of working together. We took support from consultants from Canada to help for the implementation of inclusive and participatory approaches, so as to help everyone engage into the assessment process. We've had 3 physical lead author meetings, and when we had sent our second order draft for review, the pandemic occurred and challenged the end of the assessment cycle. I'm really glad that we could build on our inclusive and participatory approaches and move online for the finalization of the report. And online activities have also strengthened the coordination across working groups, especially through specific webinars, invitations to attend virtual meetings, authors involved in multiple working group reports, specific teams on topics. One example that is publicly available is the guidance note on the concept of risk in the AR6 across the 3 working groups. And due to the pandemic, everybody has been affected, and the schedule has been adjusted with a long online process last summer to take stock of the review comments, and with a virtual final lead author meeting in February, and online activities to consolidate the technical summary, the summary for policymakers. The governments have expressed huge trust in the ability of Working Group 1 to run for the first time an approval session online. It is scheduled to take place over 2 weeks, starting on July 26. And in order to facilitate that, we have drafted a concise summary for policymakers, around 10 pages of text and 10 figures, 2 short tables. And we've also had a series of informal webinars with Q&A sessions, especially for experts involved in the review process, so that we can address the clarification questions in a continuous way and focus the approval on the remaining aspects that would not have been solved in the final revision of the draft before the approval. I want to flag a few aspects here. Specific work that has taken place focused on a cross-working group glossary, so that the terms are used with the same meaning in various communities involved in the various working group reports. The amount of work that has been supporting the interactive atlas, which is really impressive. And to give a sense of the workload, this report builds on 14,000 peer review publications, For the 2 steps of the review process, we've received almost 75,000 review comments from more than 700 reviewers in the first round and more than 1,000 in the second round. I'm curious about how many comments we will receive for the final draft of the summary for policymakers. I hope that as many governments as possible will contribute. We've also implemented a couple of aspects that intend to facilitate communication dimensions. The technical summary has an infographic on climate futures. We have frequently asked questions that are the outcome of broad surveys to users so that they reflect actual questions. We are preparing regional fact sheets as a way to have a brief communication focused on regions, which is because it's a strong emphasis of knowledge developments and policy relevant information. We've implemented the FAIR data principles to enhance the traceability of what is used in our report. The use of emulators has been strengthened. We use emulators informed by constrained projections so that the assessment of the climate response metrics is consistent with the projections for temperature and sea level aspects, which is new. And these emulators are also used for coordination across working groups. Regarding climate information for impact and risk assessments, there's a formalization of what we call climate impact drivers related to trends, extremes, indices of values above tolerance thresholds that affect each region, and an emphasis on low likelihood outcomes at the global and regional scales for a number of aspects. The draft summary for policymakers is intended to reflect the current state of climate, the possible climate futures, place an emphasis on climate information for risk assessment and regional adaptation, and then summarize the key findings regarding the geophysical information associated with limiting climate change. And this will feed into the synthesis report, building across all the AR6 reports, that is designed to start with current status and trends, move to long-term climate and development futures, and finish with the near-term responses in a changing climate. And with that, I want to stress that this, the preparation of the report has been made possible thanks to teamwork within the Working Group 1 Bureau and with our friends from the other working groups, an amazing technical support unit with the key roles played by Anna Pirani and Sarah Connors in facilitating and coordinating the work and the shift to online work. The impressive dedication of everyone involved, including collective reviews from early career scientists that have been remarkable. And I would like to thank each of you who may have been involved, and also host institutions who have supported the authors. The pressure on them has been unprecedented, especially in the context of virtual activities. It's possible to continue online. It's just much more time consuming. Thank you.
Thank you very much, Valerie, for that nice presentation. Any particular questions for Valerie? We have about 2 minutes. Just a quick question. It looks like you have a lessons learned part from AR5, right? And in addition to restructuring the working group report, what are the maybe 1 or 2 additional items that was sort of considered at a high level from AR5 to AR6?
I think there are, I would like to flag the issue of coordination across working groups. In my view, this has been, this is the dimension where most of the progress has been achieved. And it could only be possible because most of the scientists are no more working in silos. More and more climate scientists are working with those developing scenarios, for instance, are working with those focusing on impact studies. And this brings an integrated assessment to a different stage. I think the structure of our reports really needs to reflect science advances, including including these increasing handshakes that are crucial.
And then we have a question from Chuck Hakarinen. He says the use of simulators to present scenarios across working groups is good. How are model uncertainties incorporated into these simulators?
Yes, that's an important part that you can find in the literature associated, for instance, with the development of these emulators and the way they are designed to represent not just the multimodal result, but the range of uncertainty associated with available information. They are not perfect, but they are designed and used in a way to reflect not just the mean results, but the latest understanding about uncertainties. And they are complemented by an emphasis on low likelihood, potentially high impact results, which is a way to cover the whole dimension of a risk assessment.
Okay. Thank you very much. So we'll move on. Thank you again. Thank you for your time and have a nice evening. So our next speaker is Paco Dobles Reyes. Paco is a professor and head of the Earth Sciences Department at the Barcelona Supercomputer Center. His interests include development of global climate forecast systems and climate services based on subseasonal to decadal prediction information, covering sea ice variability, solar and wind energy services, agriculture, and water management, among others. And he's a member of the CESM, I'm getting confused now, either CAB or SSC, just recently appointed, sorry, CAB, I believe. So Paco is going to talk about some of the new modeling developments in Europe. Paco, the floor is yours.
Okay, thanks a lot, Gökhan. Probably I won't be talking that much about modeling, but it's I think it will be an interesting turn to the way modeling efforts are presented. I would like to first start by thanking the organizers to offer me the opportunity to speak in this workshop, and also I feel honored to be speaking after Valerie, whose work is so incredibly useful to the community, and also before Gregory Jenkins. Hello, Valerie. These are the kind of things that I do when I'm not working on the chapter. So, okay, so I'll share my screen, and let me see if it works. Okay, there I go. So I work at the Barcelona Supercomputing Center in Barcelona in Spain, and what I'm going to present here is more an initiative that is being pushed by the European Commission more than my own work. And I'm talking about this program, the Destination Earth program, because I think it's a great opportunity that we have in Europe to change things and to make a significant step forwards in the way we do modeling and for climate adaptation and mitigation, and to address the main challenges that we have to tackle to have a new society that is being transformed to adapt to these and to the resolution of these challenges. This presentation has received substantial contributions from Peter Bauer, who works at ECMWF. The Destination Earth is a program of the European Commission, and the aim is fairly simple, or it can be formulated in a very simple way. The implementation is slightly more complicated. So the objective is to develop a very high precision digital model of the Earth, both solid and fluid Earth, to monitor and simulate natural and human activity, and to develop and test scenarios that would enable more sustainable development and support European environmental policies. And this sounds a bit like policy top-down wording for scientists to keep working on what they've been doing in the past 40 years. But as you'll see in the next slides, this is far from being the intention. Destination Earth has several elements that define its infrastructure. So the infrastructure is contributed by a data lake that will contain or broker all the data that are relevant for addressing, well, to address the problems that are relevant for to address the main challenges that society has concerning nature, and also a core platform that will allow to perform data analysis and simulations. At the same time, it will also provide a set of an infrastructure in the form of software that is developed in collaboration across Europe that are called digital twins. And this is implemented in the context of a really large and ambitious research program called Horizon Europe, which is funded at the height of around 80 billion euros for the next 7 years, and also a very ambitious operation and services program that is run by the European Commission and the European Space Agency that is called Copernicus, that includes the running and launching satellites, and also the development of services for the benefit not of just of the European public administrations, scientists, and businesses, but it's open to everyone around the world. There are two initial digital twins that are being considered in Destination Earth. In the first phase, one is the weather-induced and geophysical extremes that is mainly focusing on aspects related to the prediction of extremes at short time scales, basically weather forecasting time scales. And at second digital twin, that is the climate change adaptation twin, that is the one that will be the focus of this presentation. The Destination Earth engine is made of the high performance computing and data handling ensemble that offers extreme scale software infrastructure, and also cloud computing and data handling set of facilities. And both of them are offering and targeting different capabilities that will be offered to researchers around Europe. And those different elements of the engine are made available to the digital twins that appear in the vertical in orange in the slide. The two that I've mentioned in the initial phase, that are the weather-induced and geophysical extremes digital twin, and the climate change adaptation digital twin. And this digital twin engine is going to be made possible by three European agencies, the European Center for Medium Range Weather Forecasts, EUMETSAT, and the European Space Agency. So they'll receive support from the European Commission to make this program a reality. And they'll align it with many other sources that they have for offering services for both scientists and businesses in Europe. I would like to spend a minute explaining what is new in this engine, and one of the key aspects is the existence of new core platforms in Europe. That are part of another European program that is being put together in collaboration with the member states that is called EuroHPC. EuroHPC, among many other things, is setting a number of pre-exascale high performance computer platforms around Europe. And there are three of these pre-exascale machines that are being installed this year. And there will be two exascale machines that will be made available in 2023. And Destination Earth will make use of these platforms to make to perform the experiments and the data analysis that will make the digital twins possible. And this is key because somehow the Commission, the European Commission, is investing in all the different elements that will make the Destination Earth engine possible and functional. Let me go to the idea of the digital twin and why this is being used in Destination Earth. And I'll start from an example that can be easily understood, and that comes from the personalized medicine fields. So there are digital trends of many things that are being emerging right now, and in particular, the digital trend for personalized medicine is very interesting because the problem starts with the identification of the diagnosis of a problem in a patient, which is this red circle that appears here in the A part of this figure. The diagnosis is analyzed in a computer that is where the symptoms are crossed with many other with a database of many other symptoms that could be compatible with this diagnosis. And then in C, the different treatments are considered for the treatment of the solution of the problem in this specific person without intervening in the person, which makes that the solution is much less invasive than it was so far. And somehow the digital twin in personalized medicine aims at providing the best treatment that could be compatible with the symptoms that have been detected in that patient. And the key idea that I would like to emphasize in this example is that somehow the user comes first. So it's not that very clever people working on biocomputing will come up with interesting ideas and solutions and apply them across the board to all patients, but rather to have a platform that can address specific problems from specific patients. So how does it work, and what is the context that we have in climates? Well, there's a very interesting literature emerging in our community that is bringing together physical scientists and social scientists. And in particular, there's this paper led by David Stainforth that has a very interesting reading here that has been underlined in red, that reads, climate science research needs to be more guided by the questions addressed in the social sciences and economics, which is something that we haven't done so far, or not systematically. While climate economics needs to be more aware of the sources of deep uncertainty in the response of the physical system, which is again something that we have struggled with because the communication of the uncertainties to other fields outside climate outside the research in physical climate has been, to say the least, quite inefficient. However, there are barriers to engage with users or with other communities, and some of these barriers are could include the lack of awareness of the existence of even another community that is relevant to our fields, like, for instance, philosophers of science, or the difficulty of the interpretation of the results and the ideas that are coming from different communities or in the communication with a user, or also the lack of the expert synthesis, and which is something that the IPCC is trying to do somehow for governments to make for them to have the elements to make decisions, but this is not available across the board. A possible solution is to distill, using the best climate data sources that we have available now, some information that could be integrated in decision making. And this is what climate services are aiming at doing. And so basically the goal is that through co-production and co-design of the climate information to develop that information that could be relevant or for planning, policymaking, and practice at any spatial and time scale. However, even with the help of the social and human sciences that are fundamental to make this work, to make this chain that is feeding climate the practice of climate services, we have a problem to achieve success. And is that the quality of the service is severely limited by the quality of the current climate data sources. We know already, and for instance, Jerry mentioned this during his presentation, that one of the main problems that we have is the important and severe model errors that our models have. And this has important consequences. And there is this very interesting book by Matt Brown with the title Science and Moral Imagination that contains many interesting ideas. But one of them is that the reliance on not good enough models could lead to overconfidence in our conclusions. And that, in the essence, it could lead to the underestimation of the uncertainties of the information that we are dealing with. And also, what is even worse, the physical risk before we make any decisions. So what is the role of the digital twin and destination Earth in this context, in which models and the sources of the climate data that is being used to produce climate information are not adequate? Well, as I mentioned initially, there are two digital twins that will be implemented in the first phase of Destination Earth. One is the extremes, the digital twin. The other one is the climate adaptation digital twin. That both of them will have to look and consider the three aspects that appear there: data simulation, scalability of software infrastructures, and links to impact sectors. But the really interesting thing is that the expected phases in the implementation of these digital twins should start with this first point here. This sweet definition with the of the experiments that will be performed in the design of these digital twins that should take place with the identification of representative user needs, and this is where things are changing. So the users come at the time of designing the experiments and at the time of implementing any of the new things that we want to introduce in our models in programs like Destination Earth. There are other phases that are very important as well, like the implementation plan, which will bring us from research to operations, because it's also important to mention that Destination Earth is not a research program. It's a program to enable a change based on the on new technologies to increase our operational capabilities. And then there are lots of science questions that we want to address, technical questions that will need to be addressed, and organizational efforts that will have to be coordinated, plus important resources that will be required and also that will need to be estimated. If I go to point 3, the big science questions, and what makes us think that this ambition will bring us to anything that could provide better climate information to the users, I would like to use a few examples from either published literature or from a European project that finished a few months ago called Primavera, also funded by the European Commission. And both the literature and the results of this ambitious project, that was the Harris-MIP contribution from the European institutions, is indicating that the increase in resolution of our models is making them more realistic. And this is particularly the case when we start considering things like the interaction between the ocean and the atmosphere, which we know is critical if we want to have a realistic estimate of the impact of climate change over land, or the representation of the characteristics of tropical cyclones in basins like the North Atlantic. So somehow we know that the increase in the atmosphere and ocean resolution at a minimum will give us the opportunity to explore and represent the physical processes that are relevant to understand and predict climate much better than with the models that we have. But at the same time, this needs to be also supplemented by a better use of the observations, and as I said before, a clear identification of the user needs. In any case, what it's important is that in spite of how tempted we might feel from increasing the model resolution to have to make a more interesting paper to be published in a few years' time, the important thing is, and the key is to be aware that the objective is to support good decision making and not to end up just with another beautiful model or a set of new really nice models from the scientific point of view. The instruments to make this a reality are provided on one side by the Digital Europe program, which is part of the European Commission's programs for the increase the digital capabilities in the European countries. So the first phase of the this program that is funding Destination Earth will last 30 months and will fund a core platform at the height of around 80 to 100 million, and the implementation of the first two digital twins at the height of 25 to 30 million each one of them. This is for 30 months, and it comes on top of the really substantial funding of around €1 billion for the new pre-exascale machines that will be made available to Destination Earth at around 10% of the total resources available to the Commission, which is a non-negligible amount of computing time to say that has to be taken into account. At the same time, and as I said at the beginning, Destination Earth comes along with other programs of the European Commission. In particular, is being aligned with this Horizon Europe program for research and development, where there are already calls announced that are aligned with Destination Earth and mention Destination Earth in their wording, targeting different aspects like the research necessary to develop Earth system models and adaptation scenarios, or the development of research for research infrastructure necessary for implementing these digital twins. There are some breakthroughs that will be necessary to make this a reality. One of them is a better use of extreme scale computing and data handling, and that's necessary if we want to have more realistic models, but also a better use of the observations and a good combination of these simulations and observations to improve those models. We also need a substantial effort to have a full integration of the social sectors in the workflow, so that we can end up with information that is action-oriented. And at the same time, one of the key elements in all the actions that are promoted by the European Commission is that there is open access to the data, the software, and the workflows that are generated, so that there is the possibility for non-experts to access, and what is really new, to intervene and make a selection of the data sources that they are most interested in. So summarizing the role of Destination Earth for climate, I would like to mention that at the core of the program, the benefits to the local and regional actors can be found. And this is expected to happen through a better use of the observations that could also help to have better models, the use of new platforms for high performance computing and high performance data analytics that can enable ambitious experiments, upgraded workflows and data treatments that could allow and make these ambitious experiments a reality, and to address problems like how to merge climate predictions and climate projections along the lines of what Jerry has mentioned in his presentation, so that users can finally have a real impression of what is actually interesting to them, instead of the information in silos that usually they are offered from the climate research community. So why to tell all this in a workshop like this one, when mainly this concerns the activities in Europe? Well, one of them is, one of the motivations for this presentation is to offer the opportunity, or at least to open the floor for a discussion on how to collaborate in Europe and between Europe and the US. And one of the possibilities to do this is through the World Climate Research Program Digital Earth's Lighthouse activity. Lighthouse activities are a new cross-cutting activities of the World Climate Research Program, of which there are 5, that try to bring together the traditional separation of the communities that that takes place in the program. And out of these 5 lighthouse activities, there is one that is called Digital Earths, that is aiming at the establishment of integrated interactive digital information systems that provide information on the past, present, and future of our planet. So that wording that appears there in red in the slides is not very different to what we have been trying to do in the last few decades. But however, when we look at the 4 areas of activity that have been formulated as part of this lighthouse activity, we can realize that there is a strong parallelism with what is already planned in Destination Earth. One of them is the work on global coupled ultra-high resolution modeling, with the aim of ending with feasible models that can run at 1 kilometer resolution in both the ocean and the atmosphere, and if possible, also the chemistry. A better use of the data simulation, but this time for climate, not just for the initialization of weather or climate forecasts. The formulation and development of regional digital Earth systems, so basically regional models that can really address problems that have been somehow neglected so far. So for instance, like how to provide climate information for urban settlements and cities. And finally, also the 4th activity is the engagement with a broad area of digital technologies. So somehow very close to some of the aims and objectives of Destination Earth. The second opportunity is the new EU and US agenda. There are discussions between the US and the European Commission to set a new transatlantic agenda for global change that is very ambitious and that tries to tackle 4 areas that represent key challenges for humanity. In area 2, we find that the aim is to work together to protect our planet and prosperity, where climate change plays a central role. And the European Commission is actually currently looking for projects that can be included in that area and that can foster the collaboration between EU scientists and US institutions. So I'll leave it there. I hope it wasn't too long in my presentation, and I'm open for questions. Thank you very much.
Thank you very much, Paco. So we already have a question from Jeremiel. He says, what will the mechanism be, i.e. how will you do it to entrain users into the experiment design process?
Okay, yeah, Jerry really points to the key difficulty here. Somehow that what has been happening in increasingly Europe is that there has been huge investment in the development of climate services, and I know that similar efforts have taken place in several institutions in the US. I think that the difference in Europe is that there has been a specific intention to bring together communities like physical climate and social sciences, and there's an increasing number of philosophers of science that are working in in climate modeling institutions. I wouldn't say that there are a lot of them, but it's a non-zero number, which is an infinite increase with respect to what it was 5 years ago. So somehow the inclusion of social and human scientists in institutions like, for instance, at the BSc where I am, really makes the people who are working on the implementation of these models more aware of the difficulties that the users might end up having. So, for instance, it's very common that many of us have been called to give talks in professional meetings, or in even in dissemination workshops or events. And what we find out is that at first, most of us find it very frustrating. And second, it's incredibly inefficient because we don't have the instruments and we don't have the vocabulary to do these kind of things. However, it seems to be much more efficient, and it seems to really attract much more attention if those presentations or those dissemination efforts are made by people who can really bridge the gap in terms of vocabulary, concepts, and even formulation of questions between any kind of user, including the citizen and the physical scientists and the kind of work that we do. So that work has been already done. And I'm not saying that it's already over, but there is a path that is already clear to, for instance, try to solve questions like, for instance, which variables are really relevant to keep? And what is the resolution that is really relevant instead of trying to keep everything at 6-hourly or 3-hourly frequency at the native resolution? So things that have a really strong impact on the way we run our models can be addressed from a completely different point of view if we take into account those who are going to use the information, not the data, but the information.
Okay, thank you. Any other questions for Paco? I had a quick question. I believe there's a very recently funded effort led by Bjorn Stevens, also funded by the European Commission, I believe. How are the two projects related? I can't remember the acronym of that new one.
Yeah, you're talking of NextGEMS, probably.
Yeah, I think so. Yeah.
Yeah. So NextGEMS is it's a research project funded by the European Commission. I think it's funded with 10 or 12 million for
Yes.
4 years, and it's basically working in the same direction. So NextGEMS is mainly focusing on the model evaluation of models that are that might be either coming from the Destination Earth development efforts, or that might set the basis for the Destination Earth developments. So NextGEMS is, for instance, trying to run global couple models at around 5-kilometer resolution, trying to address problems like what is the impact of having explicit convection, deep convection in these models. And going back to the question about what is the role of social sciences here. So one of the issues that they are going to try to explain is what is the relevance, or why should the public administration invest in global models at those resolutions when we have Cortex? Yeah, this seems like a trivial question, yeah? But the users really ask these questions, and we don't have the elements to respond to these questions. So we need an experiment at 3 or 5 kilometers that is comparable to what Cortex is already doing. We need to scientists that do perform the model evaluation of those experiments, and we need someone who is going to be able to explain this to a policymaker in simple terms. And this is what it's one of the things that NextGEMS is going to do. So they're going to run in parallel. There will be other projects that will be looking at how to formulate the new HydroSmip2 in the context of the development of these new models. For sure, this is open to the participation and collaboration with scientists in other continents. So somehow what the Commission is trying to do is all these different programs to try to align them so that we can see a real change in climate modeling. But it requires funding, and it requires machines to do it.
Right. We have two questions. I'll try to take one from Hansi Singh. Thanks for the talk. I was wondering how the digital twin framework will account for internal variability in the Earth system.
Okay, so this is a very good question. So how do you run an ensemble, for instance, in a case like this? Yeah. So let's imagine that we want to run a simulation of at around a global coupled simulation at 3 kilometers. That we can do 6 months per day of simulation. Okay, this is ambitious, but is doable in the period of time that we are talking about here. That means that every 3 months we'll have one simulation that will be of something like 50 or 60 years. And we can, once that simulation is over, and assuming that we are focusing on the next 20 to in the next 20 to 30 years, we can run one simulation right afterwards. So we can have these simulations running continuously. It's not that we need to have those ensembles all at once. The point is that by running simulations in that way, of course, we'll need quite a lot of members to do this thing and quite a lot of time. But the good thing is that the continuous interaction with the users by doing this thing will also allow us to adapt those simulations to provide the outputs that those users will be really interested in. So variables that are missing, diagnostics that haven't been included at the beginning. So it's not ideal, but it's probably the best way that we can make use of these machines. Again, taking into account that the Commission really made the commitment of providing all this computing time already.
Okay, thank you. So there's one more question. If you can answer it, that's from Chuck Ackern, and you can answer it in the Q&A separately.
Okay,
thank you, Paco.
I'll do it.
You should
Thanks
move
a lot,
on.
Gökhan.
Right, thank you. And our final speaker for this morning or this afternoon or this evening, wherever your time zone is Greg Jenkins. Greg is a professor of meteorology and atmospheric science, geography, and African studies. He is also the director of the Alliance for Education, Sciences, Engineering, and Development in Africa in the College of Earth and Mineral Sciences. His general interest areas include atmospheric chemistry, climate change, and tropical meteorology, all with a focus on the African continent. So Greg, the floor is yours. Thank you.
All right, thanks so much, Gökhan. In the event that I'm having issues with my internet, in the event, I will just ask you to run it. Yes. And I'll just speak from there.
Sure, I have
so
the
first of all,
presentation.
First of all, I'd like to thank you for inviting me, Gökhan, and also all of the great talks this morning. I enjoyed them all, and I'm looking forward to the rest of the workshop. And you know, I began my my whole science career at NCAR as a grad student. And I'll go more into a few of these things in a bit. So let me share the screen. And again, hopefully I can get through this. This is a slightly different talk, but it's one that, you know, reminds us why we do the work that we do in our various, you know, from our various perspectives. It's just an extreme event. This is Hurricane Dorian. As it's about to impact the Bahamas. And so I'm going to talk about climate justice, the challenges and the opportunities to the climate community. So first of all, the key takeaway points are the climate science community needs to increase the insights. So what I mean by that is the processes and the connections to societal impacts and the responses. It needs to increase its awareness that we can only focus on science without understanding that there might be societal issues entangled. And then we all have to go beyond our zones of comfort when you're dealing with climate change or climate justice. So it's not, I wish I could just think about science, but I really can't. And then the climate science community, and this one is probably more challenging, must step up to the nation's effort around climate justice and how that becomes actionable science, and then how it becomes, you know, a climate justice solution. You know, we hear the agencies talk about the role of climate justice, but it's not very clear about what action should be taken, especially from a place like NCAR or even at many of our institutions, universities. So let me start out by saying, this is how I define climate justice. Now, there are definitions out there, but for me, from my experiences, is that it's the intersection between climate change and our climate science community, social justice, and environmental justice. And the picture there on the right is an example of what I mean. So this is the People's Climate March in 2014. We're marching for climate, but the students in the front are African-American students, and typically they're out there focused on environmental justice. But look closely and you'll see that all the students have their hands up. And this is at the point when there was, I mean, I don't know, tens of thousands of people who wanted 2 minutes of silence for the earth. But these students also understood that earlier in the year, Mike Brown had been killed by the police. So they also were aware that all of these factors were playing out at once. So we all know this about the warming of the planet. So when we show this to each other, we're kind of bored and saying, okay, what's the uncertainties? But every single time I show this to a public audience, they're all saying, what is going on? And if you show it to even some of the folks who might be resistant, like farmers in central Pennsylvania, they say the same thing. What? It's everywhere. So we have to think about the impact of our work and its connection. So let me start out by showing you a little bit about environmental justice, and then we'll, hopefully this may work. Then we'll kind of move on.
Well, the environmental justice movement is, as a movement, is relatively new. Although there were lots of isolated struggles that occurred in this country prior to 1982, for example. That's usually the date that's given for the birth of the movement in Warren County, North Carolina. There were lots of struggles around pesticide and farm workers, around communities that are struggling against highways being built through their communities, and with petrochemical plants, et cetera. But it was not until Warren County, where that PCB landfill, that toxic waste landfill, was placed in the middle of this predominantly Black county. And residents in that community said no. And we started to get people from all over the country, led by Reverend Ben Chavis, who at the time was the executive director of the Commission for Racial Justice at the United Church of Christ, that began to galvanize people and attracted lots of folks to Warren County and to protest that landfill and to talk about this whole idea of environmental injustice and environmental racism. And once we started to see people actually going to jail, over 500 people went to jail over the siting of that landfill. So it became not just an environmental issue, it became a civil rights issue and a human rights issue. And that's when you start to get people from all over the country, African Americans and Latinos and Native Americans, Asian, Pacific Islanders, to start to think about this whole idea of everybody has a right to live in an environment that is free from pollution. And no community should become the dumping grounds. And so I think that's, you know, that particular moment in history in 1982, where this shot heard around the world of environmental racism and this Black community being dumped on, being targeted, and people saying, no, we have a right to live in a clean and healthy environment. That's when the whole idea of environmental justice as a national movement came into effect.
Okay. All right, so let's, if I pause that and move on. So let's, if we can, take you here. Again, hopefully I have enough bandwidth to run this because it's instructive to know really how this plays out.
Warren County to become a dump site.
The State Highway Patrol began moving in on the marchers as they approached the entrance to the state landfill. The signs and chants of the protesters made clear their opposition to having the toxic chemical buried in their county.
I don't want this stuff thrown in my water. We're marching because we do not want this to affect our future. If you do not cease this unlawful act, you will be arrested.
The leaders of the protests said they would not move, and they were the first arrested. As they were being escorted away, the crowd moved in on the entrance. Many of the marchers then sat in the road, and the patrol began arresting them and placing them on a jail bus.
State officials said they had no choice but to make the arrest if they were going to move the people out of the way and get the trucks in here.
One protester jumped in front of the first truck and was quickly hustled away. In all, 10 trucks arrived for the first dumping. As they unloaded the PCB soil in the landfill, state and federal officials defended the decision to stop protesters and to store PCB here.
We were hoping that we were going to have, of course, just the protest, but you witnessed the fact that there was an attempt to obstruct, which we simply could not allow to continue.
We feel very confident that we've built a facility that is going to work the way in which it was intended, and we intend to just carry this project out to its completion.
State officials say they're determined to continue the operation until they get the job done. Brenda Summers, WBTV News, Warren County.
Okay, so the issue here is that this would not have happened in neighborhoods with resources, and it would not have happened in white neighborhoods. And so when we shift this out to talk about social justice, we know all of the events that have been going on, and they have impacted us, many of us, over the last year and a half, to the point of exhaustion. And it's not just George Floyd or Breonna Taylor, it goes beyond that. It's been going on for a number of years. And it's, this last week, we talked about, or 2 weeks ago, the Tulsa race riots, which basically led to a lot of death and the complete destruction of many Black-owned businesses. So this is not new. It's police brutality, mass incarceration, redlining, educational inequity, health inequity. These have been underlying issues that have gone on for a very long time. So when I take you back even further, it's just to give you your understanding of how did we get here? So this is Africa as we know it today, as it's known today. But this is the diaspora. And the diaspora was created hundreds of years ago. In fact, in 1434, the first Africans were taken from Nigeria to Portugal in a place that's now called Lagos. And if this runs, I would just like for you to visualize, this is a visualization of slave ship tracks across the Atlantic. And, every dot that you see represents a ship with many people in them.
It's not running, I think, Greg.
Oh, I'm sorry. I have to do a new share. Let me do a new share. Okay. So let me pause and just an example. So this is the 1600s. This is letting us know the ship that, it's transporting people, whether it's Spain or Portugal, or most of these are ships from Portugal, but we'll let this run through time. And this is really the crux of the problem, because without representing history correctly, we can't really understand the problem, and so we can't understand the solutions either. And I show this to my class, freshman seminar on climate change and et cetera, because I tell them that, like, we can't solve these problems unless we're grounded correctly. And so this is a time when in the Americas, there was all of this talk about independence and freedom and liberty. And so it's just such a contrast and a kind of a oxymoron to the fact that while people were talking about freedom, millions of people were being enslaved at the same time. And come up on 1776, and you see so many ships with so many people. They're forced into these ships. There's nothing voluntary about it. You cross 1776, you get out to the Constitution time frame, and we know that transatlantic slavery was supposed to come to an end in 1808. And yet you see just gobs of ships just continuing. And I might say that the 1808 end of transatlantic slavery did not mean the end of slavery and the movement of people in the United States. Did not mean that. So we're after 1808, and we see lots of ships going towards Brazil. Let me just pause it again so you can get a sense of again, this is a Brazilian ship, French, etc. Just an amazing number of people being moved into bondage, because it wasn't the end, it was the beginning. Most in South America, you were working sugar plantations, the Caribbean, sugar, the US, cotton. So we still see these ships moving. The British they were patrolling in the late 1800s. So we get out here to 1859. And this is about 50 plus years after the end of transatlantic slavery. And if you click these ships now, you see large American ships still moving people from the continent, and they're moving them towards Cuba. And again, there's not a way that history can resolve these kinds of things, except we can say it happened. So let me go back to the presentation, which is here. And all of this has consequences. So if you look at me, I'm like millions of Black people in the African diaspora. We do not know exactly our origin, where we came from. We also know that we may have some of the enslavers' genes, DNA inside of us. This is something that we've got to come to grips with. But we don't know. My people are from all over the coast, from Senegal down to Angola. That's where we're left. And when I go and I do research in Africa, I always take the students with me. These are students from Howard. And it's because we all realize that, like, if someone didn't survive that passage and then have the strength to just continue through slavery, working cotton fields and experiencing a lot of violence, we wouldn't even be here. So we recognize that. And Beyonce, who's the singer, says that the coast belongs to our ancestors. And I feel like this is really something that many African Americans feel when they go to the continent, that there's a place of departure. If we think about the Industrial Revolution, we always have to ask the question, where did the dollars come from? Well, the dollars came from the backs of people who were forced into slavery. So you see in 1791, there are 2 million pounds of cotton, but by 1860, it's 1.5 billion pounds of cotton. This is driving the Industrial Revolution in Britain and in Europe and in the US and throughout much of Europe, because the income, the resources are becoming available. Now, this is the US side of the picture, but this is the African side of the picture. Extraction to the max, whether it's peanut oil or palm oil to drive machines in Europe, rubber or minerals, and all this is being exported. So people on the continent were subject to the same level of violence as in the US. And so when you look at this picture on the right, I put Hershey chocolate because to this very day, cocoa is exported from Ghana directly to Hershey, Pennsylvania. And so many products are exported to Europe without any processing on the continent. And so when you say there's 50 or 60% unemployment, you can understand why, because everything's exported away and there's no processing in many of the countries. It's a tragedy. And when you look at the income of people on the continent, this is really it. This is a direct consequence of what started in 1434. And this is the real paradox for Africa. Very low emissions, but many people who live in extreme poverty. So we know that they won't be able to adapt to climate change. They're not the resort. There's no need to talk about resilience. When you're living on $1 or $2 a day, that's not even in your vocabulary, resilience. This is a kind of a global north term, and it makes sense for the global north. It might make sense because even within the global north, there's a lot of inequity. So one of the things that I'm thinking about is the climate solutions. So we know that everyone's saying, if we get transportation offline, we go to electric, that would reduce the negative impacts from carbon dioxide and other pollutants, particulate matter, would make the air better. But it might not work, especially if we are, excavating cobalt from the Congo on the backs of the poorest people in the world. That's a problem, and they might be kids. So we have to think these solutions carefully and through a very just lens. Now, just this example, this was in the New York Times last year. This brings home where EJ and climate change and social injustice all come into play. So look, this is redlining in Richmond, and redlining happened all over the country. And it was driven by the federal government. So those areas which are in pink are typically the areas where people of color and poor people went. These were not the places that the government considered good. And so all kinds of things happen around this. Many of you know that for many of the houses that were sold, they could not be sold to African Americans. It was written. The banks weren't going to give you the money, and the realty company, they just would not sell you the property. This might still be going on, but this is where it started. But the part that really comes out to light in this New York Times article is the fact that when you look at red line districts, there's a lot more concrete there. And consequently, there's less tree cover in red line districts. And if you compare those to other neighborhoods that weren't red line, you don't see that same kind of pattern. So what that all ends up meaning is that red line districts are warmer than the surrounding areas where there's wealth or where red line districting didn't occur. But this is also true in flooding. And many of the poorest neighborhoods were built in poor drainage areas. And that's a fact, whether it's the 9th Ward or some parts of the US in the north, Northeast, et cetera. this is how the system was built out. So we really can't talk about climate change without understanding that this other piece is running in the background, because it is, and it's going to have an impact in the future. And in this article, they just went through numerous cities, and all the areas that are considered like least desirable had much warmer temperatures, you know, relative to the areas that were considered the best or desirable. And we're seeing this play out. We know it's going to play out in the future. So when we talk about heat stress and heat waves, we're going to have to really think this through carefully. And somehow we need these communities at the table, but it's a real hard thing to do when you don't have power. So we come to an end here. You know, we all know where the high emissions are coming from, and we know where the low emissions are coming from. But what we also know is that large areas where we have low emissions, the continent in particular, are going to be impacted. They're highly vulnerable to climate change. And when you look at the US and you get down at the county level and all these other levels, like you see it, it's very clear. And not only is inequity and vulnerability there, but quite often the laws help to keep it there, to sustain it, not to break it down. That's going to be an issue over time. At the end, the costs are still there. You can't get around it. So I'm in the last 4 slides, and here I'm talking right to us, the climate sciences community. So first of all, we got to really think about the research that we're doing. And while we talk about research to operations, that won't be enough. Like, you carry the burden. It's not someone else. When we talk about climate change, we're talking about projections down the line. We're not necessarily talking about an upcoming forecast. Now, I know there's been a push towards that within NCAR and also NOAA, but we just really need to understand that when people are talking about climate change, they need more guidance. And so there's a limited focus on research to societal needs, which I call R2SN, or research to policy. We got to go down that road. I mean, this is not a kind of a stationary problem that we're dealing with. Now, the communications of climate change threats and impacts on society and vulnerable communities, they are not clear to those constituents. They may be clear to you, but they're not clear to them. And you can't talk about policy without talking about the public, because it's the public, normal people, who elect policymakers. And if you want to deal with an intergenerational problem like climate change, the route that we're taking is wrong. I'm not going to say it's right by any means. We are behind the problem, and it will take a while to catch up. And then I got to say this too, because the reward system needs realignment in facing global threats. We've all been trained to chase grants, to write papers. But there comes a point where you start seeing devastation, and that's not the solution to those people who are being impacted. That there needs to be an adaptation plan that starts to emerge around how do we deal with these threats. And I don't think the position that we've taken in the past is going to work. I think we've kind of seen that happen with COVID, where we've seen a lot of inequity break out, and you don't deal with that inequity through traditional means. So when the bus or the van that's administering vaccines goes to the poor neighborhoods, you know that if the bus or van doesn't go there, those folks are not going to take the vaccine. So you got to step out of your comfort zone. So let's end this out, okay? So in my opinion, our community has to address science priorities. People know more than likely that the change is happening, but they do not understand the rates of change. They don't understand the intensity that might be associated with an extreme event. The scale isn't very clear. We're all down at the local scale. We don't know if this is happening regionally or nationally or internationally. And I'm just really talking about the average person. And then the subseasonal stuff. It's been a big problem in Africa for a very long time, but it's starting to impact the whole globe. And people need to know what to do. Farmers, resource managers, power companies, they all need to know, what do we do? Is this going to increase over time? And if so, what strategies should we start taking? And it's not always a technology strategy, okay? It's really, part of it is awareness, because you have to talk to your constituents about that. Obviously, sea level rise, the Antarctic ice sheet collapse, if we're talking about Thwaites Glacier, and coastal communities are totally coupled together. If Thwaites collapses, there's going to be hundreds of millions of people that have to move in the next century. They need to know, what is the likelihood of that? They need to know what happened from the paleoclimate community 120,000 years ago when it collapsed the last time. They need to know from the archaeologists, like, how did these societies manage? And they also need to know this from traditional societies in North America, like the indigenous people who've been here for 10,000 years or more. What did they do in the face of a changing climate? They have histories and they know how they dealt with it. But with 7, 8, 9 billion people, that is not going to work well if we don't get ahead of the curve. And then the impacts on BIPOC communities and the poor remain a major challenge. Every time a hurricane hits the Gulf Coast, I hear half the people saying they're going to rebuild, and I hear the other half saying, I don't know what I'm going to do. And then as scientists, all of us, we have to shift to this more advisory role to society. When people are asking us about what's going on, we can't point them to the IPCC report. We have to tell them right there. And we can't really be, talking about uncertainty and risk. They don't get it. They just don't get it. Now let's finish this up. So let's talk about the BIPOC community again. We have low capacity, and that is impacting us and our ability to get the messages to our communities, but also to be engaged in looking for solutions. Less than 3% PhDs to African Americans. In some cases, no one's at a university. Very few Black women in this field at university. This is a problem, okay? National labs, it just spills over. Not many people there. Universities, funding agencies. So you see this trickle down over time, and it's no solution to it. And then this other issue, which is about our mindset. Meritocracy does not address equity or injustices. You can't address it by saying you get in if you get, 1,400, GRE score. That makes no sense. How do you get people in? This is a big problem, and no one knows how to do it except the people who are totally engaged in it. Then, even if we get people in, the work environment could be wrong. So the work environment may not support the recruitment or retention of BIPOC climate scientists. You might get them in, but the experience might be so horrific that they leave. Or you can't get them in. And it's not that you're saying we can't find them. It's our search committee process is a problem. We automatically go to CVs. We don't look at the rest of the person. We think about what we want. It's selfish, and that's the way we've been trained. I'm telling you though, you can leave this problem, it's not going to get better. So we also have to realize that these societal injustices, they are there, they remain significant, they impact people, whether it's students or faculty or scientists. You get knocked out of the game when you see people shot and killed on TV by the very people who should be protecting you. This is not cool. Really, it just isn't. So let's talk about the opportunities. Here's our opportunity. Increase BIPOC involvement in climate sciences. In sciences, think about your mission policies, your hiring policies, and if they are not or there, if they're there or not, make sure that your environment is right, inclusive, diverse, anti-racist environment. Some of you don't know what that means. But for me, if I'm catching a lot of microaggressions, that is a racist environment, because at the end of the day, my energy is gone and my stress level is super high. And I don't need to check off early because that's already a thing that runs in my family. Got a mentor. This is all of us can do this, but you got to remove this like white superiority framework. You can't be saying, if you don't do like I do, no, just accept people where they are and deal with it. Our job is to entrain. Our job is to communicate. Our job is to pass knowledge so that others can continue. We can't do that if we're turning people off. And then we got to help communities, because this is real. And when I've seen it with my own eyes, it really hurts to see how people are being really impacted by climate change. So we got to do more interactions. It's not enough for us to just write papers to the journal Climate or Science or Nature. We got to get out there with people who are out there on the front lines. A lot of young people are in these nonprofit groups. I do not run away from them. I feel like they have to know the best climate science and what's happening. We have to deal with farmers, and we got to deal with coastal residents. So they don't know what's happening, but they know they're being impacted. So my last slide is this one. So mentoring, it takes a village to raise a climate scientist. As you know, Warren Washington is and will always be my mentor. And we paid him back for all the great things he's done by naming a building at Penn State after Warren, but also Jerry Mill and all of the others that I really benefited from at NCAR, Chester Newton, Jim Hurrell, others, that was very valuable in raising a climate scientist. So I'm going to stop there. I hope that you've gotten something out of this, but more importantly, I hope that you can see your own power as individuals and as institutions in helping to deal with this issue. Thank you.
Thank you very much, Greg. That was a great talk. So we are 1 minute late, but there is a question that I think we can take. Actually, there might be two. Let me check quickly. From Adrian Foster on the chat side, do you have any suggestions for people with privilege, i.e. white, but little power, i.e. early career, to push back against those in power for trying to increase diversity? E.g., when your department chair says, no, we are not going to investigate demographics for who is dropping out of our program because we don't think it's important.
You got to challenge them, because if you don't deal with accountability, you can't get these problems solved. And that's really so you put yourself in a risky position, but trust me, it's worth it at the end of the day, and it's appreciated.
So one more question on the Q&A side from Christine Shields. Great talk, Greg. Can you give us an example of a local or regional, county, city, state, etc., effective R2P project, and hopefully one that takes climate justice into equation? Thanks.
Yeah, at the local level, I feel like it's R2P and is research to societal needs. So you get in there with all the stakeholders. The stakeholders really have to put the pressure on the policy folks. And really, they have to deal with it. If your area is being flooded, they got to find solutions. But it really is your role in helping the local group deal with that. They have questions. They need your expertise. And they need you to also advocate with them for change. It's harder as we go up in scale, but it's really the same thing. It's, you've got to deal with all the stakeholders. And hi, Christine, long time.
Yeah, Greg is actually an NCAR person too, as you said. And then he's actually serving on the CESM CAB, just started serving earlier this year, I believe, if I'm not mistaken.
Yeah.
And then there were two comments, but they are not questions on the chat side. Holly Oliveira says, Greg, thank you for talking on the most important topic of the day in terms of what to do about climate change. And then Yungchin Zhu says, I'm very touched by your talk, Greg. Thank you very much. Amazing talk from Stephanie Falk. I think that's it. Any other questions for Greg while we have him?
You can always contact me by email if you want. I'm always available.
We lost your visual, Greg, by the way, but anyway, I think we are done. No more questions. Okay. Well, thank you very much, Greg, and thank you for to all of our plenary speakers. So we'll come back at 1 o'clock with 15-minute sort of brief updates from the working groups. We will keep the Zoom on. If people want to stay on and chat or do sort of socialize a bit, that's available. So we'll be back at 1 o'clock and Zoom is on. Thank you.
Are you there, Elizabeth?
Hi, Julio.
Hi.
I can see you and hear you, which is good.
Okay, good.
Greetings, Julio.
Hi. So soon the race starts to finish in 15 minutes.
Yeah, I mean, I have to keep time, right?
I know.
We can just cut you off and we'll just...
Yeah, just cut me off. I'll have my stopwatch going, so...
We'll have Elizabeth to just move the slides quickly.
Yeah, you need some kind of like that shepherd's crook.
Yeah.
Get him off the stage.
I couldn't remember whether I put any break in the agenda. I guess we did. Okay, there's a 2:30.
That's good. Oh, you're at NCAR?
Yeah, I'm in Greg's office actually in the information systems area.
Okay. Yeah, I'm bumping my my attendance to twice a week in July.
Okay. Yeah, I'm coming 3 days a week, Tuesday, Thursday, and Friday. So
okay.
This is a special day, though. We wanted to run it at least the first day from here,
yeah,
just in case.
I can well understand that. So I'm desperately hoping that by the winter meetings we'll be back in person.
We can only hope.
That's all. Yeah, that's all.
Yeah.
Maybe some hybrid. I don't know.
Well, I mean, as we discussed before at the working group co-chairs meetings and all that, we are missing the in-person interactions, lunchtime interactions and breakout interaction or break time interactions. So
yeah, yeah.
Nothing new.
That's for sure. I mean, there is the advantage of being able to bring talks from overseas.
That's like, I mean, yeah.
But yeah.
It's interesting the amount of investment at those ultra high resolution models that Paco was talking about.
Yeah, yeah. And as far as the improvements, I mean, certainly the Gulf Stream separation really depends mostly on the ocean high resolution, doesn't it?
Well, likely, yeah. I mean, primarily that's correct. And if I'm not mistaken, he said 1 billion euros for the computers and all that stuff, right? That's what he said.
I didn't catch that. I saw they were running, I thought it was a misprint, but maybe it's not. 1/10 degree atmosphere?
Yeah, that's not a misprint.
Yeah, wow. By the way, speaking of resolution, maybe I shouldn't ask at this here, but
yeah, we'll ask it later.
Yeah.
So the number is going up to 122. So we'll start in a few minutes.
Okay.
I see one of the nicks. The other nick is missing.
Mm-hmm.
I can't go wrong with the whole atmosphere working group co-chairs because they are both, I mean, internal ones, they're both Nick. So I'm not.
Nick squared.
I always have to ask who you're talking about.
Well, I think both Nicks are there because I see.
Yes, yeah, they are both there, both here now.
Oh, I'm going to run.
So if we will not have any questions and answers, they are going to be discussed, I mean, any further discussion at the working group meetings. So if you can stick with the 15-minute time slot, that'll be great.
Okay, I'm going to get some water. I'll be right back.
Okay. Elizabeth, do you want to put the thing up? Do you see the full slide or do you see the presenter mode?
I see presenter mode.
Elizabeth, they are seeing the presenter mode. Yes. So we are addressing that. That's the beauty of people being in this sort of club proximities.
Yeah.
Okay, so we'll get started and welcome back, everybody. So the afternoon session, at least the first part, well, first big chunk of it is going to be updates from the working groups. Each working group has 15 minutes, and we will not take any questions because most of these will be discussed, these highlights at the working group meetings or cross-working group meetings tomorrow. So I would like to request that all working group co-chairs stick with their 15-minute allocation. So our first speaker is going to be Julio Bachmeister, Atmospheric Model Working Group. Please go ahead, Julio.
Okay. I'd just like to thank my co-chairs listed on the first slide. And please advance. Yes. This is the outline. I will be talking fast, even though I'm neglecting lots of interesting work. First, I'm going to talk a little bit about our unified vertical resolution efforts. I'll talk about climate process teams, then some variable resolution work, and then a number of other topics that you'll see as we get to them. So please advance. First topic is our efforts to develop unified vertically, a single Wacom CAM configuration for climate and CMIP type simulations. This is an effort that's really being led by Isla Simpson of CAS, the Climate Analysis Section. Please advance. This is where we are. At our winter meeting, Isla presented results of a 80 kilometer top configuration, 81 levels, free tropospheric, lower stratospheric resolution of about 500 meters. And this, we're pretty happy with it. It has a decent QBO. The stratospheric zonal wind climate is okay. There's an issue with a dry bias that I'll mention I'll mention again at the end of this section. So since winter, what we've really been focusing on is developing a cheaper version, and this is all relative, of course, a cheaper version of the model for tropospheric physics development. And the starting point for this is 48 levels with a top at about 40 kilometers. In addition to the 48 starting levels, we've added 10 PBL levels. So you'll see the grid in a second. We encountered a number of problems getting to higher resolution in the boundary layer. There were some instabilities in the surface flux calculation with which were fixed with Bill Large's help. And there's always an issue with defining cloud-based properties in Zhang McFarlane, and Rich Neal has taken this on and will be showing results from this at his poster tomorrow, which I really encourage you to go to. So bottom line is that we now have a configuration that we're reasonably happy with. It's a 48 level plus 10 boundary layer levels additional. So that's a total of 58 levels with a modified ZM. So if you go to the next slide, this is the grid. I don't want to get into a lot of details. It's a complicated figure, but you can peruse it at your leisure when these slides are published. It just shows the various grids that that we're considering, or that we've more or less settled on, really. The 58 level cheaper configuration and the 91 level, that would be 91 levels, that would be 10 added to the 81 levels that we're happy with in the free troposphere and lower stratosphere. So please advance. As I mentioned, firing Zhang McFarlane from the lowest model level is always a problem. Rich Neal has developed, he's implemented some code that will take a dynamic average based on the PBL height diagnostic and calculate cloud-based levels from that. That's shown in the lowest two panels of each sort of super panel. What you see here are mean precipitation on top and standard deviation in the bottom. And what I really want to highlight here is that if you look at the bottom super panel, you'll see that in panel D, where all we've done is increase the number of levels in the PBL from panel C to panel D. That's the only change. That's really just kind of led to an explosive increase in variability and precipitation. Rich's mods, which as I mentioned again, as I will mention again, he'll discuss tomorrow. If Rich's mods have the ability to really reduce this variability explosion to reasonable levels. So sort of outlined in gold is what I'd call our current favorite configuration with PBL height determined cloud-based properties for Zhang McFarlane and a total of 58 levels in the atmosphere. So you'll see that the variability is reasonable in this configuration, and in fact the mean precipitation I'd say is improved over what we had in the old model, which is in panel B in the top group. So please switch. So the next steps, we need to reassess the climate variability and stratospheric variability in the, let's call it now the full unified model. That would be the 81 level configuration plus the 10 extra boundary layer levels, with Rich's modifications to Jean McFarlane. We have some outstanding mods for the spectral element dicore. I should mention that we are now we're now using the spectral element dicore for this development. We'll need some final tuning for climate, and I expect we'll be beginning coupled runs at some point before the next winter meeting. I certainly hope we'll have something to report then. And just to mention briefly, this is our water vapor problem. This is a plot from Rolando Garcia, and I just want to reassure the Wacom folks that we are not going to, we're not going to ignore this problem. As we increase vertical resolution, you see in this plot that cold point water vapor, goes down in the cold phase, or the wet phase, sorry, that would be the dry phase, the wet phase of the annual cycle. So this is an issue we're aware of, and it's one of the things we'll be trying to address in the next few months. So next slide, please. I'm going to briefly talk about the climate process teams. We have two within AMP. There's another CPT that I neglected to mention, which is very interesting, but just didn't have the time. It's a boundary layer land surface coupling CPT, which I hope we will report more on at the winter meeting. But so let's go on to our CPTs in AMP. One is boundary layer to deep convection, essentially implementing a mass flux model into our current implementation of CLUB. So this turns CLUB, this turns our boundary layer scheme based on CLUB into sort of a unified shallow convection, it can go deep, deep convection scheme. This is work being done at NCAR by Adam Harrington. The overall PI is Joao Teixeira, and Michael White at Naval Postgrad has originated this work. So please, next slide. This is a picture, and I encourage you to listen to Joao's presentation tomorrow on the CPT. This shows PDFs from an LES simulation compared with PDFs diagnosed by CLUB, and the dots are the point, the point PDFs of the mass flux flumes in CLUB MF. And the encouraging thing here is this nice agreement in the slope of the PDFs between the LES and the CLUB MF implementation. And again, tune in tomorrow for more details. So please go on. Our other CPT is momentum fluxes and momentum transport in the boundary layer. The work at NCAR is being done by Chris Cruz. Please advance. This plot shows a diurnal cycle of meridional winds over the southern Great Plains. Chris is beginning to look into processes here. You'll see that this is a run, it's sort of a boundary forest cam run, nudging everywhere except over the central US. And you'll see there's good agreement in the general pattern of the diurnal cycle, which probably is large-scale forcing, but there's significant disagreements in the location of maximum winds and in some of the details in the diurnal cycle. And this is the sort of thing that Chris will be looking at more. So please advance, I'm running out of time. We have variable resolution efforts, which will be discussed tomorrow in the SEMA section by Adam Harrington and Patrick Callahan. The really new effort here is the South America effort, which is joint with RAL at NCAR. We're going to be comparing high resolution cam runs with WRF, and you'll hear more about that tomorrow. And I also want to mention that there is a significant amount of regional refined work being discussed in the in the WACM CAM-CHEM session using the CONUS, the continental US grid. So please move on. So the last real topic I want to bring up are oscillations in low-level wind. This is something that probably has been in the model, at least at low amplitude, for a while. It becomes more pronounced in CAM SE and at high vertical resolution. What I've shown here are various examples of these oscillations. They occur in E3SM as well, as you can see as the sort of ugly speckles within the white ellipses. And on the left of the slide are points from Brazil from a run done by Adam Harrington, in which he's tried a number of things to solve the vertical oscillation problem, or sorry, the time step, the 2 delta T surface wind oscillation problem. And likely causes are that we have too large a physics time step, and it's combined with inconsistent winds and surface drag due to the process order in the physics. So please advance. Our Adams—
2 minutes, Julio.
2 minutes, I know. Adam's low touch solution is to reorder the time loop. He has, I think, correctly identified maybe the root cause as the fact that surface fluxes are being calculated in the time loop, the old time loop, which is on the left, after club. So there is an inconsistency in the winds being used by club and the surface drag in the model. And the oscillations are largely resolved by reordering the time step, as Adam has done on the right side of that panel. So that's one possible solution. We can increase a coupling frequency, which is expensive, certainly not viable for climate simulations, but maybe as a development strategy. Okay, so next slide, please. Software engineering update. In the interest of time, I just want to emphasize the bottom points. The Common Community Physics Package, CCPP, is well underway, and we will begin porting physics to this soon. So CCPP, a new infrastructure for structuring the time loop is on the way. Next slide, please. Other development, which will be discussed here mostly, enthalpy budgets by Peter. I'll let you read, but yeah, bottom line is tune in tomorrow. And so next slide, please. Other highlights that I want to really just quickly go over. FE3 is in CSM 2.2, and I want to welcome a new hire as part of our CAM7 funding. Yang Tian from Lawrence Livermore will be joining us, and she will be helping us integrate LES into our development process. So you can just put up the summary slide, next slide, and I'll stop talking.
Thank you very much, Julio. So we are going to move on to a whole atmosphere working group. I'm not sure which Nick is going first, so please go ahead.
Okay, I can go first. That'll make it easy. Hi, everyone. My name is Nick Davis. I'm one of the co-chairs along with Nick Peditella, the whole atmosphere working group. I also want to recognize our external co-chair, Jessica New from NASA JPL, and also Mike Mills, who's our liaison. Next slide, please. Okay, so we want to use this presentation to really present to you an overview of some of the last year's efforts on WACM and WACM-X, and in particular their transition to more adaptive whole atmosphere models. So I'm going to talk a little bit about how we've tried to reduce the complexity of the model to enable flexibility and broader use, how the comprehensive nature of WACM has been leveraged in the CSM2 Earth System Prediction Framework to study predictability and impacts. And then Nick is going to talk about how some aspects of increased complexity have allowed frontier science applications, including increasing the resolution of the model and coupling it to a magnetosphere to examine geospace variability. Next slide. So the first thing I want to talk about is the CSM2 Earth System Prediction Framework. I think this is something that's going to keep coming up at this workshop throughout the week, although it's probably worth attending the Thursday session in the Earth System Prediction Working Group, because there's I'm imagining going to be a greater discussion of it there. But essentially just echoing what Gökhan has already said, this is operating right now in essentially real time using WACM 6. It's got a prognostic atmosphere, ocean, sea ice, and land components that are initialized in some different ways. The database of hindcast output is now available at the Climate Data Gateway. Thank you to the team that has produced the hindcasts for doing that. That's going to enable, I think, a lot of greater community use. And like I said, the forecasts or the real-time predictions are occurring every Monday right now, although they paused because it's summer. And I should say that this is developed and maintained by Yaga and her team of experts on managing all these different components. Next slide. So lower cost configurations of WACM. WACM 6 is definitely one of the more expensive cases you can run when you're using comprehensive chemistry, where you have troposphere, stratosphere, mesosphere, lower thermosphere chemistry. At 1 degree horizontal resolution for an F case, it's 15,000 core hours per simulated year, plus or minus. And that's quite an increase over CESM2 or CESM1. So there are some truncated chemistry versions available, including middle atmosphere chemistry, which knocks you down to 8,000 core hours per simulated year at 1 degree horizontal resolution. And as it's been discussed at previous workshops, there's also a 2 degree configuration, which if you run with middle atmosphere chemistry is 3,000 core hours per simulated year, which gets you basically to the core hour cost of CESM1 WACM. So from CESM2, you can essentially, using middle atmosphere chemistry and a coarser horizontal resolution, get down to the core hours per simulated year that you used to have with the previous generation of CESM. And we're undertaking a rigorous analysis of the climate and the climate response of all 3 of these configurations to make sure that the community has a reference document to understand, when can we use middle atmosphere chemistry and when can we use 2 degree horizontal resolution. So on the right, I'm showing you from these 3 different configurations a pretty standard plot to assess equilibrium climate sensitivity from the abrupt 4 times CO2 simulations, basically showing you the relationship between global mean surface temperature and the net radiative imbalance at the top of the atmosphere. And all of these configurations in general have essentially the same climate sensitivity. And that seems to be the story even for the circulation responses. So from a climate perspective, these configurations are essentially equivalent. It's just obviously if you're wanting to model the troposphere, you do not want to use MA chemistry. The other set of external folks working on this analysis, some folks from Cornell University, including Daniel Visioni, are looking at this from a stratospheric aerosol perspective. And really the big differences are in terms of the background aerosols, with the comprehensive chemistry tending to have lower background aerosols. But during the sort of extreme events like volcanic eruptions, all of these configurations are comparable. So we're fairly confident that these low cost configurations of WACM are going to be useful for the community without incurring a big expense on the side of realism. Next slide, please. So I think Louise is going to talk next about probably this in much more detail than I will. And it's already been mentioned, Musica is this sort of comprehensive multi-scale configuration for chemistry modeling that's being developed currently at NCAR. And what I'm showing you on the right or on the left are contour plots at 30 hectopascals of the 1 hour high pass filtered U prime omega prime. So essentially the gravity wave momentum flux. And then I'm showing you on the bottom some transects at 90 west from south to north, and then at 30 north from east to west. And you can see these dotted curves on this plot are showing you transitions from our global 1 degree grid with the spectral element dicore to a 1/8 degree refined grid over the continental United States. And you can see pretty clearly that you go from essentially modeling very little high frequency variability In the transition zone, you're starting to model some very large scale waves. And then within CONUS, you're resolving a lot of small scale gravity waves. And so in this current setup where we have regional refinement in the spectral element dicore, we're entering this sort of gray zone of gravity waves where we're resolving some of them. So currently we're undertaking a project to assess the resolved dynamics and transport within this region, partly to inform parameterizations to understand how can we make the model a little bit more scale aware, but also to help us understand the fundamental transport and coupling between the surface and the lower atmosphere and the middle and upper atmosphere. And we are actually going to have a presentation on gravity wave aware chemistry in the joint whole atmosphere chemistry climate session. So I think, as we're moving to these more refined grids, it really is important to think about what we're resolving and how we need to take that into account. Next slide, please. Thank you. So one of the community projects that's going on right now that's being coordinated by Doug Kindison and Simone Tilms is some simulations for the WMO scientific assessment of ozone depletion. So I'll talk about these two plots separately because they're sort of slightly different projects and chapters. So on the left, this is showing you observations of total column ozone in the black. In blue is CMIP6 coupled simulations. Excuse me, in green, CMIP6 SSP245 simulations. And then in red, this is the new addition, is the REF-D2 simulation, which essentially is an updated emission profile that takes into account new and projected changes in halogens. And so essentially, from what you can see in this plot is that the REF-D2 simulation has a sort of delayed recovery of ozone. And right now it looks like, based on that emissions curves, total column ozone's recovery is delayed by 5 to 8 years to its pre-ozone hole values. On the right are some temperature curves from the SSP585 simulation in black, and then a set of simulations here, REF-D2 in green, and then several of these prescribed transient stratospheric sulfate distribution simulations in purple and red. And so essentially the idea is the sulfate is prescribed in the stratosphere in these purple and red curves to ensure that global mean surface temperature remains at a consistent value. So it's this feedback algorithm. And both of these simulations are going to appear in the WMO ozone depletion report. So we're going to have some presentations on aerosol schemes and also on an assessment of simulated stratospheric ozone in the joint session. Next slide. And this is also another set of projects related to climate interventions. There's going to be a presentation on this also in the joint session by Jager Richter, just showing that these are simulations for the ARISE SAI experiment. It's an ensemble of simulations. On the left is showing you the result of these geoengineering simulations and their response in CESM1, and on the right, CESM2. So there are some differences that have been introduced in the new version of the model, and Jager is going to talk more about that on Wednesday. Next slide.
You have about 4 minutes, Nick. So
in the few minutes that are left, I'll just give a brief overview of some of the activities more related to WACOM-X. So we've done some high resolution simulations in WACOM-X, which for a whole atmosphere model extending to 500 kilometers, half degree is actually fairly high resolution. And this is an example of the first time we've simulated equatorial plasma bubbles, which are these kind of striped depleted regions that you can see in the white circle. And this is through coupling WACOM-X at this half degree resolution with the NRL ionosphere model. And we can generate these large scale plasma depletions in the model on the left that are consistent in scale with what we see in the observations. So this is encouraging in terms of going forward. It's for high resolution modeling of all of geospace. Next slide, please. And those previous results were based on using the FE DICOR, which has some issues in terms of the going to higher resolution at the pole. So we've been working on the SE development in WACM-X. This required some modification to the DICOR to account for species-dependent in the thermosphere, and then also, as Julio mentioned earlier, development of a regridding scheme was implemented to transform between the SE coordinate system and the geomagnetic grid that's used for ionosphere electrodynamics. And on the right is an example of the difference we see. This is the temperature at around 400 kilometers during a geomagnetic storm, simulated in WACM-X with the FE DICOR at 1 degree resolution, and then the SE DICOR at also effectively 1 degree horizontal resolution. And you can see there's much more structuring in the SE DICOR because we don't need to implement an artificial sort of filtering at high latitudes because of the pole singularity. So we think we'll get a much better representation of the dynamics of ionosphere and thermosphere during geomagnetic storms. And in the SEMA session tomorrow, Kevin Pham will talk more about developments related to coupling with the SE DICOR to a magnetospheric model. Next slide, please. And last, one of the activities we've been working on is implementing new sources of data assimilation. And this is really so that we can look at, study the predictability of the near-Earth geospace environment by doing initialized predictions, and then also for looking at case studies by having a better constraint. And a lot of the recent work has been focused on assimilating new satellite mission data from Cosmic 2 and then the NASA Gold and Icon missions. And again, we're using this to look at essentially short-term forecasting of geospace environment. Next slide, please. And just as a summary, we'll have the joint session on Wednesday morning with the chemistry working group. And there will be more details there on a lot of what was discussed in this talk. And I think since we're out of time, I can just stop there and you can read kind of what's been going on and what's planned for the future.
Thank you very much, Nick and Nick. So we'll move on to Chemistry Climate Working Group, and Louisa Emmons will be providing the update.
Hi, everyone. I'd like to start by thanking my co-chair, Xiaohong Liu from Texas A&M, and Simona Tilmes as the liaison, and all of our development efforts really count on Francis Bitt for doing the software engineering. Next slide. So for those of you new to CESM, just a brief overview, the Chemistry Climate Working Group really focuses on developing the representation of gas phase and aerosol species in CESM and works on furthering our understanding of the interactions between chemistry, aerosols, and climate. And we look at the interactions with the whole Earth system and study the impacts of aerosols on climate, the precipitation and circulation, as well as looking at air quality across different scales. So in this talk, I'm going to present some of our aerosol and chemistry developments currently in the works, talk a little bit more about Musica that's been mentioned, and mention a model evaluation project. Next, please. So here are a few of the aerosol developments that we've been working on for some time and hope to get into CESM 2.3. There's a new dust emission scheme from Natalie Mahowald's group. There's also already currently in the ChemChem version an aerosol scavenging scheme for convective clouds, and we'll add that to the CAM and WACM comp sets. There's also, we're working on an updated scheme for the dry deposition of aerosols. And we have a new online DMS emissions scheme for from oceans that I'll say a bit more about in a second. And we are implementing the Karma sectional model, and Simona will talk about that on Wednesday morning in more detail. And we have a new addition to the modal aerosol model scheme, adding a stratospheric sulfate course mode. Next slide. Say a bit more about that in this slide. So it's adding on to MAM4 a stratospheric sulfate course mode. Texas A&M group has really been leading this effort. So in CESM 2.0 and up through 2.2, the course mode size range and standard deviation were modified as to better represent the sulfate aerosol in the stratosphere, particularly from eruptive volcanoes. But this inadvertently also modified the dust and sea salt sizes. And so MAM5 now adds a coarse sulfate mode for the volcanic aerosol and puts the dust and sea salt coarse mode sizes back to the original MAM4 design that was in CESM 1. So on the lower left here is the new MAM5, and the red line shows that it matches the stratospheric sulfate burden compared to satellite in the purple line. And it returns in the lower right here, we can see the CN concentrations, returns the stratospheric concentrations back to more appropriate levels than were in the blue original CESM2 case. Next slide. And so this is, we have a new capability for calculating DMS emissions from oceans. So there's the upper right here shows the climatology that we've been using that was from ocean biogeochemistry model. So it had monthly means that were just the same for all centuries that we ran. But the new scheme is called OASIS, Online Air-Sea Interface for Soluble Species. And it uses a climatology of seawater concentrations from the Atlantic climatology that's used by many groups. And so this is just a name list option already available in CESM 2.2. You just have to give it the appropriate input files. And the plot on the left here shows that in the blue, the new OASIS time series for global emissions, and it varies, with each time step based on the meteorology that's used to calculate the emission fluxes compared to the climatology. So the new scheme is a bit higher, particularly for most months of the year, and has as well as in higher in tropical and northern oceans than our old climatology. Next. So we have a few other aerosol and chemistry developments in progress, and hope to get these implemented as well soon. The Mosaic scheme, I'm sure you've heard us talk about, has been described and published based on its implementation in CESM 1, and we're moving it to CESM 2. And this is needed for simulating nitrate aerosols, the gas aerosol exchange scheme. And we are running some interactive fire simulations as a community project, and that will be discussed more in the fire session tomorrow afternoon. A couple groups have been working on online soil nitrogen emissions, which are calculated in CLM, but really needed for atmospheric chemistry, tied to the biogeochemistry and the land model. And Maria Valmartin and Anthony Wong will give talks on that work on Wednesday morning in the chemistry and WACM session. And several other things are ongoing. Megan emissions are being improved by Alex Gunther's group, particularly the impact of drought. An emissions handling module called HEMCO that's used by a number of models is being implemented by Harvard. And we're working on a new photolysis scheme that's calculated online that will replace the lookup table we've been using. And as always, there's additional chemistry being tested and evaluated, simpler versions and more complex versions. Next slide. So as it's already been mentioned today, Musica is the multi-scale infrastructure for chemistry and aerosols, and it's really a framework for further developing chemistry and aerosols in CESM and other models to really take into account the needs for simulating at different resolutions, from fine to global in a single configuration. And this is being developed in partnership with SEMA, the System for Integrated Modeling of the Atmosphere. So there's a paper describing the Musica vision in BAMS, published last fall by Gabby Pfister. And we really invite the whole community, anyone interested in atmospheric chemistry and aerosols, to be involved. We have a number of working groups already formed to look at particular aspects of the problem, chemical schemes, emissions, multi-scale physics, etc. So we are calling the first version, the 0th version of Musica, a configuration of CAM-CHEM with the spectral element dicore and regional refinement. And one of the grid we've started with is this CONUS grid with 1/8 of a degree resolution over the continental US and 1 degree for the rest of the globe. And this is a comp set in CESM 2.2. So it's available already to the community. Next. So these are some first results from these simulations, and Becky Schwantes, who's now at NOAA, and Forrest Lacey really led the preliminary first set of really testing and getting this version of the model running. And Becky's been looking particularly at the impact of both horizontal resolution and chemical complexity. So with finer resolution, we can much more accurately represent the emissions in the model. And these two plots show for two different chemical complexity schemes, the difference between the fine resolution and the coarse resolution for surface ozone in, I think it's August, and shows that over the all the urban areas show more concentrated ozone levels with the finer resolution than in the coarse resolution. And the results are fairly similar with the two different chemistry schemes. And the lower right here shows the change in the NOx emissions, showing that they're really concentrated, more concentrated in urban areas with the finer resolution. Next. And these two plots show the difference in the chemical complexity for the two different resolutions, showing that really the finer resolution shows a much stronger sensitivity to the chemical complexity. So to really improve our models and study the impact of new chemistry, we definitely need to use the finer resolution. And Forrest is giving a talk in the Wednesday morning session, looking at these simulations, particularly for their health impacts. Next. And several groups are now developing new grids for Musica version 0. So as part of, in support of the ACLIP experiment, which will be an aircraft experiment next year over, based in Korea, to look at the outflow from the Asian monsoon, this grid with a 1/4 degree resolution over all of South and East Asia is being used to study the role of the Asian summer monsoon originating over South Asia, includes an anticyclone over the Tibetan Plateau, and can show the shedding, the outflow of the monsoon over the West Pacific region. And a graduate student at the University of Iowa is developing this 8th degree grid over North India to look at air quality and in that region. And Dusong Zhou, an ASP postdoc, is has created a 1/16 grid over South Korea to look at air pollution there, and he has a talk on Wednesday discussing that person. Next. And finally, we have we're to really help out the community. We're setting up a community simulation where we'll save monthly restart files, and this should really help users to have the chemistry, atmosphere, and land initial conditions that they need to do simulations for the CONUS grid or for any other regionally refined grid they want. So we're doing the simulation running it from 2010 to 2020 and with monthly restarts. So hopefully users will not have to run a long time with their own spin up. And we'll post more instructions on the information about that on the Musica wiki page. Next slide. And a project I'm leading is developing a framework for facilitating model and observation comparisons, and to take into account all the different structure of atmospheric chemistry observations, and to compare to different model grids, regular grid or the unstructured grid, and match them up and do analysis and evaluation of the model, as well as further understand the observations. And will be written in Python and building on Monet tool that has been started by NOAA. And we're connecting with the other activities for model and climate evaluation in NCAR, the CAM diagnostics, and the JEDI program for data assimilation. Next slide. So I'll just end saying our session is on Wednesday morning, and we have a few web pages for more information. Thanks.
Thank you very much, Louisa. We'll move on to Ocean Model Working Group, and Frank Bryan will be presenting. I think we may need to switch slides, right?
Yes.
Almost there.
While we're waiting, I'll just say I'm presenting for the Ocean Working Group along with my co-chair, Ian Grooms from the University of Colorado. And this
is the wrong one.
Well, maybe earlier. This is
earlier, yeah. You have to go earlier, Elizabeth.
And I also want to acknowledge the capable and critical contributions of the Ocean Working Group liaisons, Gustavo Marquez and Alvaro Tuntis. We're in presenter view.
Yeah, we are in the presenter mode, Elizabeth.
Go up to the top, display settings.
Yeah.
Okay, go ahead to the next slide. Next slide, please. There we go. So as many of you know, development of the POP ocean component model that's been used in CCSM and CESM for the last 20 or so years has ceased, and we will be moving to a new ocean component model with CESM 3. And I'm going to spend the first part of this presentation describing where we are with our MOM6 configuration and what will likely be the basis for the CESM 3 ocean component model, and here contrasting it with what the current version of POP has. So we're going to somewhat higher horizontal resolution, but still in the eddy parameterized regime, so about 2/3 of a degree resolution. A distinguishing feature of the MOM6 model is a very flexible, what is referred to as arbitrary Lagrangian Eulerian algorithm for representing the vertical coordinate. And we're currently exploring two alternative representations, a level-like coordinate that is similar to POP, and a hybrid level isopycnal coordinate that I'll describe in a little more detail in the next slides. In either of those, with higher vertical resolution near the sea surface and somewhat higher number of levels in any of these alternatives. Another distinguishing characteristic of MOM6 as contrasted with POP is that we will have what is referred to as a natural boundary condition on fresh water. That is, the ocean model will exchange mass of water with the other components of the hydrologic cycle, in contrast to POP, which was a constant volume model, so that when it received a water flux, it did not actually add that mass of water to the ocean, but rather removed or added salt in order to affect the same change in salinity. So that is an important distinction that I'll come back to towards the end. The vertical the representation of vertical mixing processes are still at this point quite similar, with a K-profile parameterization based diapycnal physics. POP had a representation of the wave effects in driving Langmuir circulations and their effect on boundary layer physics. We are currently in the process of re-examining the representation of wave processes in the ocean and the interaction of wind waves with surface boundary layer processes. I'll also come back to that in a second. The representation of horizontal stirring and mixing by mesoscale eddies is also quite different in MOM6. It is based on the Gent-McWilliams-Reddy type formalism, but the evaluation of the diffusivity is based on a diagnostic of the unresolved mesoscale eddy kinetic energy. This is sort of a TKE kind of scheme, if you know that terminology from boundary layer physics. And in addition, we have a backscatter scheme so that some of the available potential energy removed from the mean potential energy state by the Gent-McWilliams parameterization is returned to the mean kinetic energy, representing the upscale transfer of energy through the baroclinic instability process. The viscosities in MOM6 are also tied in with this mesoscale eddy kinetic energy and scaling spatially with those. These EKE-based schemes we feel will be much more scale adaptive than the current representations in POP. There's a slightly different representation of the transfer of solar radiation in the upper ocean. The scheme we had been using in POP is ill-suited to vertical resolutions below about 2 meters, and we're pushing that limit now, so we've moved to a different scheme, which we feel would be more accurate in the near surface layers. The numerics in MOM6 are quite a bit more accurate in terms of being monotonic in the horizontal advection. The AL algorithm basically replaces vertical advection with a remapping, and that is, we are exploring different interpolation order schemes in that as well. There are a number of other parameterizations in POP that we are still exploring the best way to go forward on. For example, overflows that are parameterized in POP are very much tied to the particular representation of topography in the vertical grid in POP and would not be suited to MOM6 numerics. So we're looking at different ways to move forward on those. Similarly, the story box model will require some rethinking on how that interfaces with the GCM. The coupling API, we have both MCT, the older MCT, and the newer NUOPSI caps and interface to the coupler working. The bottom line is that the version of MOM6 we're currently working with would be about we're estimating 5 to 8 times more expensive than the current version of the POP workhorse model. A factor of 2 there is just accounting for the additional 2 to 2.5, accounting for the additional number of grid points and the rest of that factor accounting for additional algorithmic complexity. Next slide, please. So I'll show a few more slides comparing some of these different alternatives we've been exploring in terms of the vertical representation. Two cases with a level-like coordinate with either 65 layers, which is roughly similar to what POP has, and 75 layers. And then two schemes with this hybrid level isopycnal scheme, again, somewhat higher resolution. All of those cases have identical physical parameterizations. In addition, on some of these plots, I'll have results from another case using the vertical grid from the HICOM community, that's basically used in the US Navy's operational forecasting system, and from the OM4 model at GFDL. Next slide, please. So here's just a slide to show you how these different grids represent the vertical structure of the ocean. On the right are cross sections through the Western Equatorial Pacific warm pool from, I guess it's 30 south to 30 north at 165 east. And the gray lines here are the grid coordinate surfaces. So you can see the level coordinates, as you would expect, constant across the section, whereas these hybrid schemes, they're set up to have level coordinates near the sea surface in order to represent the mixed layer well, where the density is vertically uniform. And then once you enter the stratified interior to transition to an isopycnal coordinate, along which the properties have weaker gradients, so that dispersion and diffusion errors in any advection scheme will be more similar to a physical mixing process than if these were level coordinates. So basically the idea is to reduce the amount of spurious diapycnal mixing in the stratified interior of the ocean. The trick here is to come up with recipes for prescribing this transition between the level coordinate regime near the surface and the isopycnal coordinate regime in the interior. And here, for example, at the bottom, you can see very different choices between the GFDL OM4 case, which pushes the level coordinate regime up very close to the surface, whereas the Navy configuration pushes it quite a bit deeper. And we've been exploring different versions sort of in between these two limits. This just shows you the grid spacing in the vertical on the equator at 165 east, so right in here. And you can see that there, especially as you just below the base of the mixed layer, it can be very difficult to retain the representation of the fine vertical scales in this transition layer. So this is still something we're continuing to explore. Next slide, please. So here's just a few very high level planetary scale metrics of the differences that arise with these different choices in vertical grid. So you can see here's the global mean temperature drift. You can see they're opposite signs for the Z star versus the hybrid, with quite a bit lower drift in the hybrid coordinate cases. In the middle panel is the strength of the Atlantic meridional overturning circulation compared to the rapid array estimates in black. You can see the hybrid coordinate versions are staying closer to the observations, at least through the upper ocean, although both models are struggling to represent the very deepest Antarctic bottom water cell. And then in the upper right, the Atlantic meridional heat transport. And again, the hybrid coordinate model versions are coming closer to the observational estimates in the Z star at this point in time. Next slide, please. And here is just a comparison of the sea surface, the mean sea surface temperature error the bias across different versions of the model. You probably can't read the numbers here, but in fact, the RMS errors are quite close, within a few hundredths of a degree of each other. And many of the large biases are seen across all these model versions, and they're just endemic to models at this horizontal resolution, such as Western boundary current separation issues. There are more subtle and important differences in the tropics and subtropics and places like the Jin Sea across these versions that we'll be continuing to explore. Next slide, please. So in addition to this workhorse model that will become standard in CESM3, we're pursuing capabilities in CESM with MOM6 at different resolutions and in different configurations. So for example, we have versions configured running in aquaplanet configurations with a fully dynamic ocean model. This is work led by Jianing Wu from Stony Brook University. We have a near full aquaplanet, has small polar continents at each pole because of grid singularities, and a version with a single 1 grid point wide continent that can support zonal pressure gradients and western boundary currents. Jianing's paper looks at the differences in the climate in on those two different planets. This is part of the effort in developing a model hierarchy capabilities within CESM, and Alper Altuntas will be speaking to this on Wednesday in the software engineering working group. We also have a high resolution version of MOM6 running in the CESM context. This version is running on the same 1/10 of a degree grid as we have been running POP for a number of years, and is currently being used in the IHSP project that Gokhan mentioned this morning. And this is a surface eddy kinetic energy, and you can see that the MOM6 solution is very closely reproducing the energetics and mesoscale dynamics as we've seen in POP, and is a viable replacement at that resolution as well.
1 minute, Frank.
Okay, and also a regional downscaling capability, something we've never had in POP. We've had efforts to provide regional downscaling in other other ocean models, for example, ROMS. We now have this capability basically to support regional downscaling out of the same code base as our global model, which we think is a much more sustainable situation. Next slide, please. Near term, as I mentioned earlier, MOM6 is a natural boundary condition model. We are exchanging mass with other components of the system, and that mass carries enthalpy or internal energy that has not previously been accounted for in the CESM system. So we need to revise the coupling and other components to account for that aspect of the energetics. Peter Laritzen will be speaking to that point on Tuesday morning. There's a strong effort within the Ocean Working Group to bring in more comprehensive treatment of wind waves in the Earth system, both in terms of their interaction with ocean physics, as well as a component of the environment that impacts human activity. And finally, we have a strong involvement in the current oceans climate process team, which is looking at energetics-based eddy parameterizations, including machine learning methods. There'll be a talk on that by Lorzana in the mixed layer cross working group meeting, I believe, on Thursday. Next slide. And just leave it there with some resources. As Gokhan mentioned, you can run MOM6 right now from CESM 2.2. There's expanding documentation that we're developing alongside the rest of the MOM6 community. And to learn more about MOM6, we have an 8-part webinar tutorial series that was broadcast last summer and winter. So that's it.
Thank you, Frank. That's the machine learning session, not the mixed layer.
Yeah, right.
Okay. So our next speaker is Keith Lindsay. He'll be giving an update on biogeochemistry working group activities. Keith?
Thank you, Kokon. I'm presenting this material on behalf of my co-chairs, Gretchen Keppel-Alex at the University of Michigan and Abby Swan at the University of Washington. One of the highest profile activities of the BGC working group is a configuration of CESM with a coupled carbon cycle, where the carbon cycle is coupled through the different components and also to the radiation code in the atmosphere. And so I'm going to start off by showing some results of the coupled carbon cycle in CESM2 that was submitted to CMIP 6. Next slide, please. So this is the modeled surface CO2 in the ESM HIST experiments. This is a prognostic tracer in the atmospheric model where it's being conservatively transported by CAM, and there are surface fluxes in the land and the ocean and fossil fuel emissions. In the top panel, we're just looking at a globally averaged surface CO2 concentrations in these ESM HIST experiments. The thick black line is the observed global average, which is used in the prescribed CO2 concentration runs that most people are probably more familiar with. There's a dashed line, which is the concentrations from CESM1 with the BGC turned on. And then there's a couple of lines, which are two different ensemble members from CESM2. And the top panel is the model and observations, and the bottom panel is model minus observations. There's a few things going on here. One is that because of the spin-up procedure, we ended up having slightly elevated CO2 in the pre-industrial control run. So back in 1850, the CESM2 runs were a few ppm high compared to observations, and that bias persisted for into the middle of the 20th century. Both versions of the model show an increase in bias over the mid 20th century, and this is common to all CMIP coupled carbon cycle models. That in a lot of work has been done, it really hasn't been tracked down why the coupled carbon cycle models are not able to reproduce the growth of atmospheric CO2 over the mid 20th century. A key thing that's going on in the latter part of the 20th century is CESM2, the bias is flat. We are 15 ppm too high, but the growth rate is very similar to the observed growth rate, and that is in contrast to CESM1, where the growth rate was considerably higher than observed. And so this is an improvement, a notable improvement of CESM2 over CESM1 is primarily due to improvements in the land model. Next slide, please. Another aspect that we look at in the carbon cycle models is the seasonal cycle of atmospheric CO2 at the surface. And a notable place where the seasonal cycle has very large amplitude is well observed is at Barrow, Alaska. Here we've got the same coloring scheme as the previous slide, where the thick black line is the observed seasonal cycle over a latter part of the 20th century. And in CESM1, the seasonal cycle was weak compared to observations, and in CESM2, we are much closer to observations. Though we're a little bit out of phase, but there's a substantial improvement compared to CESM1, and the amplitude is much better. And then if we look at that amplitude as a function of time, you can see in the bottom panel, CESM2 is doing a much better job compared to observations than CESM1 was doing. Next slide, please. But there's still room for improvement. That was at Point Barrow, up in close to the Arctic Circle. If we look at the similar sort of diagnostic at Mauna Loa, Hawaii, which is measuring sort of free troposphere concentrations of atmospheric CO2, you can see that the model has improved from CESM1 to CESM2, but in that free troposphere, we still have a ways to go in terms of getting the amplitude correct compared to the observed amplitude of the seasonal cycle. This is an ongoing work to determine the discrepancy between the model and the observations. in separating it between surface fluxes in transport of atmospheric CO2 anomalies out of the boundary layer. Ongoing work to figure out which of those are contributing more to this bias. Next slide, please. Thank you. Looking more closely at surface fluxes of CO2, I should say that the previous figures were from paper and prep by myself. And this is from a paper, actually I should have updated this slide. This is no longer in prep, this is submitted by Long et al. And this is looking at the air sea CO2 flux in the latter part of the 20th century and comparing to a neural network fill of sparse observations of PCO2 and CO2 fluxes in the surface ocean. And in the left column is looking at maps of the annual mean surface flux, and the model is doing a decent job of reproducing the main structure that is observed. And in the other panels, we're looking at the seasonal cycle of the zonal means. You can similarly see that the model is doing a good job of capturing the patterns in seasonal cycle that are observed and reproduced and simulated in the neural network. And the zonal average across all months is then plotted in this final column, and the model is doing a decent job of reproducing the meridional structure of the air sea CO2 flux in this latter part of the 20th century. If you notice carefully in this leftmost panel, these numbers of the global integrals, this is not really an apples to apples comparison because of the different treatment of riverine fluxes and sediment carbon burial in these two different products. And so if you take those into account, the model looks better than you might think compared by seeing this, besides seeing the discrepancy in those numbers. It's a little tricky to compare observations of this neural network to the model when you're looking at the global integral because of the way different terms are treated differently. Next slide, please. Changing gears a little bit is in looking at how the carbon cycle feeds back into the rest of the system. This is some work from Claire Zarakis. I'm not sorry if I'm mispronouncing Claire's name, at the University of Washington. Claire is looked at in CMIP6 models and also CMIP5 models, how the physiological change in plants to rising CO2 generates air temperature changes besides the radiative effects of rising CO2. So in the top panel, top on the right, is the air surface temperature change in the multi-model CMIP model from warming at 2x CO2 that is purely due to physiological contributions. So this was achieved with a idealized experiment where the land and ocean models see this increased CO2, but the radiation code does not. And so we see warming going on, even though the radiative CO2 is getting the pre-industrial value. And if you look at the percent of that warming compared to what happens when the radiation code gets, you see that it's a non-trivial percentage. You see significant portions of the globe are 20% of the warming is due to physiological response from the land model. And this is happening by the CO2 fluxes impacting the hydrologic cycle and the water fluxes out of the plants and leading to changes in water vapor and cloud distributions in the atmosphere. And if you look in the left panel, you see that CESM1 was sort of in the middle of the pack, and it looks like CESM2 is a stronger impact, but this analysis has some complications from increased decadal variability that's present in CESM2 compared to CESM1. So this work of Claire's is really showing that what happens in the carbon cycle doesn't stay in the carbon cycle, and the importance of the land model to climate, besides things just like albedo that most people would be familiar with. Next slide, please. Some additional work that is going on with the carbon cycle is looking at the predictability of the carbon cycle from the DPLE. So this is going back a generation of the model to the lens era version of CESM2. And this is from Nikki Lovendusky's group. And what Nikki's analysis is showing is that when we look at the potential predictability of air sea CO2 fluxes in the DPLE, we see a very, and this is global averages, a very strong correlation between globally integrated air sea CO2 fluxes and what we get in a forced standalone model. The reconstruction is what these figures are referring to as in that forced standalone model. And the potential predictability is showing that the model is doing a very good job of, the coupled model is doing a very good job of reproducing the forced response that we get in the ocean ice simulation in that reconstruction. We're not able to capture what's going on in this observational product, which is the same neural network that was the results in the Long et al. Paper. And there's ongoing work to try to understand the mismatches of the potential predictability and the predictive skill that we are not able to achieve with this version of the model. Next slide, please. I'll just give a brief overview of some other ongoing activities as I'm starting to run out of time here. There's some core model development that is going on that impacts everyone using the carbon cycle, particularly the ocean carbon cycle. As Frank mentioned in the previous slides, CESM is transitioning to MOM6 for CESM3, and we're working on coupling the ocean biogeochemistry module, MARBLE, to MOM6. This is Mike Levy is handling a lot of the software engineering of this work, of the plumbing of the MARBLE code to MOM6. And there's a lot of details that are being worked out between the passing the data fields and diagnostics and a number of units that are different as we're moving from a CGS model to an MKS model, which makes life fun. There's also scientific challenges as we switch to MOM6 of working to accommodate a time varying vertical grid that has potentially very thin layers. And this is applying MARBLE in situations of vertical grids that we previously haven't exposed it to with our previous simulations with POP. And we're needing to do some scientific improvement to be able to accommodate that. There's a whole slate of PI-initiated science, and I'm going to have mostly ocean-focused stuff that I'm mentioning here. There's a group across different institutions working on a more elaborate plankton functional group scheme for the ocean BGC, having more phytoplankton groups and grazing groups. There's work going on at UC Irvine on improving the sinking particle dynamics by using more recent observations. We're coupling the ocean BGC model offline to higher trophic levels, for particularly looking at fishery models. There's continued work going on fast spin-up techniques, extending it to the full BGC model, and also extending it to MOM, so that as we transition to MOM6. And I'll mention stuff that was presented at the Paleo working group meeting previously this summer of coupling ocean BGC to a prognostic sediment model. And there's the Burn group is doing work with coupled carbon isotopes, which is a step beyond just looking at the carbon-12. I think that's my last slide.
Right, that was the last. Thank you very much, Keith. So our last speaker before the break is Bill Wider, and he'll provide an update on Land Model Working Group. Thank you, Bill.
Yep, thanks, Gökhan, and thanks, Keith. It's nice to hear that the land model is important in doing things well. But I'd like to give you an update on behalf of me and Rosie Fisher, who's the new co-chair of the Land Model Working Group, who stepped in for Charlie Coven, who's still involved in the CESM effort. But next slide, please. And There we go. So I'd like to start with a few research highlights, and there's obviously too much to go into much detail on this slide, but these are kind of the list of accomplishments that we've made in CTSM 5.1 relative to CLM 5. And I'll highlight a few of these in the upcoming slides, but the one that I kind of want to highlight here is the WRF CTSM beta tag that was released by Dave Lawrence and the rest of the CTS team, which is allowing the land model to also be used for weather research and forecasting. Next slide, please. And so one of the new features that's in CTSM 5 is a biomass heat storage parameterization that Sean Swenson put together. And this is just showing in offline simulations that CTSM 5.1 is cooler relative to CLM 5. And these are offline, so they're forced with a data atmosphere. But if you go to the next slide, we've just started looking at the impacts of these changes on coupled simulations. And so this is from an FComp set that Keith Lindsay ran. And kind of the take-home message here is that adding this biomass heat storage term is reducing temperature due to energy being used to warm up the biomass. So you see that at nighttime in the top panel, especially in the tropics, which are warmer at night with the biomass heat storage feature on. And then during the day, because that biomass is storing energy, it takes longer to warm up the northern hemisphere, which leads to a change in the diurnal temperature range shown in the bottom panel. So there's a lot that we still need to kind of investigate here, and especially for the coupled model. But for this audience, it seems relevant to know that CTSM 5.1 is cooler than CLM 5 was. And it's because of this biomass heat storage term. And there's another feature of Sean's development was to remove the stability cap that was in the old parameterization of CLM 5. And so we need to kind of dive in to see how this plays out regionally and at different times of the year, both at seasonal timescales and at diurnal timescales. Next slide. This was just a fun way to get Keanu Reeves up on the CLM, to let you know what's going on with CLM, but CTSM 5.1 also has the matrix, which is a semi-analytical spin-up approximation developed by Chris Liu and Yichi Luo, who will present a poster tomorrow afternoon. But the big gain for us is that spin-up is roughly 5 times faster for especially high latitude carbon and nitrogen pools. So you were using that moving forward in some of the future directions that I'll be talking about. Next slide. And really none of these developments could have happened without really having a really great software engineering team. So I wanted to just give a shout out to both the CTSM and FATE's software engineering crew, because being away for a year and a half or a year and some months we've still managed to be quite productive. So thanks everyone on this page. Go ahead to the next slide. And then I want to spend the rest of the time today talking about some of our ongoing efforts. So next slide. And a big one of those is being led by Dave Lawrence, and is kind of motivated by some work that Gordon has been doing. So this is a figure from a paper of Gordon's from a few years ago, showing that model uncertainty is really the biggest piece of land carbon cycle uncertainty. And sorry, Elizabeth, I forgot to take out all the animations, so you can advance a few here now. And so we know that CLM 5 is different than previous versions of the model, but go ahead and advance again. The question then is this related to different parameter choices that we used for CLM 5, or structural uncertainty in the way that we're solving equations in the land model? You can move to the next. And so the goal of this parameter perturbation ensemble are to complete a comprehensive parameter uncertainty assessment and calibration of the full CTSM BGC model. And a big piece of that is developing the infrastructure that kind of makes the PPE possible, and then to start exploring the sensitivity of different components of the land model, both in land only and in coupled simulations. And so, like I said, Dave Lawrence is kind of spearheading this along with Daniel Kennedy and Katie Dagan. Next slide, please. And you can advance one more, Elizabeth. And so the first 2 phases of this are done. The infrastructure development was pretty involved And our hope is that other components of CESM will be able to use some of this infrastructure to explore parameter sensitivity in their own individual components. And so that involves identifying parameters, extracting all of those parameters onto a parameter file, and identifying reasonable ranges for those. We're also doing this by creating a sparse grid. So we're not representing all points, but just a subset of points, and then developing a scripting infrastructure to kind of efficiently move through the PPE. And then phase one is this one at a time parameter ensemble, looking at a range of environmental perturbations, and this is now done. And Daniel's been able to check for reasonableness of the simulations by looking at things like survival and GPP, and then rerun the simulations when he needs to with new parameter ranges. So we'll start moving into phase 2 and 3, probably starting this fall. And the plot that's below is just showing that we can look at things like the mean effect of different parameters on quantities of interest here, plant productivity, as well as their effect on interannual variability, which is something that the Land Model Working Group is starting to pay more and more attention to. So you can go ahead and go to the next slide. So in addition to the parameter perturbation experiment, Meg Fowler is doing quite a bit of work with SCAM, which is the simple column model. And the kind of new capabilities here are enabling to run SCAM with a CTSM restart or initial conditions file. And so we're starting to have discussions about using both the coupled model and then potentially SCAM with the PPE to start really investigating how changes in the land model parameterization affect the atmosphere. Go ahead to the next slide. There's a lot of developments going on with CTSM and FATES, and so many of those have FATES as the functionally assembled terrestrial ecosystem simulator. And so a lot of those developments have to do with developing more complexity. So Jackie Schumann, Charlie Coven, software engineers, Greg and Ryan, as well as Adriana, who's going to be a new project scientist, joining NCAR, I think in August, looking at effects of fire, nutrients, crown damage, plant hydraulic stress, and land management, kind of ways that we can more realistically represent ecosystems and ecosystem processes and their recovery from disturbance. And then much of the work that Rosie Fisher is doing is then coming up with ways to back out some of that complexity. And so what's shown in the diagram here is her kind of schematic of how you would put together a satellite phenology mode where you kind of turn off many of the features that are in FATES and are able to compare the FATES representation in an SP simulation to the big leaf simulation that we're getting currently now with CTSM 5.1. And so these reduced complexity modes should help us kind of both accelerate the FATES development and understand how different features in FATES are affecting both land-only and coupled simulations. Next slide, please. You can advance a few here, thanks. So Sean Swenson's also working on the representative hill slope model in CTSM, and the motivation here is to start thinking about how explicit lateral flow within a grid cell works, and also thinking about downscaled meteorology, which affects things both like the incoming solar radiation on north versus south-facing hill slopes, as well as the partitioning of precipitation with elevation. So you get both more precipitation and more snow at higher elevations than you would at lower elevations. And the next slide, please. And Sean's having some promising results. What's shown on the left set of panels here are 16 representative grid cells for both lowland and lowland sites, and then upland sites with different aspects. As opposed to running a model in super high resolution, running it with this representative hill slope lets you map what's happening in these kind of idealized upland and lowlands and north and south facing slopes to what's happening in a grid cell. And so then what's shown on the right is how you could map those grid cells on the hill slopes onto a representative grid cell and look at how things like elevation and aspect affect things like snow at a single grid cell and then across. Sean's been working mostly in the Western US right now. Next slide, please. Bin Pang and Danica Lombardazzi have been working to develop the CTSM crop model. And so what's shown in the top row in red is what's happening now with the crop model in CLM. And then what's shown in the middle is this what the plan is for the revised CLM AgSys crop model. And aside from having much more complexity in the model and many more phenological stages, the key features here are our ability to look at different forms of crop failure, especially from heat stress, water stress, nitrogen limitation, frozen soils, all kinds of kind of more realistic ways of representing kind of how extreme events can negatively affect crop harvest moving forward. So that's a future development for CTSM 5.2 and beyond. Next slide, please. And then finally, some work that we're doing as part of an NCAR NEON collaboration is developing a simple containerized cloud-based system to take NEON data and CLM simulations, single point CLM simulations. And so a team at NEON and a team at NCAR, including Gordon, Donica, me, Jim Edwards, Brian Dobbins, and I neglect to put Negan's name on here, but Negan's been critical in this, is working to take NEON data, gap fill it, develop the parameterization for site characteristics to then run CLM. And all of this is going to be put into CLM Lab. So Brian Dobbins is involved, and the aim here is to have a containerized, a containerized way to do these single point simulations and share the results relatively efficiently. So we'll be talking more about this at the Land Model Working Group tomorrow. You can go to the next slide, please. And then I'll just finish with this kind of a quick look at the things that are planned for CTSM 5.2 and beyond. And again, many of these activities will be discussed more at the Land Model Working Group tomorrow morning.
Thank you, Will.
Yep.
We're actually right on time, 2:30 local time. So we'll take a 20-minute break and we'll be back at 2:50 Mountain Time, or 14:50 for the Europeans, if there's anybody out there from Europe. And we'll start with the polar climate at that time. Thank you again. So we'll start in about a minute. So again, a reminder, please stick with your 15-minute allocated time for the co-chairs. I don't see the screen yet, Elizabeth. Nothing is showing up. Okay, technical difficulties have been resolved. So we'll continue with the Paleoclimate Working Group, and Hansi Singh will be presenting on behalf of the working group. Please go ahead, Hansi.
Thank you, Gökhan. So I'll be presenting the update for the Paleoclimate Working Group on behalf of myself and my fellow co-chair, Marika Holland, and our CEIS Consortium liaison, David Bailey. And before I begin, I'm presenting from the University of Victoria, which is located on the unceded territory of the Lekwungen people. And next, please. Oops. Am I supposed to advance my slides? I don't think I can.
We are advancing. So, Elizabeth, is there a problem?
Ah, there we go.
Okay.
Okay, yes. And so before I begin, I'd like to also acknowledge that Black lives still matter and that it is Pride Month. So I'm hoping that everyone is having a good Pride Month. And also this is all in the spirit of inclusion and equity in the geosciences going forward, as well as the lovely climate justice talk that we had this morning. Okay, so to begin, I'd like to just go over some priorities of our working group and what I will be presenting today. So to begin, I'd like to be saying something about CEIS 6 in the CESM2. Next, please. I'll be saying something about integrating models and observations through Mosaic, the big field campaign in the Arctic. Next, please. And then I'll be saying something about our particular science priorities and talking about what different parts of our working group are currently undertaking. Next, please. So the really exciting thing is that CEIS 6 is now finally in CESM2. So this is like super exciting. So Dave Bailey is responsible for this. So it's pretty awesome that he's been working so hard at this. And evidence that this is indeed working is available here. So on the left figure here, you see the Northern Hemisphere sea ice extent. On the right is the Southern Hemisphere sea ice extent. And the blue shows the new CEIS 6 incorporated into CESM2. So super exciting. And you can see, you know, it looks a little bit unremarkable because it looks very similar to CEIS 5, but it's actually a pretty different model, or there's lots of new bells and whistles, which I'll be explaining in a second. Next, please. And here I show differences in sea ice thickness. I've been told by Dave not to read too much into these. So these are the difference between CESM2 with CEIS 6 versus CESM2 with CEIS 5. So, you know, you'll have to wait for a little bit to get some more updates on perhaps how CEIS 6 differs in terms of its climatology from CEIS 5. Next, please. So what's in CEIS 6? Well, we have the CEIS Consortium to thank for all of their model developments here. Next, please. So the first thing that we have is landfast sea ice. Next, please. We have coupling to MOM rather than POP. So this is what Frank Bryan has been presenting earlier in the Ocean Model Working Group presentation. So this is pretty crucial for getting CEIS to be compatible with the new CESM3, which is currently in development. Next, please. There is now a flow size distribution. Shout out to Letty Roach for her development of this for CEIS. Next, please. And then the really exciting thing is that now the physics and the dynamical core in CEIS are separate. So IcePack is the sea ice thermodynamic plus redistribution column model. You can run this independently of the dynamics, which is very cool. And the other neat thing, next please, is that there is now modularity. So basically what this means is that you can mix and match physics and dynamical cores and answer all of your burning science and practical questions about how sea ice works. Next, please. So the next area that I'm going to talk about is integrating models and observations. Here is the Mosaic icebreaker, just amazing sets of observations that have happened over about a year as this icebreaker sat in the Arctic with a collection of the scientists in the middle of a global pandemic. So pretty amazing that they still managed to do that. Next, please. And so what we would like to do is we would like to integrate these observations with models. Next, please. And so, in fact, some earlier work by Alice Duvivier actually sort of helped in terms of understanding what the trajectory of such an icebreaker would be. So these little tiny lines that you see here over the Arctic, these are a couple of different types of trajectories, one where there's only seasonal sea ice on the left, one where there's perennial sea ice. You can see that the trajectories look pretty different, as you can imagine. And so, you know, we can use models to help make observing easier. Next, please. But we would also now like to take these amazing observations made in Mosaic and put them in our models. So one area of potential interest is the spectral albedo of ponded ice. And it turns out that there's light melt ponds and there's dark melt ponds, and that these have pretty different albedos in the visible. Next, please. So on the top here, you see a light melt pond. On the bottom, you see a dark melt pond. And you might think, oh, that one on the bottom is deeper, but it's not. The reason why the light melt pond and the dark melt pond have very different albedos is actually because of the spectral characteristics of the underlying sea ice. So pretty cool and probably important to get this right in your model so that you properly capture meltout. Next, please. And so these pond albedos, since they are highly variable, they're a key target for model improvement in the near future. So shout out to Maddie Smith and Bonnie Light for this data from the University of Washington. Next, please. So another area is involving snow heterogeneity. So here is a measurement on the left showing a 200 by 200 meter field where we are looking at the surface topography of the sea ice using LIDAR. And then on the right, what we see is the difference between a future time and the present time. And the only difference here is that there's been a snowfall event. So instead of the snowfall event just kind of uniformly coating the ice, we see that it is indeed coating the ice very particularly on areas that are ridged. And this is because of winds. So essentially we get a redistribution of snow from level ice to ridges. So thanks to David Clemens Seawolf from Dartmouth for providing this data to us. And this is another area that we have targeted for improvement among others. Next, please. So now I'd like to go over some research priorities of our working group and different folks that are working on these different priorities. So first of all, one area of priority is prediction, predictability, and reanalyses. So on the left here, I show the potential predictability in CESM from Holland et al. 2019. This is over 6 time periods. And what we see is that the potential initial value predictability sort of has a sweet spot around the 2010s where it was sort of at its maximum, and that it is less before that time period and less after that time period. And it turns out that this is actually because of a confluence of factors that have to do with a balance between ice meltout versus thickness sensitivity of meltout. So anyway, there is a lot of initial state dependence in sea ice predictability, and this is an area that one can use perfect model experiments to understand. And I'd also like to acknowledge the Earth System Predictability Working Group for some newfound collaborations in this area, and hope to have some updates on that, on those collaborations with our working group. Next, please. And then I'd also like to acknowledge some really cool sea ice reanalysis work using SEIS in collaboration with the DART team. And this is work that's being done by CC Bitz's group at the University of Washington. And they're doing some really neat work currently with Yangfei Zhang regarding being able to find optimal parameter values using ensemble Kalman filters, optimal parameter values for sea ice. Next, please. So another major research priority area is the coupling between winds and sea ice. So we ask, how do Arctic and Antarctic sea ice, how do they respond to winds? This is work being done by Letty Roach and Ed Blanchard-Rigglesworth at the University of Washington, as well as Xinghua Ding at the University of California at Santa Barbara. Next, please. And then we also are interested, on the flip side of that question, how do changes in the sea ice impact the surface winds? So this is work being done by Laura Landrum, Steve Avris, and Alice Duvivier. And so on the top figure here, you see this change in sea ice between the last 30 years of the 21st century versus the 20th century. And the red basically just indicates that the wind speed has vastly increased over those areas where sea ice has been lost. And basically, the bottom figure shows that the larger change in ice fraction that you have, the larger decline, the greater the change in wind speed. So basically, as soon as you get rid of the sea ice, the winds just go crazy and whip right up. And some recent experiments by Alice Duvivier suggest that this is indeed due to the surface roughness of sea ice, which is very effective at quelling winds. Next, please. So some more research priorities that we have are about sea ice, natural variability, and external forcings. And in particular, we would like to understand how much of the sea ice response is due to internal variability, how much is due to natural forcings like volcanoes, and how much is due to external forcings, anthropogenic. And so the first sort of question here relates to Antarctic sea ice resilience over the historical period. This is work that currently Alice Duvivier and I are working on. Next, please. And there's also some work regarding sea ice sensitivity to both ozone as well as ozone depleting substances that have a high greenhouse potential. So this is work being done by Lorenzo Polvani at Columbia University. Next, please. And then there is the sensitivity of sea ice to volcanic eruptions, particularly the shortwave forcing at top of atmosphere, which you see on the left due to the sulfate aerosols in the stratosphere. So this is a simulated couple of ensemble members for the Mount Pinatubo eruption. This is a set of model simulations for that. So on the left is the shortwave at the top of model. In the middle is the sea ice area anomaly, which you can see expands following the eruption. And then on the right, you see the volume anomaly, which also you can see gets larger. So this is work that's currently in progress by Marika Holland and collaborators. Next, please. And finally, I'd like to acknowledge the awesome biomass burning work and sea ice's sensitivity to biomass burning forcers in Earth system models. This is work being led by Patricia Di Rupentigni et al. And Patricia gave a fabulous talk this morning. So hope that you got to see that. Next, please. And finally, another set of catch-all research priorities are sea ice processes, parametrizations, and impacts. So first of all, we are interested in sea ice growth processes, particularly polynya, snow to ice conversion, as well as basal growth and the relative prevalence of each of these and how that depends on the thermodynamics parametrizations and models, for example, as well as how the relative prevalence of each of these affects the sea ice's sensitivity to forcers. Next, please. We're also interested in the impact of sea ice parameterizations on sensitivity and predictability. So here I show the autocorrelation of sea ice area on top in the CSM2, on the bottom in the CSM1. And you can see that in the CSM1, the ice has much more memory. In other words, it's like redder. The correlations are higher for much longer than in the CSM2, which is shown above. And so this is kind of work in progress to sort of figure out why this is the case, and perhaps whether this has to do with the thermodynamics, whether this has to do with the ice-ocean coupling. There's a lot of interesting questions here. Next, please. And finally, we are very interested in the impact of sea ice on the atmosphere, on the ocean, as well as on biology. So I'd like to give a shout out to Jen Kay and her work on the CSM2 tuned ice runs, which hopefully that work will be submitted very shortly. And the really exciting thing about that is it suggests that you can actually tune the sea ice without necessarily totally messing up the rest of the climate system, which is kind of a relief, right? Because, you know, it's nice to get the sea ice right, but you don't want to break the rest of the model. And then I'd also like to acknowledge the work on seabirds and biogeochemistry in the Antarctic and in Antarctic coastal plinias being done by Alice Duvivier and Marika Holland and others. Next, please. And so finally, I'd like to just articulate a wish. And this is a wish that we are able to couple the sea ice biogeochemistry with the ocean biogeochemistry. And the reason why this is so important is because there's a lot of critters, like larval organisms, like larval krill, for example, as well as algae, as well as lots of different tracers that are found in the sea ice. And currently these are not coupled to the ocean. So some of the BGC people, I might be coming to chat with you. So just giving you a prior warning on that. Next, please. And so please give us community input. Please join our mailing list. We'd love to talk to you. Next, please. And please come to our joint Paleoclimate Working Group, Land Ice Working Group session. This is on Thursday morning. There will be fun breakout sessions. And afterwards, we will have a Zoom lunch, which will be so much fun. So thank you all.
Thank you, Hansi. I'm assuming there will be beer as well, but
it'll be virtual beer. It will be bring your own beer. Bring your own beer. Yeah.
Thank you. So our next speaker is Bill Lipscomb from Ocean or Sea Ice, rather. We are going to Land Ice. Bill, please go ahead.
Thank you, Gökhan. Elizabeth, do you have the talk ready?
Just 1 second.
All right, thank you. I'll be speaking on behalf of my fellow co-chair Jan Lennertz and the Land Ice Working Group liaisons, Gunter Legee and Kate Thayer-Calder, and the many working group participants who did the research I'm going to be talking about. Now, are we on, is this the view that we're wanting to have, or should we have, can we go to full screen?
We are going to bigger screen, just a second. It's okay now.
Great. Next slide, please. Well, I'd like to first talk about work that's been ongoing for the past couple of years to do simulations with CSM coupled to the community ice sheet model with an interactive Greenland ice sheet, and also standalone ice sheet simulations in support of community projections of sea level rise, which we've been very active in using CESM. Then I'm going to talk about some newer work where we're looking not just at the present and future, but also the evolution of paleo ice sheets. We're also beginning to move beyond ice sheets to other forms of land ice, including mountain glaciers, and beginning to look at glaciers in the Himalayas and other parts of high mountain Asia. And then I'm going to talk about some exciting new development work on being able to run coupled not just with Greenland, but also with Antarctica or with an arbitrary number of ice sheets in CESM. Next slide, please. Gökhan showed the slide in his summary this morning. We've done a number of simulations with CSM coupled to a dynamic Greenland ice sheet, where we've run for pre-industrial and then historical and future climate scenarios. In the upper right is pictured the response of the Greenland surface mass balance to carbon dioxide increasing by 1% a year up to quadrupling and then being held fixed. You can see in the middle and right panels that there's a very large increase in the size of the ablation area represented in blue as we go to a warmer climate. And as the ablation area expands, we have rapid contribution of Greenland to sea level rise, more than a meter by year 350 in this 4 times CO2 scenario. And you can read about this in the special issue in James. Next slide, please. Now, something people want to know about the Greenland ice sheet when we're looking at various warming scenarios is, at what point does the surface mass balance, the difference between accumulation and ablation, become negative? Because at that point, even if you don't have any more calving loss, if you maintain warming for an extended period and then the mass balance is negative, then most of the island of Greenland will ultimately deglaciate. So in this particular study, people who work with both CESM and the RACMO2 Arctic Regional Model put their heads together and did some dynamical downscaling of CESM2 output to RACMO2 to determine the threshold where you have where the surface mass balance is negative. And what they found is that this happens around 4.5 degrees Celsius of warming for Greenland, which, because of Arctic amplification, corresponds to a smaller global mean warming of about 2.7 degrees. As you might expect, when you reach that threshold, depends a lot on your emission scenario. In the high emission SSP 585 scenario, we reach that threshold or turning point around 2055, whereas in a strong mitigation 2.6 scenario, that threshold is never reached. Next, please. Continuing on from the quadruple CO2 experiments, Miriam Biscayno and colleagues have done some long-term deglaciation experiments where they've looked at how long does it take Greenland to entirely deglaciate in a couple model. In this case, they've run the ice sheet model asynchronously, meaning more than one ice sheet year per climate model year, so that you can run a larger number of years. And they find that it takes, in this scenario, about 1,700 years to deglaciate Greenland completely. You can see from the panels at right that most of the southern half of the ice sheet is gone by the time you get to year 700 or 800. And the Greenland ice sheet, which currently has lots of outlet glaciers draining to the ocean, becomes a terrestrial-based ice sheet with little or no calving by about year 300. There's a large acceleration in melting starting around year 120 when solar feedbacks really kick in. And also some suggestion that even before you get to the negative surface mass balance threshold I talked about, you do reach a point where you can have complete deglaciation, and that's because of surface mass balance elevation feedbacks as the surface lowers in a retreating ice sheet. Next, please. Moving on to sea level projections. We were part of the ice sheet model intercomparison project for CMIP6 or ISMIP6. And there was another group looking at mountain glaciers called GlacierMIP over the same period. Just recently, a summary paper was published in Nature by Thames and Edwards et al., summarizing the results of these projects. A key finding was that if we are able to limit global warming relative to the pre-industrial to the Paris target of 1.5 degrees Celsius, that would roughly have the median land ice contribution to sea level rise between now and 2100, from about 25 centimeters to about 13 centimeters. But not all land ice responds the same to warming. For the case of mountain glaciers in the Greenland ice sheet, the majority of mass loss is due to increased summer melting from warming temperatures, and the models are fairly consistent with one another about how that happens. But for Antarctica, there's a great deal of model disagreement and a lot of uncertainty due to competing processes. You have increased snowfall in a warmer atmosphere, which tends to make sea level fall, but that competes with mass loss, which can already be observed due to ocean warming, getting beneath ice shelves and causing the marine ice sheets to lose mass and possibly destabilize. Next slide, please. Now, those projections were focused on the time between now and the year 2100, but in many cases, by 2100, things are just beginning to get interesting with more rapid mass losses. So a project we did using CESM was to look at longer term projections of Antarctic ice loss driven by warm oceans. So the idea here was you take the ocean warming that's projected to occur by the latter part of the century, continue forcing the ice sheet for another 400 years out to 2500, and see how much mass is ultimately lost. The answer is it depends on a lot of details in the model, including which CMIP ocean model you're using to provide the ocean warming anomaly. Also depends on some details of the ice sheet model, including the way you parameterize subshelf basal melting and the basal sliding along the bed. We found about an order of magnitude difference in the ice loss at year 2500 from only about 15 centimeters to about 1.5 meters. The two figures on the left, you can see where most of that grounded ice loss is. It's largely in the Ronnie Filchner sector and the Ross sector. However, most of the ice loss observed today is in the Amundsen Sea sector, and there we found threshold behavior. Under some circumstances, there's very little loss, but then you reach a tipping point and you see catastrophic loss in the following centuries with sea level rise of 1 meter or more. So we're very interested in better constraining our parameterizations because it's obviously of great social importance, whether the Thwaites Glacier Basin remains stable or not. Next slide, please. Moving on to some paleoclimate simulations. Aaliyah Summers, who was a postdoc here, has led a project on transient simulations of the last interglacial period from 127 to 119,000 years ago. In the top set of panels, you can see the shrinking of the Greenland ice sheet for the first 5,000 years or so, followed by its gradual recovery. And in the lower set of panels, you can see the surface mass balance with negative values in red. A key finding of this set of experiments was that it matters a lot how you treat vegetation. In the experiments that I've shown here, we use the biome vegetation model to update the vegetation as the climate evolves. If you don't have those updates, you find that Greenland retreats much less. So that seems to be a really important mechanism in simulating accurately the rate of retreat of the Greenland ice sheet during paleoclimate periods. Next slide. Going forward in time a little bit, about 116,000 years ago was when the Northern Hemisphere, Canada, Eurasia started to reglaciate. And Marcus Liverstrom has in review a very interesting study looking at glacial inception in CESM. And he finds first that CESM does a really good job of simulating the timing and the places where glaciers reform around 116,000 years ago. Also, he has an interesting finding that to get the Scandinavian glaciers to reform, you have to cool the climate by closing off the ocean gateways in the Canadian archipelago. That results in weakened convection and Nordic Sea cooling, which allows for Scandinavian inception. Next slide, please. I'll just talk briefly about some work which is now in progress. Continuing the paleo theme, Sarah Bradley and Michaela Petrini have been working on simulations of the Northern Hemisphere ice sheets at the time of the last glacial maximum, 26 and 21,000 years ago for the couple simulations they've done so far. Their plan is to simulate the surface mass balance of these periods and then use the resulting surface mass balance to force standalone ice sheet simulations, and ultimately to couple these simulations to see if we can accurately simulate the dynamics of the ice sheets at and then after the last glacial maximum when deglaciation began. Next, please. Another project using the new variable resolution CESM capability, which others have talked about, is to see how well we can model ice processes in high mountain Asia. Traditionally, we haven't tried to do this because the grid resolution required was too high, but now we can refine a grid down to 7 kilometers for parts of high mountain Asia. And doing this, we can simulate a more realistic surface mass balance. Renee Weingard, working with Adam Harrington at NCAR, finished a 20-year simulation last year. We're now tuning that simulation, trying to get a better surface mass balance and also updating our glacier fraction data set. And then once that's done, we're going to start a new spin up and see if we can run through 2010 or beyond and get a realistic surface mass balance for glaciers in high mountain Asia. Next slide, please. Also, a very exciting piece of development led by Bill Sachs with contributions from many others. Until now, we've only been able to run with a single ice sheet in CESM, and usually that's been Greenland. But we're now adding support to run with an Antarctic ice sheet dynamically out of the box. And in addition, we'll be able to run with multiple ice sheets, Greenland, Antarctica, or perhaps Antarctica and paleo ice sheets in one simulation. This requires, for the first time in CESM, supporting a model component with multiple grids, and each grid instance can have its own physics parameters. So for example, you can run with some settings different between Greenland and Antarctica. That work is not quite complete, but it's pretty close, and we're now in the testing stage and hope soon to make that available for research to the broader community. Next, please. I will wrap up just by mentioning a few new projects. Kate Thayer-Calder is working with GHub, which is a new NSF cyber infrastructure project. GHub is building connections between the data and modeling communities of ice sheet modelers and glaciologists. And our contribution will be to contribute curated CESM data sets and diagnostic tools for visualizing fields relevant for ice sheets. Some other projects that are just getting underway. We're using our new Antarctic coupling capability to study the evolution of Antarctica during the last interglacial, when it's thought that the West Antarctic ice sheet may have collapsed, as a possible analog for future warming and future waste retreat or collapse. We're looking at, excuse me, relatively high resolution ice sheet ocean coupling in the MESO-MIP2 project, and also the high mountain Asia work I mentioned. Once we have a surface mass balance, we can use that surface mass balance to force CESM and use CESM for the first time, not just for ice sheet, but for mountain glacier studies. Last slide, please. As Hansi said, we have a joint session with the Paleoclimate Working Group on Thursday. We hope you'll come and hear more about some of these efforts, and please feel free to reach out with questions or ideas. Thank you.
Thank you very much, Bill. So now we'll be going to Paleoclimate Working Group, and Esther Brady will be providing the update. Esther, are you there? It looks like she's on the attendee session, Elizabeth.
Okay, this makes more sense for me now.
Yeah.
Nothing was making sense earlier with any of the
You have to be in the right group.
Yeah.
Yeah. We'll start the presentation just a second.
I was wondering why things weren't happening the way I thought they should. Okay, I'll get started. I'm Esther Brady, co-chair of the Paleoclimate Working Group, and today I'm going to share some highlights from our activities. First, I'd like to acknowledge my co-chair, Arnie Winguth from the University of Texas, and Betty Otto-Bliesner and Sean Zhu from the NCAR Paleoclimate Group for their contributions. Next. But first, I would give a broad overview of our working group. Our members conduct studies for specific past climates, ranging from deep time in Earth's history to climate of the Common Era with Earth system simulations and proxy climate information. Some of our science priorities are to investigate relationships between climate drivers, such as greenhouse gases, volcanic activity, ice sheets, etc., and the system responses and feedbacks, to assess simulated out-of-sample climates against the paleoclimate reconstructions, and provide a long-term perspective on climate sensitivity, feedbacks, and processes over a range of spatial and temporal scales. Next slide, please. I'll start highlighting some of our activities. First up is the CMIP-6 Tier 1 past 1000, a PMIP-4 experiment designed to evaluate forced and internal variability on decadal and longer timescales over the last millennium. This is a collaboration between the Paleoclimate, whole atmosphere, and land working groups, and it uses the CESM2 WACM-6 middle atmosphere configuration to best represent the volcanic emissions, thought to be an important driver over this period. We have two simulations and a control. The two simulations have different volcanic emissions as shown in the upper panel. And the other transient forcings are the same for each run, such as the PMIP-4 solar forcing in the lower panel, revealing the grand minima and more active periods shown over the last millennium. These simulations and a control are now finished and will be released and documented in a forthcoming manuscript. And that slide did not come out the way I thought it would, by the way. Next. Next is the transient last interglacial coupled climate ice sheet simulation that Bill just spoke about with the CESM2 model coupled to the CESM2 ice sheet model, a joint project between members of the Paleoclimate and land ice working groups. This project investigates interactions between climate, a dynamically evolving ice sheet, and vegetation feedbacks in warmer conditions relevant for informing the future when melt from Greenland ice sheet will lead to major impacts due to rising sea levels. As Bill discussed, the simulation starts at the height of the last interglacial and run in an accelerated mode with transient orbitally driven insolation changes. One simulation had a vegetation distribution periodically updated from biome 4, run offline with climate model input, and the other with fixed pre-industrial. And two figures from Aaliyah's paper are shown here. We found the high latitude vegetation response to the orbital forcing provides important feedbacks, crucial for getting the enhanced Arctic warming in the biome 4 run and retreat of Greenland ice sheet to a minimum extent shown in the left panel at 122,000 years ago. The greater retreat shown on the right, in the right panel, is also from the biome 4 simulation. A manuscript has been submitted led by Aaliyah Summers, and simulations will soon be released. And we have now a complementary transient Holocene CESM2 simulation in process. Next. Another project investigates response to large freshwater additions from melting continental ice sheets that occurred during deglacials with focus to the Heinrich Stadial 11 event. This was a cold event that took place in the penultimate deglacial leading to the start of the last interglacial. It lasted about 4,000 years at a time when sea level rose by about 80 meters. It's hypothesized to be important for the collapse of the West Antarctic ice sheet during the last interglacial. These plots are from a CESM2 simulation with freshwater added to the North Atlantic at about the same rate as I just mentioned. By 1,000 years, you can see that the Atlantic meridional overturning circulation collapses. Arctic sea ice has expanded. Southern Ocean sea ice has retreated, and a strong bipolar seesaw pattern appears with cooling over the Northern Hemisphere and warming over the Southern Hemisphere. This simulation will be used to investigate linkages between the ocean circulation and the climate responses and assess the capability of CESM to simulate abrupt change in response to tipping points in the climate system. The simulation continues, and a new collaboration with the University of Washington researchers will use CESM and CESM to explore what conditions lead to a collapse of the West Antarctic ice sheet. Next. A future project we plan is to simulate key paleoclimates at a high resolution with the CESM 1.3, run with the quarter-degree CAM SC model coupled to the 1-degree ocean component. We'll utilize boundary conditions and initial conditions from current paleoclimate simulations. For example, the last glacial maximum, an extreme warm period in the Eocene, and the warm mid-Pliocene. The simulations will be used to improve proxy data comparisons, investigate extreme weather phenomena under different forcings, and the state dependence of phenomena such as tropical cyclones and atmospheric rivers. Demonstrating the promise of this project for the science, are these figures here from a high resolution simulation run by Run Fang from the mid Holocene. She shows a reduction in the density of the tropical cyclone tracks in the mid-Pliocene warm period compared to pre-industrial, though the number of very intense hurricanes were increased. Next. Now I'm going to talk about some current development activities. First is work led by Jean Zhu and the Paleoclimate Group at NCAR to develop what we call the Paleo-calibrated CESM. The motivation is summarized in this figure here on the right. As you can see, the equilibrium climate sensitivity of the different CESM versions correlates well with simulated LGM cooling. Versions from CCSM3 to CESM1 yield glacial cooling that reasonably agrees with the best estimates from the proxies, as shown by the grade range. CESM2 with the highest ECS exceeds the range found in the last IPCC assessment and shows extreme cooling well outside the proxy range, suggesting high CESM2 ECS may be unrealistic for simulating out-of-sample paleoclimates, putting much paleoclimate science out of reach. This motivates developing a paleo-calibrated version for paleoclimate applications. Over the course of the work, Jean performed a number of simulations isolating different parameterizations, taking CAM5 to CAM6, and found cloud parameterization responsible for the larger LGM cooling. Next. This new paleo-calibrated CESM2 still retains all the latest CAM6 physics with a few tweaks to the cloud microphysical parameterizations. These changes impact cloud feedbacks, reducing positive global shortwave cloud feedback. And as you can see, it brings the simulated LGM cooling in better agreement with the proxy data, as you can see in the figure on the right, with a global cooling of about 7 degrees and a lowered ECS to about 4 degrees C. The corresponding pre-industrial and historical simulations look good too. For more details, I refer you to Jean Zhu's talks. The first is going to be on Tuesday in the Atmospheric Model Working Group meeting, where he'll talk about the cloud parameterization work he did. And then the second at the Paleoclimate Working Group meeting, where there will be a focus on the LGM simulation. Next. I'd like to make you aware of 2 development activities underway by our external community that Keith Lindsay mentioned in his talk. Both of these activities were presented in our winter workshop. The first is by IPCC and Joost at the University of Bern to implement carbon isotopes into CAM6 and couple those tracers to existing carbon isotope tracers in CLM and POP. The second is by members of PalMod to incorporate the interactive sediment model Medusa into CESM 1.2 in order to include slow processes that affect the marine carbon cycle and bottom water chemistry and allow more direct comparisons to the sediment archives. These preliminary results that they presented were both exciting and promising for bringing new capabilities for new science applications. Next. Thank you. I'd like to just mention that one aspect of our working group is supporting the paleoclimate community for CESM applications. It's not easy to take raw paleoclimate boundary conditions, which are very different from modern, and configure the model. So we host community expertise on configuring the CESM for non-modern boundary conditions. We hope to grow the resources at these links shown here with contributions by the community for the community in a collaborative spirit. We also provide paleoclimate simulations on NCAR's Climate Data Gateway. Uses for these include process studies, forcing offline models, using the paleoclimate proxy data in combination, and running additional sensitivity runs. Some available collections are listed here on the slide. If you come to our working group meeting, you will be able to hear some talks that use these simulations in wide applications. Okay, my last slide next, thank you. And with the last slide, I thank you for listening, and I hope to entice you to our working group meeting on Wednesday morning. We have 10 interesting talks, many by early career researchers, on a wide range of topics and time periods, titles of which produce this word cloud to the right. 2 discussions will focus on questions that emerged from the submitted talks. These discussions should help crystallize how paleoclimate modeling can help inform climate sensitivity and suggest implications for future climate, and how to better understand past climate change by combining models with proxy data. I invite you to our session and the virtual meetup that follows at noon, where we can have a more direct, informal discussion. Thank you.
Thank you very much, Esther. So we'll move on to software engineering working group, and that's going to be represented by one of the co-chairs, Bill Sachs. Please go ahead, Bill.
All right, thanks. So I'm presenting this work on behalf of many of the members of the software engineering working group, as well as the other co-chair of the working group, Leisha Bernadette at NOAA. Next slide, please. So a lot of work right now is underway to develop next generation diagnostics packages for CESM components. And so I want to start by inviting you to our presentation and extended discussion on this topic at the Software Engineering Working Group session Wednesday afternoon. One of the goals of this discussion is to identify new areas for collaboration on diagnostics packages. So we really hope you can attend to contribute your thoughts on a variety of questions, such as what features are most important to you in the new diagnostics packages that are being developed. Next slide, please. There's also continued work towards improving the management of CESM's output data sets. This is getting to be increasingly important because compute power is growing much faster than our available storage space. So one avenue of work is in reducing CESM's output volume, such as through various compression techniques. And Alex Pinard is going to present a virtual poster on Tuesday touching on this, and specifically discussing the LDC Pi tool that has been developed to help evaluate different lossy compression techniques. So we hope you'll be able to stop by his poster and learn more about this project. Next slide, please. Another avenue of work related to model outputs is in developing guidelines for data preservation and curation. And Gary Strand is going to present a virtual poster Tuesday on that topic. So again, we hope you'll be able to stop by his poster and learn more about that. Next slide, please. Over the last few years, a few members of the Software Engineering Working Group have been working to develop a new component coupling infrastructure. This is based on the Earth System Modeling Framework's NUOPSI interoperability layer. This new infrastructure is known as the Community Mediator for Earth Prediction Systems, or CMEPS, and it's really just about ready for use now. It is ready for use and is already being used for some applications, and it's just about ready for kind of wider applications at this point. A big advantage of CMEPS is that it makes it easier to introduce new grids than it has been in the past in CESM. This is getting to be very important because it's becoming more and more common for CESM users to create their own new grids for their specific science application, including refined grids. CMEPS provides the ability to calculate regridding weights between components at runtime. So that removes the need for most of the mapping file generation that used to be needed in the past as kind of a pre-processing step for CESM. A recent CMEPS feature also removes the need for land and ocean domain files, which were another barrier to creating new grids in CESM. ESMF also offers a variety of features that help with debugging and performance. For example, CMEPS introduces a new capability to have different threading levels from components that share the same processors. And this is going to be able to offer us large potential improvements in model efficiency for the full coupled model. A final key benefit is that CMEPS is shared between multiple modeling systems beyond just CESM. So this is really facilitating collaboration and interoperability with other agencies, including other projects funded by NSF and NOAA. In addition, bringing in more people into the development of CMAPs and the use of CMAPs is leading to a more robust system. Next slide, please. One example of the new science that CMAPs is facilitating is something you heard about from Bill Lipscomb a couple talks ago, which is including multiple ice sheets in a CESM simulation. Until now, CESM has only supported a single ice sheet at a time. We are close to having support for multiple ice sheet grids, such as Greenland and Antarctica together in one simulation. This turned out to be much easier to support in CMAPs than it would have been with the old coupling infrastructure, thanks to the ESMF capabilities for handling hierarchies of model components. Next slide, please. CESM for a long time has had a valuable feature that allows users to substitute data components for the prognostic atmosphere, land, ocean, sea ice, and other components, which supports hierarchical model development. So you can test and run your component, say the land component, offline, forced by a data atmosphere. There's a new development complementing CMAPs of developing new data models. These CDEPS data models, the community data models for Earth prediction systems, are also based on ESMF, and these replace the old data models based on the Model Coupling Toolkit, or MCT. As with the old data model infrastructure, CDEPS provides both data components and also infrastructure that prognostic components can use to ingest their own forcing data. And CDEPS is providing new features in both of those areas, such as by providing new online regretting capabilities. As with CMAPs, CDEPS is being used in multiple modeling systems, and it's contributing to a number of collaborations already with various NOAA and NSF projects. Next slide, please. All right, so when is all this going to be ready? What's the status? Already, CMAPs and CDEPS are available in the latest CESM development code, not by default, but you can invoke them by running with the flag driver nuopsy. There's already been extensive validation of many configurations. In fact, that validation has been successful. Validation of the fully active configuration is right now underway. At this point, new coupling features, such as the ones I described for land ice, are just going into CMAPs and not into the older coupling infrastructure. Starting with the CESM 2.3 release, which will be the next release version of CESM, CMAPs and CDEPS will be the default infrastructure, though you will still for some time be able to run with the older MCT coupler 7 using a driver MCT flag to the create new case command. Our plan, though, is to drop support for the older MCT coupler 7, at least by CESM 3, possibly earlier, to be determined. However, I want to emphasize that older coupling infrastructure will still be supported in the stable CESM 2.1 or CMIP 6 release code for as long as that release code is supported. Next slide, please. Substantial work is continuing in the development of the Common Community Physics Package, or the CCPP, which facilitates sharing atmospheric physics code between different models. At this point, work has begun to converge towards a common framework used by both NCAR and NOAA, and this is based on the second generation code generator, capgen.py. The expectation is that this process should be complete within this calendar year. Next slide, please. So traditionally, CESM has been run on supercomputers with users or software engineers, system administrators, porting CESM separately to each system where someone wants to run the model. This usage is not going away, but a new complementary usage is now available, leveraging container technology in the cloud. This is really a big paradigm shift. We can now provide not just code, but also fully working portable environments. So it's now possible to get CESM up and running on a new machine in really literally a matter of minutes. This ability to embed new tools with the code also allows us to extend things in ways that would otherwise be incredibly complex, like offloading runs from a local container up to the cloud, or providing tools that work anywhere via these platforms and can interact with various APIs or databases for other purposes. Next slide, please. Another really exciting new project is the development of a graphical user interface for creating a CESM case. The initial motivation for this was to help users discover and understand what simpler model configuration CESM offers. But really, this is general enough that it's going to be very useful for a variety of purposes, and really for any users coming in fresh to CESM, or even experienced users with CESM. Really what we're realizing is as more and more options become available in all of the CESM components, and there are many more ways that you can possibly mix and match different options, it can be really hard for users to know what options are available and which options are compatible with which other options. So this new tool is really going to help immensely with this problem. There are a couple of major pieces of this project. First, we are developing new metadata in the model to express interdependencies and compatibilities between different options within a component or between different components, say what atmosphere components are compatible or incompatible with certain ocean options. And second, we're developing a graphical interface to choose these options. This interface presents only the options that are compatible with each other and allows you to easily see the meaning of the different options, as is highlighted at the bottom as kind of the hover over text that appears. I hope you can make it to Alper Alpuntas's talk on Wednesday afternoon, where he's going to present more details on this exciting new tool. Next slide, please. Another new set of developments is that new workflow scripts have been developed to help with running CESM in a variety of forecasting applications. So these new scripts automate a variety of steps, a number of steps that are required in these forecasting applications. First, collecting and pre-processing initial and boundary data. Next, staging the model ensemble members, then running those model ensemble members, and finally post-processing and archiving the data. A challenge with this has been that each type of forecast requires slightly different scripts, but the template is the same for all of these forecasting applications. So we want to make people aware of this, partly because we want to encourage people to use these tools if the template seems to fit their need, and also because these scripts provide examples of how you can use the SEAM infrastructure, case objects, and the publicly available Python subroutines to do things that go beyond just the default SEAM functionality. And these are available on a branch in GitHub as branches in GitHub as shown below at the bottom. Next slide, please. Finally, I just want to end by encouraging everyone to post issues via the CESM forums or via the GitHub repositories and the issue trackers when you run into problems, so that we really want to help to continue to improve the model for everyone, and really want your help in identifying issues so that we can do that. We truly do want to receive this kind of feedback so we can know what isn't working for people. We do realize, though, it can be hard sometimes to know where to open an issue, especially given that there's so many CESM components and so many repositories. So I want to start by saying, please don't worry too much about that. We'd rather have you open an issue in the wrong place rather than not opening one at all. That said, I want to show you in a couple of slides what we've put together to try to help you find the right place to go for help, either an issue or just help running the model. So first off, the ESComp, Earth System Community Modeling Portal, github.com/escomp is a good place to find most, though not quite all, of the repositories included in CESM. Next slide, please. To get a full list of the repositories and specifically directing you to where you can open issues for each component, you can go into the CESM repository, so github.com/escomp/CESM. Click the issues button for next, please. And then new issue, and next slide, please. And there you'll get an issue chooser. I'm just showing the top here. There's actually quite a lot of listings on this page. And so you'll get a bunch of links that will bring you to the right location to report issues in CESM as a whole or in any of its various components. I do want to call your attention, if you're not aware of it already, to the CESM forums near the top of this page. In many cases, that should be your first place to go for help. But this landing page also includes links to open issues in the various component repositories. So again, really, we want to encourage you, please do let us know when you run into any problems with the model. We really do want to help you out. Thanks a lot.
Thank you very much, Bill. So our next speaker is going to be Isla Simpson, and she'll be representing Climate Variability and Change Working Group. Just a second, we'll put the slides up.
All right.
Okay.
Thank you.
Go ahead.
Thanks. So I'll give the update for the Climate Variability and Change Working Group on behalf of my co-chairs as well, Aishu Hu from NCAR and Sarah Larson from NC State. And they're both new co-chairs in the last year. The liaisons, Adam Phillips and Gary Strand, and also previous co-chairs, Clara Desser and Jerry Neal, because some of the projects I'll talk about started at the time when they were co-chairs. So if you go to the next slide. So a large part of what we do in the Climate Variability and Change Working Group is to make simulations with the latest models available to the community. So I'll run through what we've done in the last year and where we're going in the coming year. So this is one set of simulations that we typically run. These are simulations with prescribed sea surface temperatures taken from observations, and we have two 10-member ensembles. With the Goga ensemble, which has observed SSTs prescribed globally, and the Toga ensemble, which has observed SSTs time varying in the tropics and the climatology elsewhere. And these have been available for a while now, but we have updated them. In particular, the Goga runs now extend to the end of 2020. If you go to the next slide. So a new ensemble that has become available in the last year are tropical Pacific pacemaker ensembles with CSM2, and we heard about this type of experiment from Jerry this morning. So we have a 10-member ensemble, and this is where sea surface temperature anomalies in the tropical Pacific are relaxed towards observation. So that gives us coupled simulations, but with ENSO-like variability in the tropics that resembles that of the real world. And these go from 1880 to 2019 at this point. And what you see in the figure at the bottom there is the mask that's used for the relaxation. So where it's red, the sea surface temperatures are being relaxed. And this is a bit different from what was done in CSM1. In CSM1, only that kind of rectangular region in the Eastern Tropical Pacific was relaxed. And in CSM2, this is thanks to a suggestion from Dylan Amaya. We've changed that mask a little so that we relax in that kind of wedge shape out into the Western Tropical Pacific to kind of capture the Western Pacific SST variability more correctly, but kind of minimize our impact on sea surface temperatures in regions that we think respond to the Eastern Tropical Pacific. If you go to the next slide. Another thing that we added along with these pacemaker experiments are step-by-step instructions for how to set them up. So if you want to reproduce the tropical Pacific pacemaker, or if you want to relax SSTs in another region, you can try and follow these instructions. And if anything is unclear, please get in touch. Go to the next slide. We've also added an additional simulation to the pre-industrial control series. So we had already kind of extended the CMIP6 pre-industrial control out to 2000 years. And we had run a 1,000-year-long pre-industrial control where the sea surface temperatures were prescribed to be the climatology of the coupled run. And the new one that we've added this year is the third one there, the 500-year-long uncoupled pre-industrial control that has time-varying sea surface temperatures prescribed corresponding to a segment of that coupled run. So together, these three simulations can allow for exploration of the impact of having sea surface temperature variability versus having coupling or not in both directions. Go to the next slide. So working group members were heavily involved in the CSM2 large ensemble, but I'm not really going to go into the details of that because we're going to hear about that from Keith in a few minutes. But what we have run within the working group are a suite of simulations that are complementary to the CSM2 large ensemble that we're about to hear more details about. And so one of them is listed here, is what was referred to as a medium ensemble in CSM1, basically running the same model, but with a different forcing scenario. So we've run a 16-member ensemble of simulations from 2014 to 2100 under the SSP 245 forcing scenario. So that's less forcing than in the SSP 370 scenario, which is what is used in the CSM2 large ensemble. And we heard a bit from Patricia this morning about the biomass burning issue. So just a note is that these simulations use the smoothed biomass burning emissions to avoid those discontinuities in the GFED era, but that only affects the first couple of years of these simulations since we're starting in 2014. Next slide. So another big project that's underway, thanks largely to the work from Nan Rosenblum and also with help from Sasha Glanville, is the single forcing large ensemble. So this again will be complementary to the CSM2 large ensemble. And a slightly different approach is being used here than what was done in CSM1. So in CSM1, the single forcing large ensemble consisted of simulations where everything was evolving except for that forcing of interest. And we're kind of doing the opposite here. So we're keeping all other forcings fixed at 1850s values and allowing the forcing of interest to evolve over the historical and then into the future period. So this is still underway. If you go to the website there, you'll see the data location, and some data are there and more will be arriving. Currently, the simulations extend from 1850 to 2050, but the plan is to extend these out to 2100, dependent on resources. But I think if we can continue to run efficiently, we will have the resources for that. These are currently, well, not quite yet, but they will be 15-member ensembles for each forcing, and we've chosen 4 different forcings. So we have simulations where only the greenhouse gases are evolving and everything else is kept fixed at 1850s values. We have simulations where only the industrial aerosols are evolving and everything else kept fixed at 1850s values. Then we have an ensemble where only the biomass burning aerosols are evolving. And again, this is using those smoothed biomass burning aerosols to avoid discontinuities in the GFED era. So these will be most directly comparable to the second 50 members of the CSM2 large ensemble. And then our 4th single forcing ensemble is what we're calling everything else, which is where we basically put all of the other forcings that are evolving in time evolving together. And so the motivation for this is so that we can test additivity and linearity. So we should be able to add up these 4 ensembles and see whether they add up to the anomalies that you get when everything is evolving together. And the hope is that the forcings in the everything else simulations are kind of active at sufficiently different times, kind of frequencies and different periods in the simulations, that this could also be used to just isolate the impact of those individual forcings. But we can also build off of this if interesting things come up and we want to try and separate things out further. Go to the next slide. So now we're on to simulations that we plan to do in the near future. And so one of the big projects for the coming year is that we'd like to do a regionally refined down to 1/8 degree simulation in the North Atlantic. And you can see the proposed grid there on the right for what this simulation will be using. And the plan is that this would be an AMIP simulation, so prescribed sea surface temperatures that are based on observations, and that will run from 1950 to the present day. And thanks to a suggestion from Steve Yeager, I think what we'll probably use as the SST data set here is actually the SSTs from a 1/10 degree forced ocean and sea ice simulation. So that would allow us to have kind of observation-based low frequency variability in the sea surface temperatures, but also have kind of fine scale features, ocean eddies and things, which you might expect would be important for ocean atmosphere coupling, but you can't really get at that from the observations going back to 1950. And so the primary motivation for this run is that we think that there's deficiencies in the representation of North Atlantic jet stream variability related to sea surface temperature variability. And there's evidence that, and you might expect that the nature of ocean atmosphere coupling might change as we go to this kind of very high resolution. And so we want to see whether that's the case, and it will allow us to look at kind of AMV type variability and its impact on the atmosphere. But we hope there will also be lots of other uses for this simulation. We already have a student from Quebec who's interested in looking at polar lows. And if there's anything you'd like to look at in this simulation, please let us know so that we can be sure to save all the relevant output. Go to the next slide. So a couple of other simulations that we have planned in the near future. We heard from Julio earlier about the new vertical grid. And what we'd like to do in the Climate Variability and Change Working Group is run a kind of intermediate simulation where we run with the new vertical grid, but we don't change the boundary layer. So we avoid all the additional changes in tuning and physics that might be needed to accompany that. And this will be kind of an intermediate step to look at what is the impact of having this new grid, which gives us the QBO and improved stratospheric variability on the representation of climate variability, but without all the additional physics and dichord changes that will ultimately be present in CAM7. This will also serve as a pre-industrial control run for some initialized predictions that are planned as a collaboration with Scripps. And then what you see at the bottom there, this is a project that is being led by Young-Oh Kwon from Woods Hole and his group. And so the schematic there is depicting the ocean model hierarchy from simplest on the right, which is prescribed SSTs, to the full dynamic ocean on the left, which is the more complex. And what we typically run in the Climate Variability and Change Working Group is the slab ocean configuration. But what we're doing this time around is instead using this pencil model, which is basically having kind of single column ocean model at each grid point. So that allows for mixed layer physics to be present and things like time varying mixed layer depths. And this, I believe, is underway, trying to get the control run going at this point. So hopefully that will be available soon. If you go to the next slide. So this is another project that's not kind of directly a CVCWG project, but it is of relevance, I think, to the community, and it's being led by Sarah Larson, who's the new CVCWG co-chair and in her group. And so this is an ensemble. It will be a large ensemble using what's termed the mechanically decoupled CESM, which is kind of another step in the ocean model hierarchy. So this is a full dynamic ocean, but the ocean only experiences the buoyancy forcing from the atmosphere. It does not experience the mechanical forcing from the wind stress. And so this is underway. I think once the first publications from Sarah's group are out, you can expect the data from these simulations to become available. And if you're interested, please get in touch with Sarah about this. So next slide. So this is the final slide. We have lots of new simulations that are available and ready to be analyzed. So please go to our web pages to find out more. Please also join the mailing list if you want updates about these simulations, and join us for the working group activities. We have a few posters at the poster session tomorrow, and then our oral session, and followed by a social and networking time will be on Wednesday afternoon. Thank you.
Thank you, Ayla. So our last working group presentation is by Yaga Richter on Earth System Prediction Working Group. And I just want to remind people that right after this, we will have the CSM2 Large Ensemble presentation by Keith Rogers. So Yaga, please go ahead.
Thank you, Gökhan. I'm going to give an update on the Earth System Prediction Working Group, which is co-led by myself, Steve Yeager, and Kathy Pijon. Next slide, please. And this working group is still relatively new, so it was established in April of 2020 with the goal to advance fundamental understanding of Earth system predictability on timescales ranging from subseasonal to decadal. And how we plan to do this is similarly to the Climate Variability Working Group, is planning and executing large ensemble initialized hindcast and forecast sets with and for the community, serving and promoting collaborative multidisciplinary research hub, and developing tools and frameworks to enable ESP research, for example, like the ones that Bill Sachs mentioned in his talk, to enable faster and efficient running of these initialized hindcast and forecast sets. Next slide, please. Just to get everybody on the same page, there are 3 primary timescales that we're going to talk about in ESPWG. And first one is S2S, which is subseasonal to seasonal timescale, which is primarily we focus on week 3-4 prediction, but S2S technically goes up to as far as beginning of one season. The next timescale we talk about is S2I, or seasonal to interannual, which focuses on a timescale for about a month to a couple of years. And the longest timescale we look at is S2D, or seasonal to decadal, where we look at seasons going out to decades. And as you see, what is important in each timescale changes with time. So for S2S, we have land, MJO, NAO, stratosphere, ENSO all being important. But as we go out to the decadal timescales, the role of the ocean and boundary conditions becomes more important. And this timescale S2I is really challenging. It's something that has not been studied a lot, is really in the middle of that, where probably ENSO plays the largest role, but we don't fully understand how much other factors like the stratosphere and other components of the ocean may contribute. So go ahead, next slide. So here's a summary of key accomplishments that we've done in the last a little bit over a year. So we've completed a subseasonal to seasonal reforecast set with CSM2 CAM6 and CSM2 WACM6. And I'll go through the details of this on the subsequent slides. We're also running weekly real-time S2S forecasts that contribute to NOAA's week 3-4 outlook. We completed a study of impacts of the January 2021 sudden stratospheric warming. We've completed a seasonal to multi-year large ensemble, or the SMILE project. We initiated the extension of SMILE to decadal prediction. There's work that has begun on diagnostic package. And in this 1.25 years, our mailing list has grown to 173 people, and we hope to grow it more in the subsequent years. So go ahead and next slide. So firstly, I'm going to describe briefly to you the S2S hindcast and forecast set with CSM2 CAM6 and CSM2 WACM6. So what we've done here is carried out the full subseasonal experiment protocol for the low top model of CSM2 CAM6. And this is the default version of the model. So 1 degree resolution, top at 40 kilometers, prognostic aerosols, and no interactive chemistry. And we do weekly reforecast, so always Monday initialization dates with 11 members and 45-day long simulations. And we started running real-time forecasts in April 2021. And we have a similar set with WACM, or CSM to WACM6, but this model is so much more expensive with than CAM that we could only afford to run the months from September to March and only 5 ensemble members. And the simulations are also 45 days long. And this model is running with fully interactive tropospheric and stratospheric chemistry, which is largely where the cost comes from. And weekly real-time forecasts are available since September 2020 with a 21-member ensemble. Go ahead, next slide. So here's some basic metrics on the scale of the model in the subseasonal timescale. And similarly to CSM1, CSM2 has excellent subseasonal skill. So what I'm showing on this plot on the left is a variety of sub-X models. And in the green bar there is the NOAA operational model. And this is just surface prediction skill for DJF temperature over North America. And the blue bars show you CSM1, 2 different versions that we ran a few years ago. And what you see that our skill of CSM1 was already comparable to the NOAA operational model. And if you combine the NOAA model and other sub-X models and the NCAR models into a multi-model mean, then you can further increase your prediction skill. And what I'm showing on the right here is the different versions of CSM2 compared to CSM1. And the numbers in the square parentheses show you the number of ensemble members, because that also changes your prediction skill. But overall, the message is, if you look at week 3-4, for example, that the skill of CSM2 overall is very similar to the skill of CSM1. And there's very little difference between the high top version and the low top version of the model. They're overall on average equally skillful. And these are documented in a submitted paper and review with all the output fields available. And we have a lot of output, including 3-dimensional variables and also variables to look at the upper atmosphere and high frequency output and land and ocean diagnostics. So we hope that these sets are a basis for additional experiments, although they are already useful standalone, especially if you want to get into detailed and process-oriented analysis, because we do have a lot of output. Okay, next slide, please. Okay, so since September of 2020, we've been sending a weekly forecast to NOAA, which contributes to the NOAA week 3-4 experimental outlook. So how that outlook works is many modeling centers, so the 8 modeling centers that you see in the bottom left here, send in their weekly forecast. And then the multi-model ensemble mean is made out of these. And then the forecasters apply their expertise in addition to that, so they understand the model biases and all the quirks that the models have. So similarly to the regular forecast that gets put out, there is a little bit skill to interpreting the models. And then comes out every week the graphic you see on the right. So this is the forecast for June 26th to July 9th. And what you see, the overall multi-model mean is showing largely above average temperatures for the majority of the United States. But if you look at the CSM picture, which is in the top row, the third column, it's actually not showing that. So the nice thing with S2S, in about 3 weeks' time, we will find out how skillful our model was for this particular time period. Go ahead, next slide. One other thing that we're doing with S2S is looking at mesosphere, lower thermosphere predictability. This is an effort led by Nick Peditella in HAO. So he's been using the S2S reforecast for that. And why? So basically MLT variability drives a significant portion of the near Earth space weather. So you can have adverse effects on communication and navigation. And sudden stratospheric warmings we know cause changes to the climate at the surface, but they're also related to variability in the MLT, and which is captured in the reforecast, especially if they're or less before sudden stratospheric warming event. So when you see a stratospheric warming, then you have a mesospheric cooling and associated disturbances. So the predictability, of course, has been shown to get better at the closer you are to the event. And there have not been very many studies before this one that are comprehensive, because there's very few, or actually nearly none, of the models that are running operationally with such a high model top. Okay, next slide, please. Okay, and one more example of how we're using the subseasonal framework. This is a study led by Nick Davis. And what we looked at is the January 2021 sudden stratospheric warming. And what you see here in this panel on the left-hand side is the surface observations following the warming. So weeks 3-4 after the warming, with lots of cooling in Eurasia. And if you look on to the right of that, our standard WACM forecast reproduced that pattern pretty well, with cooling over Eurasia and some warming over the United States and Labrador Sea. And what we've done to investigate the contribution to this from the sudden stratospheric warming, we changed the initial conditions, or what we call completely scrambled the stratosphere, that at our new simulations, the troposphere is nearly the same as, is initialized exactly the same as the original forecast, but the stratosphere is not. And there are no sudden warmings in this scrambled stratosphere forecast, but what you see, the surface patterns are almost identical to the standard forecast. So what we found in this study, that the sudden stratospheric warming did not contribute actually very much to weeks 3-4 surface pattern. And these are the type of studies we can start doing now that we have the subseasonal research framework set up. Go ahead, next slide. Okay, so moving on to longer timescale. So beyond S2S, here we're going to look at this seasonal to multi-annual timescale. And this effort called SMILE has been led by Steve Yeager, focusing on these 2-year predictions. So these simulations are run with CSM2, with CAM6, POP2 with Marble, CI, CLM5, 1 degree horizontal resolution, prognostic ocean biochemistry. And in these simulations, all the model components are initialized with observations, so oceans, atmosphere, and land. There are 4 initializations per year, so in the months of November, February, May, and August. And we're running with a 20-member ensemble. And these simulations have been carried out by Nan Rosenblum and Sasha Glanville. And they have all the reforecasts done from 1970 to 2018. And the forecast will begin soon. So we're looking to put out a forecast starting this initialized in May 2021. Next slide, please. So some very preliminary early results from Jean Wu, who has been looking at these and comparing these SMILE simulations to the DPLE. So if you're not familiar, the DPLE is the Decadal Prediction Large Ensemble that was carried out with CSM1. So it's a similar data set, but in that one, only the ocean was initialized. So the atmosphere and land were uninitialized. And obviously it was carried out with CSM1. And there was a larger ensemble size, I believe, ensemble size of 40 in that data set. So on the left-hand side, you have a correlation scale of the sea surface temperatures for the 2 sets of simulations. And you see for all years, the scale is overall very similar and much greater than persistence. And the root mean square error on the right for all years is also very similar between the 2 sets. However, where you see a difference is in this bottom right plot when you look at just the years that were initialized during strong ENSO events. And what you see there is you see an improved representation of the ENSO evolution in the SMILE forecast. And these are very preliminary results. We just really completed the data sets just a few weeks ago, so expect more to be coming on that. Okay, next slide. So what are the next steps for SMILE? We are beginning to extend the 24-month ensembles forward to present. So we still have 2019 through May 2021 to go. We are extending the November starts to decadal prediction. So the 24-month simulations will now be 122 months. And right now we think we have the computer time for a 10-member ensemble. And if we get more computer time, we'll try to do more. 2014 to 2018 is already complete. And we'll try to go back as far as we can to 1970 if possible. We also have a collaboration with Scripps to produce a SMILE-like data sets with the high top model that was described earlier by Julio, and also I think Ayla mentioned it. So using that higher vertical resolution version to see if there are any changes in prediction skill that come from that high vertical resolution and the QBO, etc. And Steve Yeager is reading the SMILE documentation paper, and we hope for a data release in the fall of 2021. Next slide, please. Okay, another effort that's part of the group is a diagnostic package, and that is led by Judith Berner. So she started with the ClimPred package that's been developed by Riley Bradley, and it's a Python-based verification package for initialized subseasonal to decadal prediction. The goal is to make the generation of these basic verification metrics for these various data sets very easy. An example on the right is just a root mean square error and spread, and that's just the beginning. She hopes to get other more sophisticated metrics in there, and it'll be described on Thursday. But similarly, there's not a single easy to use verification package for any of the initialized prediction simulations, which makes it, it's difficult to get into the subject without it. So hopefully the diagnostic package will improve the ability of more students and people to get involved with the project. Okay, next slide, please. So last but not least, we would love more of the community to get involved in our analysis and also setting up new experiments. So we'll discuss this a little bit more on Thursday during the working group meetings, but we were hoping to carry out additional case studies and additional experiments. We still have a little bit of computer time left for this fiscal year, which ends at the end of September. And we also have new experiments proposed in starting in October, and we would love for more of the community to get involved. So go ahead and email the co-chairs if you're interested. Next slide, please. And our working group meeting will be on Thursday from 8:30 to noon. And I'll just leave these highlights up. So all the key points that I discussed here will be presented. And in addition, Andy Wood will talk about connecting S2S predictions to water management. Dan is going to talk about data simulation. There'll be talks on drought forecasting, bias drift, and a little bit more on the verification package and the high vertical resolution simulations. So thank you.
Thank you very much, Yaga. So that concludes all of the working group updates. And as we said and repeated many times in the presentations, all the other detailed discussions will be happening in the working group and cross-working group meetings. So with that, now we are going to have our last speaker of the day. That's actually Tuesday morning, very early Tuesday morning for Keith Rogers. He's joining us from Busan, South Korea, and he'll be talking about CESM2 large ensembles. So Keith, please go ahead. You can share your screen.
Okay, thank you, Gökhan. And let me put this onto
full screen mode is right there, actually.
Let's see. Oh, there we have it. Okay, great. Okay, can you see the presentation?
Yes, please go ahead.
Okay, great. So thank you, everyone. And I'm going to give you a quick overview of the CESM2 Large Ensemble project, which is the result of an ongoing partnership between the ICCP in Busan and CESM NCAR. And so just a quick overview of our, let me open my screen up here there. So just a quick overview of the presentation. I'm going to give you a quick history of the project. I'm going to give you a few slides of overview of our center and our computing system that was able to do these runs. And then we have just submitted our presentation paper, so there will be a brief summary of what's in there, and it has a focus on forced changes in natural variability. There will also be a brief overview of underway projects, and then some information about access, just one slide on access to model output. Okay, so in terms of the history of the project, Gökhan visited Busan in February 2019, and that was the initiation of the partnership with the decision to, it was a 3-day visit, and there was all sorts of email back and forth with Clara and other people at NCAR about model configuration and number of ensemble members, and we kind of congealed at that point largely. And as the project has developed, we also want to give some special thanks to NCAR collaborators, to Clara and Ayla, for their scientific input through the project, and also for their contributions to experimental design and other more things that don't fit here. Also to Gökhan for his contributions and his input at every stage, his very active involvement and interest, and really real partnership with working with him on this project. And then also to Jean-Francois for what ended up being part of our configuration was that we did some perturbations with biomass burning fluxes, and he had raised some questions about some biases in CMIP6 forcing that led to that discussion. And it's also very important to give particular thanks to the team that really, this sentence has too many negatives in it, but a very positive thing that this team was essential to the outcome of the project. So to Sun-Sung Lee here in ICCP, who ran the model, was involved in the science, and was really essential, as well as Nan and Jim, who were incredibly helpful and constructive and involved in every stage as well. Okay, so just a quick overview of our center and our computer. So the ICCP in Busan is part of the IBS the Institute for Basic Science in Korea, which is a Max Planck-like system that Korea instituted about a decade ago. And the ICCP is the IBS Center for Climate Physics with Axel Timmermann, the director. And the ICCP's mission is to enhance the understanding of natural climate variability and man-made climate change, and to improve the ability to predict climate impacts on the hydrological cycle, ice sheets, sea level, and regional processes. And just for a quick overview of the research themes here, there's ranges from Earth system dynamics, hydroclimate, ecosystems and biogeochemistry, extreme events, deep future, ultra-high resolution modeling, climate and human evolution, and paleoclimate reconstruction. So a broad range of scientific endeavors. And so the Institute itself was founded in 2017, and you get a sense here of the international flavor of the PhD students and the researchers working here. And we're housed in the Busan National University, PNU campus. Our computer is named Aleph the Cray, that was used for the large ensemble, and we also have a speleothem isotope lab here. So just a couple of comments on an introduction to the computing system, to the Cray. So this is the supercomputer in the upper left panel, and it has throughput of 1.5 petaflops, and it also has extensive, in addition to the compute nodes, it also has an extensive storage system with, I think, 8.5 petabytes of storage, and a large analysis cluster, which has been really important for the parallel stuff that's been done to analyze in Python to analyze the model output. So to give you an idea of the throughput with this machine, for the very high resolution model with a 10th degree ocean and a 1/4 degree atmosphere, running essentially full machine, the throughput is 3 simulated years per day. The second item listed here is what we use for the large ensemble. So with 10 parallel jobs for each, we had 14 simulated years per day, which ends up being about 3 weeks for a member. And typically we were actually running about 8 jobs in parallel. And then for paleo runs, for the here there was recently a project. There's a project underway for which 2 million years were run with a lower resolution model. And for that, you can see that you can get 300 simulated years per day with 25 jobs in parallel. So that gives you an overview of what the facilities are. So let's go to the science. So this is our submitted presentation paper, and our title is Ubiquity of Human-Induced Changes in Climate Variability. There are 20 authors, I believe, and from largely from the ICCP in Busan and from NCAR, but there are other people that have really also contributed quite a bit to the project. We're included here, and you'll notice that I think one thing that's very exciting with Will Weider and with Will and Danica, that basically they have brought some also interest from the land modeling side into the project. So that's also been very exciting. And at the bottom, I have just given you the preprint information in case anyone wants to access this manuscript, and it has a DOI. So anyone who publishes before our paper is accepted, this is the reference for the preprint. Okay, so what is available with the CESM2 large ensemble? And this is not complete, but sort of the essential information. We have 100 members over 1850 to 2100 using historical SSP 3.7 forcing with CESM 2.1. We've really gone into detail with saving high frequency output for atmosphere, ocean, land, as well as the other components that are, but these are the 3 where we've really focused our high frequency output to facilitate an ability to look at more timescales than what was possible before. So the first set of 50 members follows CMIP6 protocols for biomass burning. And for the second set of 50 members, we used smooth biomass burning fluxes over 1990 to 2020. I'm not going to go into detail about that now. It has a modest effect on the mean state over 1990 to 2020, but not on the natural variability. And if there's need, I can come back at the end. There's also the MOAR component, which is greatly expanded output for ensemble members 91 to 100 and facilitating a lot of science that, that was incorporated into these runs. So 10 members. And the net result of all this is that we had 5.3 petabytes on our system of the original output, and then approximately 1.8 petabytes as it appears on ESG. So we have was really a tremendously demanding on the system the requirements for the infrastructure. There was also a mix of micro and macro perturbations for initialization. Again, I won't go into details with that. Some of that was inspired by community polling around the time of the Large Ensemble Workshop in 2019 that was put on by Clivar in Boulder. And again, I could come back to that at the end if there are any questions, but that's not going to be the focus of this presentation because it's going to be brief. Finally, just for the model version, the CESM 2.1, it's documented in Gokhan's presentation paper for CESM 2. Okay, so here is the first figure from our presentation paper, and this is really a bunch of time series of largely global quantities, showing how our model compares to observational products and just giving a sense of the behavior. And the ensemble mean is shown as solid lines, and then we have two different levels of shading for 1 and 2 standard deviation levels of the variability of the individual ensemble members. And so this is something you can, if you want to go into detail with this, please read the presentation paper. But what we're interested in here is just that for the cases where there's data, where there's the red dots, we can see that there's, it gives you an illustration of the correspondence of the variability and the observations to what you can see with the 1 and 2 standard deviation variability in the model. So no really big surprises here, but this sort of gives a justification for the model having reasonable background natural variability. And so stepping through, there's top of the atmosphere radiation, then there's precipitation, the TOA radiated flux, and there's precipitation anomaly, surface air temperature anomaly, heat content anomaly, and then there's the southern and northern hemispheric sea ice, AMOC, and NPP in the ocean and land, and then the CO2 fluxes over the ocean and land. Okay, this is really the getting to our core interest of how natural variability changes in the model. So what we've done here is this is showing for 5 variables, there's the map in the center which shows mean state changes in temperature and shading, and between the decades highlighted, the historical and the future. The temperature changes are shaded, so you can see the Arctic amplification and the growth of a stronger gradient in the equatorial Pacific, and you can see the warming hole in the North Atlantic and a number of other features, and the dots represent precipitation changes with bluish colors for increases in, darker blue colors for increases and lighter blue colors for decreases. This is really meant to be a point of reference for the different spectral analyses that are shown here. So there are 5 variables that are indicated by boxes that are connected to specific regions. And just to highlight some of these variables, let's start in the upper left with California fire counts. So what we have here is a spectral analysis and a PDF. And remember, so as it's marked here, remember as I go through this, the blue is for the historical and red is for the future. So for California fire counts, the spectral analysis shows this increase across frequencies of variance, and go from the timescale of storms and number of days on the right to the 30-year timescale of the analysis intervals here. So what we will notice here is that there's somewhat of a frequency independent change in variance, and the corresponding PDF shows that for the red relative to the blue, the the likelihood of events with higher fire counts is greatly increased. You can see with this positive definite variable. So then we shift to surface chlorophyll concentrations in the North Atlantic, effectively the subpolar gyre. You can see that there is blue to red. There's in this region, there's in fact a decrease in variance across a wide range of timescales, and that this is, we believe this is associated with the slowdown of the AMOC. And so this is also revealed in the PDF that's on the right side in that upper right panel. You can see that as you go from blue to red, you have less the occurrence of, you have a shift to less high chlorophyll concentration events. Okay, so shifting to the Amazon NEP for the lower right two panels, NEP is really the net effect of photosynthesis and respiration in the natural terrestrial carbon system. And here we see an increase in variance from blue to red. And the associated PDF here has, you can see a change in the shape of the distribution. The bottom panel is Nino 3.4 precipitation, where again we see between blue and red, we see an increase in the variance over a wide range of the somewhat of a frequency independent shift in variance. And the PDF gives you again for this positive definite variable an indication of in the future some really substantial rain events become more common. And finally, Nino 3.4 on the left side, you can see here actually in contrast to some of the others, there's less of this frequency independent shift in variance, but you can see in the ENSO band, you can see that there is a shift in the frequency of ENSO, and the PDF reveals this shift in the distribution. So what we're going to do in the next slide, I will point out also that with the Nino 3.4 precipitation in the bottom figure, one of the really wonderful things about using a lot of ensemble members is that this highlights the combination modes that were described by Malte Stucker in a paper, I think it was 7 or 8 years ago, become this nonlinear interaction between the seasonal cycle and ENSO. The shifts in ENSO frequency show up. You can see the shifts in ENSO frequency and amplitude reflected in the C modes, the combination modes. And again, this is discussed a little bit in the presentation paper. So overall, the frequency independent shifts in variance are ubiquitous, and we have somewhat of an interpretation in the presentation paper on this. Okay, to go very quickly through a little bit more detail on the Nino 3.4 region. Here we show wavelet analysis as well as seasonality information for the Nino 3.4 SST and precipitation. So for SST, let's start with the upper left panel for a wavelet analysis where the ensemble mean has been removed and the seasonal cycle retained. And this is effectively an ensemble mean of wavelet analysis over individual members. What you can see is a shift in the ENSO period from approximately, this is ranging from 1960 to 2100 on the horizontal axis, and the period is on the vertical axis. And there's a shift from a period of approximately 3.5 to approximately 2.5 years over the duration of this interval. And interestingly, it's non-monotonic. You can see that it's the variance is largest in the mid to closer to the middle of the 21st century. And you can see for precipitation in the right panel, similar shift in the period, but more of a monotonic increase in the variance over this time period, as well as in the seasonal cycle. You see a stronger indication of increased variance at the seasonal timescale. The lower panels show in the middle row, we can see for the ensemble mean SST, the evolution of the seasonal cycle between 1960 and 2100. And the red dots indicate the timing of the, for each year of the maximum temperature, and the blue dots the minimum. And so you can see an indication, we can come back if there's interest, there's an indication of between several weeks and a month or more of a shift in the seasonal cycle. And you can also see in precipitation, you develop a secondary maximum in the second half of the 21st century in precipitation in February, as well as the one that had developed in more towards April and May. And then in the lowest, in the bottom row, you can see what, for the ensemble statistics here, it's the cross ensemble standard deviation of SST and precipitation using daily mean output. And what you can see here in the lower left panel with SST is you can see the time of maximum standard deviation. So the red dots at approximately January. So it's the time, it's the time of maximum ENSO variability, the seasonally stratified time. And there's an indication of a shift towards, by a matter of weeks, of the timing of the maximum SST variability. And likewise in precipitation, you have some curious patterns, and you have the intensification. You can see in the maximum, you can see the intensification of rainfall. So this is just an illustration really for this kind of iconic region that's so often used of the kind of ensemble statistics and what they reveal about changes in amplitude, phase, and frequency. Okay, next we're going to look at some analyses of patterns, the patterns that result from analyses of again temperature and precipitation. And in the upper, what I want you to focus on here is the background shading is the colors are effectively for the historical period. These are the standard, the cross ensemble standard deviations of temperature and precipitation in the upper panels. And then the dots represent the changes. So let's focus on the dots here. This is all using annual mean and then averaged across the respective intervals and differenced. So for temperature, whereas we see, for example, in the equatorial Pacific, a modest decrease in the variance, and over the northern continents as well, and parts of the Southern Ocean, a decrease in over the Arctic and over the Amazon and over the subpolar North Atlantic, an increase. So we see more of a diversity of changes in the variance. For precipitation on the right panel, it's more generally an increase in variance as indicated by the predominance of the red dots. And so this is, in our presentation paper, we have a supplementary figure where we've done this for a number of other variables as well. This is just a view of seasonal DJF temperature and precipitation here. We've dealt with the annual mean in the supplementary if you want to look at that. So let's transition to the lower panels, which show the absolute change in the ensemble correlation. Again, the dots of the Nino 3.4 SST and global surface temperature on the left and precipitation on the right between these two time periods. So again, the correlations for the early period are shown in the background shading, and the changes are shown as dots. So just as a guide, for regions where the dots and the background shading have the same color, we can interpret this as a strengthening of the teleconnections. And where there's opposing colors, it means that there's a weakening. And so for temperature, you can see that there are regions such as over much of Africa, as well as over much of South Asia. There is a strengthening of the teleconnections in temperature, tropical Atlantic as well, and then there are regions where there's a weakening, for example, in the western tropical Pacific. So let's look at precipitation, and there you can see again same principle, that the dots represent the changes, and where there's a mismatch in color between the change and the color for the earlier period, there's a weakening of the teleconnections, and where the colors are the same, there's a strengthening. And so you can see that over parts, for example, I mean, there's a rich patchwork of changes here. Just taking as a few examples, the Western US and Southern Canada show some indication of weakening, and over Africa, there's an enhancement, and over the Amazon, there's somewhat of an enhancement. And so again, there's a rich set of structures here that are revealed through the large ensemble, and the interpretation is largely that these patterns reflect an eastward shift in the convective centers in the equatorial Pacific, and also to some extent the modulations of the Niño 3.4 index itself. And just to draw your attention to the fact that there's not a direct correspondence, there's not a strong pattern correlation between the lower right panel and the upper right panel. So there's, as we surmised before, that there's a lot of other stuff besides ENSO going on in the global modulation of variance in the model.
If you have a few minutes left.
Okay, so I'm almost done. So this is the final science figure, and this is just showing for the NEP, the net ecosystem production over land over 50 degrees north to 80 degrees north. And this is the ensemble mean view in the upper panel. So this is an integral. And what this effectively tells us is time, the early periods are in blue, the later periods are in red. So positive is uptake by the land, a net uptake, and negative is a net release. So the shifting in the most important feature here, in addition to the modulation of the seasonal cycle, which increases through time, is the expansion of the zero crossing interval between the time over which you have positive uptake over land, the growing season, by this aggregated view, expands by 2 weeks in the spring and 1 week in the fall. So we have effectively a net growing season length increase. And the lower panel shows for the individual ensemble members the timing of the zero crossing, the maximum, the second zero crossing, and the minimum. And you can see that probably the most emergent one is the first zero crossing, the spring crossing, and in that the signal relative to the natural variability is probably emergent over the first half of the 21st century. Okay, so in summary, we focused on the ubiquitous signal of frequency independent changes in variance we saw first through the spectral analysis, and we documented changes in frequency and amplitude of ENSO and phases of the seasonal cycle with the Niño 3.4 SST and precipitation, pronounced patterns of force variance and force covariance changes for ENSO and temperature and precipitation, and force changes in phenology, so the phasing and amplitude of the seasonal cycle in terrestrial ecosystems. That's the science summary. And this is the underway research with CESM2 large ensemble. So in both November of last year and February of this year, we had a virtual workshop with participants that were international participants that were doing analysis with the model output, and some of the themes that developed through that work were for changes in variability, mean state changes, initialization, impact of external forcing such as volcanoes on variability, teleconnections, and extreme events with a number of different themes. And you should contact us if you want to be put in touch with people that were working. If you're interested in these topics and you want to find out what has been done, let us know. And we'll put you in touch with the individuals that have started working on these questions. And then the bottom here, we have our own internal laboratory projects that are underway that will be submitted in 2021. So there's MJO, abrupt change in wildfire, force changes in lakes, wet bulb temperature, and so monsoon teleconnections, force changes in AMOC, and force changes in nutrient cycling and Redfield ratios. So let us know if you want to discuss any of this, and be happy to. And finally, I think you've probably already seen this is already up, that it's now documented, the availability of the large ensemble data set. So thank you very much. This is the end of the presentation. Thank you.
Thank you very much, Keith. Maybe you can go back and put that slide again, so we'll send it as a separate email as well. I mentioned it this morning in my presentation that the data sets will be available today, but I didn't provide any further details. So if people are interested in, they can just go to the CESM2 large ensemble or search for it. It'll show up now. There is no protection, so you should be able to get to all the data sets. And please use the DOI number that Keith provided for reference purposes. Any questions for Keith? It's getting late in the day here. People are getting tired. They are zoomed out. This is 8:30 this morning, and I don't see any questions. Just a minute. Okay, if there are no other questions, so Keith, thank you very much. And again, I think we will send an email to the CSM community with additional information on these data sets. And I think most of them have been transferred already from Korea. So the data size is about 1.8 petabytes that we'll be serving from NCAR. That's a lot. And the total data volume is about 5 petabytes. And the remaining data sets will be available from ICCP, I believe. You have to fill out a form, not necessarily to get permission, but because data needs to be essentially reduced sort of or in bite-sized pieces so that they can be served. Okay, so with that, I think we'll conclude today. And let me just check here. So we'll start tomorrow morning with atmospheric model working group and land model working group sessions. They start at 8:30. And Elizabeth, later this evening, will be sending you Zoom links for tomorrow's sessions. So thank you very much for sticking with us. And thank you very much for your interest in CESM. Have a nice evening or morning. Bye.